Welcome to CCNA 200-301 course. I'm super excited to share with you that I've decided to prepare a course for the new CCNA 200-301 exam, and I can't wait to share more information with you. But before I get into it, I want to give you my quick background. I've got a bachelor's in computer information systems, and I was pursuing my master's degree in network security, and midway I decided to drop out, and instead I decided to pursue certifications because I was already working in the industry as an engineer, and I thought certifications would provide better value for my money and time than a degree would. And it turned out to be a great decision. And that's exactly what I'm passionate about. And I want to share this with you as well. And hopefully you can do the same thing in your career and become extremely successful. So what I ended up doing was I ended up picking an A+ certification and Security Plus certification from CompTIA. Along the way, I picked up a couple of Cisco certifications like CCNP Enterprise, which used to be called CCNP Routing and Switching, CCDP, CCNP Service Provider, CCNP Data Center, and also a couple of Microsoft certs. I feel blessed to have had the opportunity to work for some of the largest Fortune 500 companies. And finally, I've been teaching CCNA and CCNP classes for over 12 years. And throughout my career, I've been fortunate enough to coach and mentor many students and engineers who ended up achieving great success in their careers. I'm humbled by this opportunity presented by God, and my goal is to also help you do the same. Now back to the course. So there are 6 sections of the entire course. Section 1, Network Fundamentals. Section 2, LAN, Wired and Wireless. Section 3, WAN, Routing. Section 4, IP Services. Section 5, Security Fundamentals. And finally, Network Automation. This is going to be an amazing course, guys. I am super excited. And if you're ready for your career to launch like that NASA spaceship, get ready. Let's go. Section 1, Part 1, Network Fundamentals, OSI Model. 2 things I'm going to cover in this video. What is a network? And we'll then do an OSI model deep dive. The 4 basic elements of any network are rules, medium, messages, and devices. Let me explain. So let's say Bob wants to talk to Alice. Bob has a message, like an email. So this right here would cover the message element. Bob wants to send this email to Alice. Well, Bob is using an end device, right? He's using a desktop in this case, so that covers the device piece. And what's in between Bob's computer and Alice's computer, that includes the ISP in the middle and their home networks and all that, that would be considered the medium. And finally, for all this to work seamlessly, this entire thing, we need rules. We need a common set of language that is spoken on both sides, on Bob and Alice's side, for the systems to be able to understand what Bob sent and be able to decipher that message and successfully deliver it to Alice. To do a little bit of a deep dive and to give you a little bit of a more real-world perspective, think about it. At home, you've got a PC. That PC connects to a switch. That switch connects to a router. And that router connects you to your ISP, which could be Comcast or AT&T or whoever have you. And this entire element, there are a couple of components I want to point out here. You got the endpoint right here, which is the PC. Could be phone, could be tablet, whatever. You got these cables in between. These cables are connectivity or medium, and these are important because these are the basic infrastructure element that allow communication to happen. You got to have wires or some sort of wireless signaling to be able to communicate your messages. And then we also need a switch, so that's right here, and we also need a router. Now the difference is switches create what's called a LAN or a local area network, and we'll talk a lot more about that momentarily. And routers create what's called a WAN or a wide area network. And wide area network is a collection of different LANs connected together. And that's what, at a high level, we have in a network. Next element, OSI model, also known as Open Systems Interconnect Model. It was introduced by ISO, the International Organization for Standardization, back in 1970s. So it's been around a while. It's a reference model that talks about how the network should behave. And it's a 7-layer model. And you can see the layers highlighted here. We have the overall model divided into 2 different parts. You got the top layers. These are called the host layers. And you got the bottom layers. These are called the media layers. Bottom layers are the ones we are primarily concerned with as network engineers. Let's start at the bottom and work our way up. At the very bottom, we got a physical layer. Right above that, we got a data link layer, network layer, transport, session, presentation, and then finally, application. One of the mnemonics you can use as a memory aid is, if you start from top to the bottom, is all people seem to need data processing. In this mnemonic, A stands for application, P stands for presentation, S stands for session, T stands for transport, N stands for network, D stands for data link, P stands for physical. So this mnemonic can help you remember the order of the OSI layers. And this is very important from an exam perspective. Let's dig a bit deeper. This time around, let's look at the topmost layer. What we have at the topmost layer of the OSI model is application. Now, we're not talking about an actual application, but the function that the application serves. For example, you might want to send an email. That would be a function on an application layer. Or you might want to do a file transfer through FTP. Or perhaps a telnet. That's how you log into a router remotely and be able to type commands and get feedback via CLI. Or HTTP. You open up a browser and you want to surf web. These are all different functions that are performed at the application layer. A layer below that is a presentation layer. This is where things like HTML comes in. This is where JPEG comes in. So when you go to a web browser and you open up an image, whether it's going to be a JPEG or a PNG file, it's determined by the presentation layer. This is where MP3 comes in, AVI, all that good stuff. Layer below that, session, this is the inter-host communication layer. This is where things like network file system and session initiation protocol comes in. This is where operating system lives. Layer below that is a transport layer. And this is responsible for end-to-end connections and reliability. This is where things like TCP, UDP, and RTP, or real-time transport protocol, come into play. A layer below that is called a network layer. This is where path determination and IP is located. So here is where IP comes in and routing protocols like REP, OSPF, EIGRP, all that stuff. Layer below that, at layer 2, we got ourselves MAC and LLC. And we'll talk about those details in a moment. This is where Ethernet comes in. This is where ARP lives for the most part. But ARP is kind of unique in a sense that it's got the layer 2 functions and it does communicate with the upper layer at layer 3. Because remember, ARP, or Address Resolution Protocol, is a mapping between an IP address and a MAC address. And we'll talk through those details later when we talk about layer 2 section. This is where VLAN comes in. It's a layer 2 construct. Frame relay, PPP. These two are wide area network technologies, and we'll talk more about them later in the course. And finally, at the physical layer, which is layer 1, we got things like Cat5e, we got multi-mode fiber, we got single-mode fiber. So that's the OSI model on the left-hand side right here. On the right, we got this model called TCP-IP model. And there's 2 different variations of this. If you look at the old school one, it was divided into 4 different layers. But the new layer that's also highlighted in the new CCNA book is a 5-layer TCP-IP model. And that's the model we use today, where application, presentation, and session are combined together into a single layer called application layer. Transport remains transport. network is considered internet, or we could interchangeably call it network. One below that is data link, and finally physical. Now for exam purposes, guys, you guys need to keep this in mind. So make sure that you guys memorize the OSI model, because this is very important. Now, the rest of this session is going into the details, into the depth of OSI model. So if what I just talked about didn't register with you, hang in there. It is going to make a lot more sense as we do a deep dive into each layer of the OSI model. Here's another important element you guys need to think about, and that's the encapsulation process. Before I describe the encapsulation process, another term that's important for you to understand is called PDU, Protocol Data Unit. And data within the OSI model at each layer is called PDU. So PDU for layer 7, PDU for layer 6, PDU for layer 5, so on and so forth. So that's a generic name given to data at each layer. That's how it's represented. The top 3 layers in the TCP-IP model are combined into application. This user has an email that needs to be sent to the computer on the right. It's going to send data. When this data gets to the transport layer, or layer 4 of the OSI model, is called a segment. And transport layer is going to add a header to it, a TCP header. When it gets to the network layer, it's called a packet, and it's going to add an IP header. When it gets to the data link layer, it's going to add Ethernet header to it. And finally, the bits that get transported across the wire to the other side. And then the other side looks at the bits, looks at the MAC header, removes it, then sends the data upstairs, goes to the LLC header, which once again, LLC and MAC combined are Ethernet. So once the Ethernet header is stripped off, the packet is sent to layer 3, looks at IP, removes the IP header, sends it upstairs to the transport layer. Transport layer looks at the TCP header, removes it, and finally sends the data to this guy right here, who's able to read that email. This is how this communication happens. Now, the process on the left is called encapsulation, because we're putting envelopes or headers on top of the data. The best analogy I can give you is the post office analogy. When you take your package to the post office, they stick a label on it, and they provide you with the tracking number. Think of these headers that are added to the data as envelopes. And there's a layer of envelopes that get added when the data travels from north to south, from application down to the physical layer. That's called encapsulation. But when the bits get to the other side starts to remove the headers. That's called decapsulation, the removal of headers. And the addition of headers is called encapsulation. So I just want to make sure that you guys get these two concepts, because most likely it's a good exam topic, but also from a real world perspective, it's good to know. Now, what's the purpose of the OSI model? For me, it's 3 things. First, interoperability. Now, that's a mouthful, but what does that mean? That means if I take a Cisco switch and connect it to an Arista switch, when they're connected together, they need to be able to talk to each other. I don't want these companies using their own proprietary technologies, because then that locks me into that vendor, and I do not have the ability then to do anything. And as an enterprise, as a government, or any type of business entity, I need to have that flexibility to be able to interoperate. So that's what the OSI model gives us. The second thing it gives us is a common set of language that can be used by these different vendors to continue producing great networking products that operate with different set of standards. So for example, layer 1 has its own physical layer standards, and layer 2 has its own standards, and layer 3 has its own standards. So when you're looking at a device that operates at layer 2, for example, it is only designed with layer 2 in mind. It doesn't have any intelligence of layer 3 or layer 4 or any of the layers above it. All it's concerned with is layer 2. So that is an important element. And that's what also helps with the interoperability, because that common language then allows these software engineers and these hardware makers to produce products that can talk to each other and integrate and interoperate. And finally, for me, the big one is troubleshooting. So let's say if you have a user who says, I can't access any website. Well, that means their internet is down, right? That's the first thing that comes to mind. But how do we test if it's just the internet or maybe something else going on? What we do is we have two different approaches. One called top-down approach from a troubleshooting standpoint, and the other is the opposite of that, bottom-up approach. And with these approaches, what that means is top-down means you start at the application layer and then you work your way down. Bottom-up means you start with the physical layer and work your way up. Both approaches are valid. It just depends what you are troubleshooting, and based on the information that's given to you, how fast you can get to the resolution of the issue that you're trying to address. That's what it comes down to. And as network engineers, like I said, we're primarily concerned with 4 layers. So for us, that's the focus area, because layer 5 through 7 is primarily used by software developers and programmers for designing and writing code. All right, so now let's do a deep dive into the application layer. So the very first thing I want to talk about from an application layer perspective is DNS. So let's say you type in cisco.com in your browser. The first thing that's going to happen is your local machine is going to check its local cache. If that DNS entry is available, it's going to use it. But assuming it's not available, it's going to go to what's called an IDS, or internal DNS server. Now, if you're a home user, most likely you don't have a DNS server at home. Your IDS could be most likely your service provider DNS server. Your service provider DNS server, if it doesn't have an entry, it's going to forward that DNS request for cisco.com over to root level domain servers. There's a handful of root level domain servers on a global scale, and the root level domain server is going to get that request and go, well, I don't know what the answer is, but I do know someone who can point you in the right direction. It redirects traffic to top level domain servers, and these are .com, .org, .gov, .mil. In this case, it's .com, so it refers to the .com. And then the top level domain servers redirect our request over to the second level domain servers. They're also called authoritative servers. And these are the servers responsible for hosting the actual website. What's going to end up happening at that point is that the IP address for cisco.com will be provided to our internal server, and eventually we're going to get that reply and we're going to end up getting that web page. Now, all this happens in a blink of an eye. This is a very, very fast process. And another thing I want to talk about, kind of taking a step back, is why have a DNS process to begin with? Well, guys, if you think about it, computers only understand zeros and ones, binary code. Whereas as human beings, we're good with names more than numbers. So for me, it's a lot easier to remember cisco.com than remembering, let's say, 208.11.2.22. Okay? It's going to be a lot harder for me to memorize this. And then, let alone all the different websites, dozens of websites that I surf in a day, it's just not humanly possible. So what we do instead is we have created this domain names system, or DNS system, that maps names to IP addresses. And this whole process that I just finished talking about, let me go back to it, is the whole mapping process. And all these servers are responsible for redirecting traffic if we don't happen to have that information in our local cache. In most of the instances, if you're pointing to your local service provider DNS, with all the millions of requests coming into them, most likely they will have that answer. So it should be a fairly fast process instead of having to bounce around all these different servers over the internet. Another example at the application layer is the DHCP, or Dynamic Host Configuration Protocol. So when you plug your client into a switch, what ends up happening is it sends what's called a DHCP discover request to the DHCP server. The DHCP server responds back with the DHCP offer. Then our client responds back with the DHCP request. And finally, the server responds back with the DHCP acknowledgement. At that point, we pick up an IP address. And that's what DHCP does, right? It assigns IP addresses automatically. We don't have to manually assign IP addresses. We just plug in our machine and it gets an IP address magically. But there is no magic. I mean, it's all DHCP that's taken place. Another mnemonic that can help you from an exam perspective is DORA. What is DORA? Discover, D, offer, O, R, request, A, acknowledgement. So that's the DORA process for DHCP. Now let's talk about transport layer. Transport layer utilizes port numbers to keep application sessions unique by creating a network socket. And what's a socket? It's a combination of source and destination IP and source and destination port number. Two common transport layer protocols that exist at this layer are called TCP, or Transmission Control Protocol, and UDP, or User Datagram Protocol. UDP is a connectionless protocol defined in RFC 768. It sends data as best effort. The biggest advantage is that it's got low overhead, only 8 bytes header, and the application examples are DNS, your voice, video. TCP, on the other hand, is a connection-oriented protocol defined in RFC 793. It operates reliably, but it comes at a cost. So instead of 8 bytes of UDP, we're looking at 20 bytes of overhead in the header. And the examples include web browsers, HTTP basically, email, file servers, etc. Let's quickly take a look at UDP header. I'm not going to go super deep because I'll have plenty of opportunity to do that throughout the course, but just to give you a quick overview, source port and destination port is important, especially the destination port, because that's what determines what we're trying to access. So for example, if it's DNS, that's port 53. That's what DNS is mapped to. So if you want to access DNS, that request is sent over port 53. Now that happens behind the scenes. We don't see it, but that's how it works. And as network engineers, you're expected to know this level of detail. Now, another big thing is the length. As I mentioned, it's 8 bytes. It's super lightweight. Now let's look at TCP next. Once again, source port, destination port. Destination could be, for example, HTTP. Maybe you want to go to google.com. That's port 80. If it's HTTPS, that's port 443. The big thing here is that it's 20 bytes. Otherwise, I mean, if the differential was not that big, we would have been better off just using TCP everywhere because it's reliable and there's sequence numbers and acknowledgements sent. Whereas with UDP, we don't have sequence numbers, we don't have acknowledgements. So if we lose packets, they're lost forever. With TCP, we have sequence numbers. We can rearrange if packets arrive out of order. With acknowledgements, we can go ahead and acknowledge that we have received some certain number of packets and all that. And there's some additional elements like windowing and things that I'm going to get into next. There is this organization called IANA, the Internet Assigned Numbers Authority, and they have this RFC 6335 that defines the different ports that are available. And in altogether, the total number of ports we have available to us are 65,535. To start off with, we have what's called the well-known ports. And these are 0 through 1023. These include SSH 22, Telnet 23, SMTP 25, etc. Then we have registered ports. These are ports that are used by services like Radius, Network File System, SIP, and they go from 1024 to 49,151. And finally, we have dynamic or private ports. They're also called ephemeral ports. And the reason they get the name of ephemeral is because they're very short-lived. They're dynamic and they're automatically allocated by our system. So for example, in your computer, every time you're trying to access different applications and all, your operating system can pick a port from 49,152 through 65,535 and just dynamically allocate it to the different sessions that you have opened. Could be different web pages or different video streams or whatever have you. Another important element from an exam perspective that you should memorize is this chart right here. You've got about 20 ports or so that you're supposed to know by heart. So that includes FTP, which is 20, 21, SSH, which is 22, Telnet is 23, SMTP for email is 25, TACX is 49, so on and so forth. It may seem overwhelming at the moment, but trust me, as we continue going through the course, we're going to continue referencing these different protocols and these different port numbers over time. As you continue going through your CCNA studies, this information will get pretty solidified in your head. And what you should do before you take the exam is memorize these to the best of your ability, because most likely there's going to be at least one or two questions that you will be asked. And this is also really useful information from real world perspective as you're troubleshooting and doing different things, configuring access control lists, for example, and setting up security on your firewall and allowing certain ports and blocking certain services. This information can help you identify. Instead of having to constantly look this up, if it's in your head, you can just quickly make that happen. As I mentioned earlier, TCP has the ability to be able to reorder packets or segments at the destination. So in this case, as you can see, the PC on the left, PCA, wants to send packets to PCB. What's going to end up happening is it sends 6 segments. When it sends data, data is divided into different segments. Let's say 6 segments. When these segments are sent, each segment could potentially take a different path. One segment could, for example, take this green path, and the other segment could potentially take this red path, for example, to get to the destination, and so on and so forth. End result being, when these segments arrive at the destination, they may be completely out of order. But TCP has the ability to reorganize or to reorder these segments because of the sequence number field in the TCP header. Another important concept from a TCP perspective is a TCP three-way handshake. What does that mean? Well, if Bob wants to talk to Ellis, Bob says, "Hey Ellis, I want to talk to you," and sends a SYN message. Alice gets the SYN message and says, "Okay, Bob, let's talk. I also want to talk to you." She sends a SYN ACK back to Bob, and Bob responds back, says, "Okay, thanks, and let's start communicating." Bob sends an ACK back. So this is also known as SYN ACK ACK. That's the three-way handshake that happens when any communication starts. Now, another example here, let's say Bob has a session open to google.com and Bob no longer is interested. He wants to go ahead and close that session by closing his web browser. What's going to end up happening is when Bob kills that tab in his Chrome browser, he's going to send a FIN message. Once again, that's one of the fields in the TCP header. The server is going to get it, and the server is going to send an acknowledgement back. And then the server will eventually send out a FIN or finish message, and it's going to go ahead and receive an acknowledgement back from the client that it's ready to close. At that point, the communication is properly closed on both sides, and the session is terminated. There's another cool concept called TCP windowing, where a sender and receiver negotiate a window size. So let's say in this case, the window size happens to be 3,000 bytes. So the sender is going to send 2 different sequence numbers along with sending segments. So it's going to send a bunch of packets shoved into a segment 1,500 byte long to the receiver, and send another segment of 1,500 bytes to the receiver. At that point, the receiver is going to acknowledge back, telling the sender that I got it. Then the sender is going to go ahead and continue the process, and the receiver is going to respond back saying, I got it. Now, this process is going to continue repeating itself until we get to a point where the receiver is no longer able to receive packets. At that point, it tells the sender to back off, and that's what's called a sliding window. Because we have the ability to be able to slide the window up or down depending on whether or not the receiver is able to receive more or less segments. If they're able to receive more, we keep sending them more. If they're not able to receive any more, we slide the window down and adjust. Now, what's happening when the receiver slows down is, remember, the sender had a momentum built, and the sender was sending a lot of information at a very fast pace. It's going to start storing stuff in its buffer. And the sender, let's say if it's connected to a router has a buffer. And the buffer ultimately has a queue. So the information sits in a buffer and it sits in a queue. If the queue gets full, then what ends up happening is we experience a tail drop, meaning we start to drop packets, and that's not good. Hopefully, we won't experience tail drop, and we'll have the ability to retransmit and continue forwarding packets. But with TCP, remember, the key with TCP is it has the ability to retransmit, so those packets are not lost forever. We can always retransmit if you don't receive an acknowledgement number back. And this whole tail drop and queue and buffer is QoS. We have a big QoS section. Later in our course, we'll go super deep into quality of service there. Now let's shift our focus to layer number 3, the network layer. Two main functions of this layer are logical addressing, IP addressing, and packet forwarding. And this process is called routing. The whole idea is we want to find the most optimal path to deliver the information to the other side. Once again, IP address is a logical address assigned uniquely to each device on a network. And a couple of things to keep in mind from a layer 3 perspective is it's connectionless. No connection established. It's best effort, unreliable. If the packet gets there, it gets there. If it doesn't, it can always be resent. But remember, at layer 4, if you're using TCP, we have the ability to be able to resend. But if you're using UDP, if the packet gets dropped, then it's lost. And finally, we have the media independent component. Now let's dig deep into each of these elements. So the first thing is the connectionless nature of IP. So what does that mean? So when you have a letter and you throw it in a post box, the sender doesn't know if the receiver is present, if the letter arrived, and if the receiver can read the letter. As a sender, you cross your fingers and hope that it's going to get to its eventual destination. Now, what's happening on the other side is the receiver doesn't know when it's coming. That's how IP operates at layer 3. Next attribute, it's best effort. So what that means is when this guy A wants to send packets to the guy on the right, B, packets are routed through the network as quickly as possible. Some packets may get lost along the way, but remember, IP is not concerned with reliability. If it gets dropped, it gets dropped. TCP will take care of it. If it's UDP, it gets lost. As an unreliable network layer protocol, IP does not guarantee that all sent packets will be received. Other protocols manage the process of tracking packets and ensure their delivery. Like I said, TCP, for example. That's the upper layer. And finally, the media independence component. And that has to do with the fact that whether you have copper, Ethernet, or copper serial, or optical fiber, or copper Ethernet, or wireless, regardless of the media type, IP packets are able to get from the source to the destination. That's what ultimately it's all about. Sending packets from source to destination and vice versa. That's what it comes down to. Next, let's look at the IP header. So IP header is 20 bytes in length. It's got a couple of interesting fields in there. So type of service has to do with quality of service. Like I said, we have a big section, so I will reserve those details when we get into QoS. But it's how the traffic is treated and prioritized in our network. Also, we have TTL, or time to live. That's an interesting field. If we didn't have this field, and if we had some rogue packets that had no destination, we could have packets loop around in our network forever and ever and ever. But at layer 3, after they get to the value of 255, the packets just automatically die at that point. Then we have the protocol field that determines, whether it's, for example, EIGRP or OSPF or L2TP or UDP or ICMP. That's determined here. Other two important fields are source address and destination address. That is very, very important. So ultimately, it's all about sending traffic between source and destination. Like I said earlier, that information is located here. And all of this is based on RFC 791. If you want to learn more, check out this request for comment. And by the way, this RFC, there's this organization called IETF, which stands for Internet Engineering Task Force. They are responsible for writing RFC standards or request for comments. And the whole idea is that the different layers of the OSI model, they develop the different standards. And they don't tell you exactly how things operate, but they do tell you from a high-level perspective how things should look like when you're trying to send traffic from source to destination. So they get into those type of details into these RFCs, and different vendors can use this information and develop their products accordingly. Now, another element at network layer is routing. It's the process of forwarding information across the network from source to destination. It's composed of two fundamental elements, and that is determining the most optimal path. That's the job of a routing protocol. And then transporting packets through the network. That's the routed protocol. What's the difference? Routing protocols are the ones that establish a communication channel end to end. So you can think of RIP, EIGRP, OSPF, ISIS, BGP. And then you have routed protocol, and that's the protocol that is responsible for actually carrying the data. And that's IP, IPX, AppleTalk. Now, IPX and AppleTalk are pretty much dead. IP is the de facto standard on a global scale. So IP is what actually carries the data. And that's what we ultimately care about. It's the data. But the routing protocols are the ones that define the path. So it's the way I look at it is routing protocol is like a road. So if you go on a highway, you got this road, this path, right, that you ride on, and then you got a car. To me, the car is the routed protocol like IP, and the routing protocol layer is responsible for forwarding frames. So now we're no longer concerned with packets. The packets are now called frames. And this layer is composed of two sublayers, LLC or Logical Link Control. This layer interfaces with the network layer. And then we have the MAC or the Media Access Control. This interfaces with the physical layer. So to kind of think about it conceptually, what we have is the LLC, which talks to layer 3 of the OSI model. And then we got the MAC or the media access control, which is the hardware address, also called the MAC address, talks to the physical layer, which is layer 1. So data link is a very crucial layer that has this responsibility for speaking both to the upper layer and to the layer below it. And finally, the physical layer. I'm going to go really deep into the physical layer because I think it's a very important topic from a real-world perspective. So what happens at the physical layer is encoding. We take the bits and we encode them into patterns recognized by layer 1 devices. And we also have signaling here that determines how to represent the binary bit on a specific medium. So for example, if it's copper, then we'll be looking at sending voltage. And that's how it's represented here. As you can see, encoding is the ones and zeros. Signaling is either the positive voltage or the negative voltage. And ultimately, we want to have an average voltage of 0 on a wire, especially if you look at the AMI standard. And then we got the media. Now, going a little bit deeper into the signaling patterns, all it comes down to is how the data is represented. If there is a voltage on the wire, that's a 1. If there's no voltage on the wire, that's a 0. Once again, voltage on the wire 1, no voltage on the wire 0. And this whole sequence is considered a signaling pattern. And we have different types of signals. We have the electrical signals. We have the light pulse fiber signals or the photons. And then we got the wireless microwave signals or radio frequency signals. Now let's talk about media. So the actual physical cables, we have the UTP or the unshielded twisted pair cable. If you haven't seen it, I'll show you a real world picture in a moment, but it's the most common type of Ethernet cable that you find either at home or at work. What we have is color-coded plastic insulation for wires and electrically isolates wires from each other and identifies each pair. It's a twisted pair and it protects the signal from interference. The outer jacket protects the copper wire from physical damage. The other media you may be familiar with is the coaxial cable. That's the one that plugs into, so if you have a Comcast cable at home, that's what you have. You have this connector that comes in and it plugs into your modem, cable modem, and it provides you with a cable connection. We'll also talk about fiber optic momentarily. There are some physical wiring standards set by TIA, EIA, and in particular 568 standard. TIA stands for Telecommunications Industry Association and EIA stands for Electronic Industries Alliance. And what we have here is a straight-through Ethernet cable and a crossover Ethernet cable. Now, the straight-through Ethernet cable, especially if you look at the T568B standard, that's the most common standard out there, you see how the transmit and receive pairs are connected as represented here, and then the crossover, they're mapped differently. Now, one thing that I want to tell you here, guys, is it used to be a big deal that you would absolutely want to know the difference between straight through and a crossover cable, otherwise your devices won't work. But that is no longer the case. A lot of the new devices are auto sensing. They have what's called auto MDIX feature, and it's capable of automatically reversing the wiring functionality on the fly on the switch port itself without having to swap the cables. Now, a couple of things I want to draw your attention to. So this right here is your Ethernet cable connector. This is called an RJ45 connector. This is the one that you physically plug in to your computer or any other type of device that has an Ethernet port. Now, what's an Ethernet port? Ethernet port is this right here, for example, is considered an Ethernet port. This right here is considered an Ethernet port. This right here is considered an Ethernet port. So if you have like a 24-port switch, that means you have 24 Ethernet ports on it, and you have the ability to be able to connect these RJ45 connectors into these ports. And another element you need to consider at this layer is the Ethernet NIC, or network interface card. Once again, this looks familiar, right? It's the RJ45 port. So you plug this right in here as well. Now, Ethernet NICs are commonly found in desktops, laptops, servers, and other type of devices. As a matter of fact, even these ports on the switches, behind the scenes, you actually have an Ethernet network interface card. And they're mapped a little bit differently. There's also an ASIC mapping, application-specific integrated circuit. We'll talk more about that in future videos, but this is how these ports on these switches are architected and mapped. Okay, straight through cable and crossover cable. Now, for exam purposes, you need to know from a real-world perspective, like I said, it doesn't really matter anymore because the auto MDIX feature on Cisco devices have the ability to automatically detect the cable type and fix the pins. But for exam purposes, what you need to keep in mind is straight through cable. So if you're trying to connect two dissimilar devices, that's the key word here. Straight through, dissimilar. So a switch connected to a computer, switch to a router, switch to a firewall. Two different devices, you use straight through. If it's the same type of device, like hub to hub, switch to switch, router to router, computer to computer, or computer to router, you use the crossover cable. Now let's shift our attention to fiber optics. Optical fiber is a cable made up of glass or plastic and is responsible for carrying light as signals. Primarily, it's made up of glass more than plastic. Each fiber can carry many independent channels, each using a different wavelength of light, which is also called wavelength division multiplexing, or WDM. There are two main types of fiber optic cables: multi-mode fiber and single-mode fiber. Big difference between the two, instead of going through all the little details here, is that when the light is shined through the multi-mode fiber optic cable, it can take many paths because it bounces back and forth. And I'll show you visually in a moment what I mean. Whereas single mode, when the light is shined through a laser, it shoots straight. Let me show you what I mean. So if you look at this particular diagram here, we got the multi-mode up top. So as you can see, we have light shining through the core of the fiber. And you can see it's bouncing around the walls of the fiber and kind of taking different paths. Eventually it gets to its destination, but it's kind of bouncing around back and forth. Whereas with single mode, as you can see, the laser shines through and it's just a straight shot all the way through the core of the fiber. Another important topic, guys, is the optical components. So the data is sent in the form of electrical signals. But what ends up happening is when you have fiber optic cables plugged in, the transmitter converts the electronic signals into the equivalent light pulses. And the most common type of fiber connectors that you're going to see out there are the SC connector, primarily for multi-mode fiber, and the ST connector, primarily used for the single-mode fiber. Another topic I want to talk about, which is beyond the scope of the CCNA exam, but from a real-world perspective, important, and I think you should be aware of that, is the WDM. Wavelength division multiplexing is a technology which multiplexes multiple OC signals or optical carrier signals on a single optical fiber by using different colors or lambdas or wavelengths of laser to carry different signals. It's further divided into two different patterns. We have the CWDM or conventional or coarse WDM. It provides up to 16 channels and the max throughput is 10 gig. And then we have the higher quality dense wave division multiplexing or DWDM. It provides up to 50 channels at 100 gigahertz spacing or 80 channels at 50 gigahertz. Max throughput, 80 wavelengths of OC48, a total of 200 gig per second, or 40 wavelengths of OC192, which is a total of 400 gigabits per second. Now that being said, guys, there are new standards that are actually taking things to the next level. DWDM is a very exciting realm. There's a lot happening there, and we're seeing constant new development happening on a global scale because we're in dire need of more and more capacity to connect the entire globe. So I expect to see a lot more innovation happening in this space over time. Now let's look at a couple of different physical topologies. We have a bus topology. So what's a bus topology? It's a single backbone cable terminated on both ends, as being shown here. All hosts connect directly to this backbone, as you can see. In a ring topology, we have every single host connected to the other host. And when we complete the cycle where the first host connects with the last host, it becomes a ring. And finally, we have the star topology where we have all the cables connecting to a central point. Now, this is the most popular type of topology in today's networks. All right, so if you think about your home or whatever, so you got this Wi-Fi access point at home that has all these Wi-Fi devices, laptops, tablets, smartphones connecting into it, and also physical cables plugged into it. For example, if you have your PlayStation or Xbox physically plugged in, or your Apple TV or Roku or whatever have you, all together, I mean, everything connects to a central point in your network, and that represents a star topology. Now, local area network or LAN, it's limited geographic area. It's typically within a building or within a house. It's high bandwidth media because, if you think about things that you're doing at your home, you require a lot of bandwidth. It's under one administration, and it's always on connectivity. The LAN technologies are Ethernet, Token Ring, and FDDI. FDDI stands for Fiber Distributed Data Interface. It's obsolete because it maxed at 100 meg for fiber optic, and so it's obsolete. Token Ring was an IBM standard, came out in 1984. It's also obsolete, even though at the time it was considered revolutionary because it avoided collisions. But Ethernet became the dominant standard because at the time when Token Ring and Ethernet were competing, Ethernet was much cheaper to implement. So the cost helped Ethernet win over, and Token Ring just went by the wayside. And from LAN devices perspective, you got yourself routers, switches, wireless access points, bridges, hubs, and repeaters. Now, hubs are mostly obsolete. So are repeaters on the LAN, but you might see repeaters within the service provider network for extending their fiber optic, for example. But that's a whole different animal, completely outside the scope of this exam, but just wanted to throw it out there. Now, a couple of things that I grabbed from the book because I think they were pretty cool. I'm referring to the Cisco Official Cert Guide Volume 1 is the IEEE Physical Layer Standard. So what we got is the 10 base T, which is 10 meg, is called Ethernet. When we go up to 100 meg, that's called Fast Ethernet. But when we go to a gigabit, that's 1000 meg or 1 gig, it's called a gigabit. And then we got the 10 gig, 40 gig, and 100 gig. But one thing I want you guys to keep in mind is 10 meg is over copper, unshielded twisted pair. So is 100. Now at 1 gig, you may get a fiber, or you still have the ability to do copper. Even at 10 gig, you have the ability, of course, to do fiber, but you also have the ability to do copper. But beyond 10 gig, you can no longer use copper. At least not today. If that changes in a couple of years from now, maybe, but not today. And you have to use fiber at 40 gig and beyond. And same thing with 100 gig. Now let's look at the media and segment lengths per IEEE. IEEE stands for Institute of Electrical and Electronics Engineers. They have developed all the Ethernet standards, including the wired and wireless standards that you see out there. So a couple of things to keep in mind. The length. So that's another thing to think about, guys. The copper is limited to 100 meters or 328 feet. You cannot go beyond that. That's just a physical limitation of copper. 100 meters or 328 feet. That's just pure physics, and nobody can beat physics, right? So that's it. But with fiber optic, though, we have the ability to go up to 550 meters, which is 1,800 feet, which could potentially mean we can span across multiple buildings within the same campus, for example. Or we even have the ability to go up to 5 kilometers, which is 3.1 miles. Now let's continue digging into this. From 802.3 10 gig standards perspective, purely looking at fiber optic, we got the 10G base S standard, which is multi-mode, 400 meters. We got the 10G base LX4 standard, once again multi-mode, 300 meters. We had the 10G base LR, long range, that's single mode, and that goes up to 10 kilometers. And then we got the 10G base E, which is also single mode, goes up to 30 kilometers. And we're talking about without repeaters, just a single piece of wire going from one building to another building without any repeaters in the middle. We don't have to amplify the signals. And finally, a comparison between UTP, multi-mode, and single-mode fiber. So, relative cost of cabling, UTP is low, it's the cheapest. Multi-mode is medium. Single-mode is kind of medium, but the difference from a real-world perspective, cost-wise, is fiber optics is about 3 to 5x more expensive than multi-mode. So something to keep in mind. Once again, cost of switch port, low, medium, high. Max distance, 100 meters. Can't go beyond that on copper. Multi-mode, 500. Single mode can go up to 40 kilometers without using repeaters. Susceptibility to interference, electromagnetic interference, some. When you have the copper, none on fiber optic at all. And the risk of somebody comping from cable emissions. So believe it or not, there are devices, let's say if you have a Russian spy trying to steal data from your network, they could potentially use a device that is capable of copying data off of the cable emission. And UTP can do that, whereas multi-mode, none. You cannot do that at all. If you want to steal data off of fiber optic, you have to physically patch into the path of fiber optic, which is a pretty major breach, and you're going to somehow get found out. So when we talk about cybersecurity, guys, security starts with physical layer. Always keep that in mind. You know, security is a fancy topic and gets into a lot of interesting stuff, but security always begins and starts at layer 1. Remember that. Next thing you want to look at is the wide area network. So that's the large geographical area, low bandwidth media. Typically you have serial interfaces here. The connectivity here, we have private lines or leased lines, whatever you want to call them, especially if they're like private circuits. But you can also have public circuits like internet, which are always on. We have technologies like SONET or synchronous optical network. We have T1, E1. We have DSL. We have ISDN. At some point, it's going to become obsolete over the next few years, but some parts of the world, you still have ISDN. Once again, CWDM and DWDM we talked about. And WAN devices, you have routers, ATM frame relay switches. These technologies kind of exist, but they're slowly being deprecated. And then you have modems. A couple of other important elements I want to talk about. What's a bandwidth? And somebody asks you, do you know, can you tell me what the definition of a bandwidth is? Well, what you need to tell them is it's a theoretical measure of how much data could be transferred from source to destination in a given time frame. It's a theoretical measure, okay? It's measured in bits per second, megabits per second, gigabits per second. It's finite. And the cost, the financial cost, is related to the amount of bandwidth. Well, now that we have talked about bandwidth, I think it's very timely to talk about throughput. What's the difference? Well, throughput is the amount of data moved successfully from source to destination within a specific time frame. So the difference is the other one was theoretical, and this is the actual. That's the difference. And factors that typically affect throughput include number of devices, number of users, the type of data, the network topology, whether it's point-to-point or hub-and-spoke, full mesh, whatever have you, physical media, whether it's Ethernet, Cat5e or multi-mode fiber or single-mode fiber. All these things collectively determine the throughput. WAN bandwidth physical layer standards, you got the DSL, which gives you anywhere from 128 kilobits per second to 8 megabits per second. ISDN was 128 kbps. Frame relay, like I said, being deprecated, gives you up to 44 meg. T1, E1, 1.5 meg to 2 meg. Once again, T standard is the US standard, and E is primarily used in EMEA, which is Europe, Middle East, and Africa. And then E3, T3, the optical carrier, which is OC, and the STS, synchronous transport signal. Goes from 51 meg up to 40 gig. And now we have 100 gig and 200 gig standards available as well. Welcome to CCNA 200-301 course. Today, we're going to look at Section 1, Part 2. We're still dealing with network fundamentals, but what's different is that we're now looking at network architectures and basics of Cisco CLI. Here are the topics I plan on covering today. First, we'll look at network architectures and two particular type of network architectures in particular, LAN architecture and WAN architecture. And finally, we'll look at basics of Cisco CLI. Let's jump right in. From a LAN architecture perspective, we have the infamous three-tier campus network design. And what we have in this architecture is we got these access layer switches that have the PCs plugged in, laptops. We could have servers plugged in here, different devices. We could also have a voice over IP phone plugged in to the switch directly. So these are the end devices here at the access layer that needs to be connected to the network. Taking a step back here, a switch is a very important device when it comes to building a network. That's one of the most fundamental components you need to start building a network. And access layer provides access to the different endpoints, like I said, right? So we got endpoints that are connected to the access layer switches. What ends up happening next is that we have distribution layer switches. And in distribution layer, these are basically aggregation switches that are taking a bunch of connections from the access layer switches and combining them into a distribution layer, also called aggregation layer. And here, the idea is that we got all these different connections coming from the endpoints. It becomes a point of consolidation. it handles all the different links that are coming from the access layer switches. And in particular, we call these links that are going up and getting plugged into the distribution layer switches from the access layer, uplinks. They're very conveniently named uplinks. All the links that are facing the clients and the endpoints, these are called downlinks. Okay, so this is an important terminology to understand. When somebody says, where's the problem, downlink or an uplink? Immediately you should get this picture in your head as you're troubleshooting, a picture where you understand that the downlink means the ports that are facing the endpoints, and the uplinks mean interfaces that are facing the switches upstream. And finally, we have a core layer, and the whole reason we have a core layer in our network is to consolidate a bunch of distribution layer switches. So this comes into play. This type of model, a 3-tier campus model, is suited for large enterprises. You're looking at Fortune 500 companies, possibly up to Fortune 5000, but these are gigantic, large corporations with a ton of locations. And what you end up doing is you take a bunch of different buildings and you consolidate them together and interconnect them together. And core layer is what connects those different buildings together. So for example, in building 1, you'll have distribution layer switches in building 1. And then you have building 2, that has its own distribution layer. Then you have building 3, that has its own distribution layer switches. Building 4, same thing, and so on and so forth. Well, how do you connect all of these distribution layer switches together? One way would be to actually interconnect them all in a full mesh, and full mesh gets really, really ugly really quickly. You wouldn't want to do that. Instead, what you do is you have these distribution layer switches, and we end up using one of the buildings as the primary building. So let's say building 1 might become the core of our network. And this is where we would install core switches, and all of the distribution switches from different buildings would physically run their cables and get plugged into the core into building 1. And that's why we need this 3-tier hierarchical architecture. And another reason we need hierarchy is because it's easier to troubleshoot, it's easier to design our network, plus it's easier to make purchasing decisions. When you're looking at buying access layer switches versus distribution layer switches or core layer switches, each layer serves a different purpose. So it makes your choice as an end user a lot easier to decide how to plug different switches into each layer. So it makes it like a Lego block type approach where you just fit the different blocks into the different layers for its own purpose. Next, let's look at the 2-tier network design. In this model, what we have is we got these endpoints at the bottom, our phones, PCs, laptops, IP phones, and all that. They're all connected here at the bottom directly into the access layer switches. And then we got we call this a collapsed core. Or we can call it a core/distribution layer. So here, we don't necessarily need a separate core layer. And where this comes into play is if it's a small to medium-sized business where you don't have a lot of locations. Let's say you started a brand new business and you got building 1, and a few months later, you got building 2. Your network is not that large. You can get away with just having a bunch of distribution layer switches interconnected together in both buildings. It isn't until you start adding more buildings and your network grows to a certain point that you would actually even consider looking at adding core switches. And next, I would like for you to look at the modular campus network design. This is taking the access and distribution and core. So here the picture is flipped. So we got the access switches all the way up at the top. This is where the endpoints are plugged in, right? Then we got a bunch of these links coming from the access switches into the distribution for aggregation, right? So that's our aggregation point. And from there, we further consolidate and interconnect into the core. And the whole idea is core is where you would have your wide area connection, for example, at the bottom, as you can see, or you can have your data center connected or internet. And you might say, well, whoa, what is this? Well, up at the top, you got our standard campus design, right? Access, distribution, core. At the bottom, we got access, distribution, and core for interconnecting different services. For example, these endpoints that you have plugged in. So if I'm a user up at the top, let's say if I'm Bob, and I've got a desktop that's plugged into one of these switches, well, what does Bob need to do his job? Well, Bob would need to connect to either a wide area network to access some applications, or perhaps maybe some server that's sitting in a data center plugged into, let's say, one of these switches at the bottom here. Or Bob may need to access the internet, maybe Google something or whatever, right? Or maybe watch cat videos on YouTube if Bob has nothing better to do, right? It's all possible because of this architecture. So Bob would interconnect to the access would interconnect him to the distribution will connect him to the core. Core is where the internet is plugged in through its own access, distribution, and core. And then finally, it will allow access to Bob. And this is how the traffic flow may look like. Traffic flow might take a different path, but for simplicity reasons, let's say this is the path that traffic took to allow Bob access to the internet. So this is what's called a modular campus design. We have these modules that we use to allow access to our end users, because ultimately the network exists for what reason? The entire reason for setting up a network is to allow users access to different applications so they can do their job efficiently and effectively. That's why we build networks. And as network engineers, we're concerned with how all the different network devices interconnect with each other and allow the traffic to flow through. And that's our job. Now, next, I would like to give you a quick review of the Cisco campus switching hardware portfolio. But before I take you to Cisco's website, a couple of things I want to bring to your attention. There are three main types of switches. You got the fixed configuration switches, you got the modular configuration switches, and then you got the stackable configuration switches. And I'm going to go through each type on Cisco's website. A couple of things to consider before you make a purchasing decision. You need to think about how many ports you need. You also need to think about, are you buying switches for your access layer or distribution layer or core layer? Or are you buying switches for the entire network? If it's a brand new location and a brand new site, maybe you need switches for all three layers. Or maybe you're a brand new business and all you need to do is just have 2 layers instead of 3-tier architecture. You could do that too. But these are the things you have to consider. You have to think about the port density. How many ports? Do you need a 24-port switch or a 48-port switch? What do you need? Switch throughput. What kind of throughput? Do you want a line rate throughput? Line rate throughput would mean that if you have a 24-port switch and each port happens to be 1 gig, that's 1 gig times 24, that's 24 gig. So that means that you need a switch that has the ability to operate at a full 24 gig. There is no contention ratio, meaning there is no bottleneck. Each port is able to access at a line rate. Typically, that's not the case. In campus environment, you don't need switches because those end up becoming really expensive switches. When you want to get wire speed switches, they end up becoming very expensive. Typically in a data center environment is where you would want switches that have no contention ratio. In campus environments, you're going to have 8-to-1 type ratio is very common, 4-to-1, 16-to-1 type of ratio. You're going to see stuff like that. The next thing you need to consider is PoE, or Power over Ethernet. And this is important because it just depends how many voice over IP phones you have in your environment. So if you're going to have a lot of voice phones or SIP phones, you're going to need PoE, Power over Ethernet. Meaning those switches get their power from the Ethernet cable. You don't have to plug them in separately into using an external power supply. Instead, the Ethernet port that's plugged into the phone powers it up versus non-PoE. So we also call that data port. So data port versus voice port. You need to define how many ports you need. Plus, you need to decide whether you need a copper switch or fiber switch. Once again, in a campus environment, copper switch is very common. You may need a couple of fiber switches to connect the different floors together, for example. You also need to consider power. Do you need redundant power? Do you need a switch that has multiple power supplies in it? And finally, scalability. Does your switch allow you to grow as your environment grows, or are you stuck with that switch? Meaning, if you get a fixed configuration switch, as I alluded to earlier, and if it's only 24 ports and you got 24 users on that floor, you're done. The minute you hire a 25th person, now you need a new switch to be installed on that floor. So something to think about. And that's what I mean by scalability. Now, without further ado, let me take you to Cisco's website so we can do a deep dive. So what we'll do is we'll go to cisco.com. So we go to Products, Networking, Switches. Once we come to this page, what we want to do next is we want to scroll down and you want to get to a point where it says View All Cisco Switches. Click on that link. And you will be absolutely blown away when you look at this, especially if you're brand new to networking and you haven't really worked with switches before. And let me explain what I mean. So look at how many different categories of switches you got. Blade switches, campus LAN, data center, industrial, Ethernet, InfiniBand, LAN network management, blah, blah, blah. I don't want you to get overwhelmed. The only type of switches you want to pay attention to are these switches right here, campus LAN access. You want to look at campus LAN core and distribution, and that's it. These are the only two type of switches I want you to be concerned with. Later on in the course, you can also look at data center switches, but right now I don't want you to get overwhelmed. Let's focus in on campus LAN switches and the core and distribution switches. That said, now let's go ahead and click on the access switches. Now here are the different categories of access switches. What I want you to pay attention to is Cisco released their Catalyst 9K or the 9000 series a couple of years ago, and this is the series that Cisco has been pushing the most lately. So if you're in the market looking to purchase switches, this is the series you need to be focused on. You need to be looking at Catalyst 9200, 9300, and 9400 switches for your campus access. And these 9400 switches could also be potentially used as your distribution/core collapsed as well. And I'll tell you more about it in a moment. And if we were to look at the campus LAN core switches right here, you'll see we got the Catalyst 9600. It's a fairly new series. It was launched a couple of months ago. Catalyst 9500. Don't worry about the 6800. Cisco is eventually going to sunset the 6800 platform. 6500s have been around forever, so forget about that. And some of these other switches are kind of going away as well. You primarily need to focus on the Cisco Catalyst 9K line, or the 9000 series. That's what you need to be focused on. Now, let me take you to the 9200 series. As you can see here, these are fixed switches. And let's look at the different models that they offer. What I would suggest is every time you look at a switch, the best way to learn more about it is you look at their data sheet. And Cisco does an amazing job with their data sheets. I really like their data sheets. They do a really good job. So it will tell you how many ports maximum, what type of capabilities, whether or not you have redundant power supplies or not, redundant fans, whether or not you have different additional capabilities, layer 3 and whatnot, and what type of throughput overall, whether or not these switches are stackable or not. As I mentioned, we have 3 different types of switches. We got the fixed switches, we got the modular switches, and we got the stackable switches. Now, these 9200 series switches, they fit 2 categories. They fit the fixed switches category, and they also fit the category of stackable switches. And let me show you here. You can see if you continue scrolling down, you can see how many ports, how many downlinks. Like I said, and uplink, and you got the modular uplink models, meaning you have the ability to install uplink modules yourself, and you can pick different types of configuration, or you can purchase switches that have fixed uplink modules in them. And these are the network modules I'm referring to, the ones that have the ability for you to install. You pick one of these. Like for example, 4 by 1 gig, you can do 4 by 10 gig. 4 by 10 gig means 4 interfaces of 10 gig each. 4 by 1 means 4 interfaces of 1 gig each, so on and so forth. And these switches have redundant power supplies in them. As you can see, each power supply has a single power cord connection coming out of it. So you need to make sure that you have redundant PDUs or power distribution units that these switches are going to get plugged into. And the modularity means that you have the ability to be able to slide different modules out and slide them back in. Also, these switches have the ability to be stacked. So that means maximum number of switches that you can stack together are 8. And let me show you a picture of a stacking configuration. So here's a picture. So basically, this is the back side of these Catalyst 9200 switches. And what we're looking at are these stacking cables, and see how they're connected together. And what that means is, in this picture, we're seeing 4 switches being stacked together via these stacking cables. Even though physically they're 4 separate switches, but when you use stacking cables, what it does is it makes them appear as a single switch instead of 4 different switches. So one of these is going to become primary when you stack them up like that. Let's say the first one here becomes a primary switch. When you log into it via CLI, and we'll talk more about CLI in a moment, command line interface, what ends up happening is you see if each of these has 24 ports, 24 times 4 is 96 ports, right? So what you're going to see in CLI is, like literally, you're going to see as if you have a single switch with 96 ports on it, instead of 4 different switches with 24 ports each. So it's really unique, it's really interesting, makes a lot easier for you to configure. Also, the control plane combines. It makes the configuration a lot easier. You can take advantage of redundant links operating in active fashion, things of that nature. So that was the overview of 9200 series. Now let's go ahead and take a look at the 9300 series. It's very similar to the 9200 series, and let's go ahead and take a look at the datasheet of the Catalyst 9300. These are the next class of switches. 9200s are the most basic bare bone switches you can get, whereas 9300 have a lot more horsepower and much better overall throughput. They're also stackable switches, by the way, and very similar configuration, 24 port, 48 port. You got data only switches, you got PoE plus switches, or UPoE, universal power over Ethernet. These suck up more power, so you'll see, stronger, bigger, better power supplies on these compared to the ones that are just PoE plus, for example. We'll talk more about PoE later in the course. And once again, you got the modular uplink capability, and then you got the fixed uplink capability, and you got all these different modules you can get. Power supplies, once again, you have redundant power supplies, you got redundant fans, so you have a lot of redundancy there. In case if one of the power supplies failed, the other power supply has the ability to completely take over and become the primary power supply. So you continue to run operations even if you had your switch had experienced a single power supply failure. That's pretty much it for the 9300. And now let's quickly take a look at the 9400, because this is a very interesting series, because this is a cross between distribution / core. So let's quickly look at the datasheet here. And these are modular switches, by the way. And modular switches are chassis based, and you'll see what I'm talking about when the picture shows up. But these switches, as you can see, they take up a lot more rack units. Instead of, like a 1U or 2U, these are much larger in size. By the way, there's a couple of other things you want to think about when it comes to modular switches, and that has to do with the fact that modular switches require line cards. And line cards are essentially the interfaces that you need, right? So an example of a line card would be, here's an example of a line card. You got this line card that is all RJ45, and you have the ability to plug in copper ports. So this is a copper line card. This right here is a fiber line card. You can plug in fiber connections in here. And this is how it would look like once you plug in all of your line cards and SOUP modules. Now, another thing I want you to understand and keep in mind is that on these modular switches, you need line cards that provide interfaces, and you need supervisor engine modules. And these SOUP modules, they're also called SOUP modules. These SOUP modules are the ones that are the brains of the entire switch. Without it, switch is just a shell. You need the supervisor module that has the CPU, memory, and all that. It is the brains of the entire solution, and it operates and it runs the switch. The reason you have two is for high availability and redundancy. Only one is active at a time. When the primary fails, the secondary supervisor engine takes over. Now, coming back to the slots, the 9404 chassis, even though it has 4 slots, you can only put 2 line cards in it because there are 2 dedicated slots for the supervisor engine. Same thing for 9407. Here you have 7 slots available, but you can only use 5 for the line cards and 2 for SOUP module. And then the 9410, once again, you have 2 slots that are dedicated to the SOUP module, and you can insert 8 line cards in this particular chassis. And a lot of it's becoming customers' new favorite switch. A lot of the customers I know are replacing their old Catalyst 6500s with these 9400 series switches, depending on how many modules they need. And you also got this 9600 series that was just recently announced a couple of months ago. Here's the CAT 9600 switch. Currently, it's only available in one configuration option, and that's 9606. That's the only option that's available today. Most likely, Cisco will add additional options, but right now that's all you got. But it's a very, very powerful switch. In the Catalyst 9K family, this happens to have the highest capabilities. Like if you look at up to 9.6 terabit per second in a wired switching capacity with 3 billion packets per second. I mean, this switch is a monster, right? Up to 48 non-blocking 100 gig Ethernet, QSFP 28 ports. Like I said, this thing is an absolute monster for being a campus class switch. It's almost a data center class switch, in my opinion, in terms of the capabilities it offers, but it does have a lot of campus type capabilities, and that's why it's positioned as a campus core switch. And it's all about wire speed. Packets come in, packets go out, and that's the whole purpose of the core. Now let's shift our attention to the wide area network architecture. Now that we have talked about switches, now let's talk about wide area network and routers. But before we talk about routers, let's take a step back and look at the wide area network technology from a high level perspective first. So what we have is the overall wide area network is divided into 2 different categories. You got the private WAN and you got the public WAN. The private WAN, you got 2 subcategories, dedicated and switched. Under dedicated, you got leased lines, T1, E1, T3, E3. They're still around, but they're slowly being deprecated over time because it was sort of an expensive architecture to maintain for the telcos and the different service providers on a global scale. And trust me, I know this because I used to design leased lines and frame relay and MPLS networks, so I'm very familiar with that. And then the other category is switched network. Within the switched network category, you got 2 subcategories, circuit switched and packet switched. Under circuit switched, you got the PSTN and ISDN. PSTN and ISDN is almost dead, but it's still there. PSTN is also slowly going away, but you still got your PRIs and things like that, which are part of the PSTN for voice capability. And then you got the packet switched, where the Metro Ethernet comes in, MPLS, frame relay, ATM. This right here is the most popular type of private WAN type of connectivity that's preferred by enterprises on a global scale today. And then you got the public WAN, which is basically the internet. And you got the broadband and VPN capabilities here. You got things like DSL, cable, wireless, like LTE, 4G, 5G, and all that jazz. It's all up here. Now, before we dig deeper, I want to take a moment to discuss with you and articulate the difference between circuit switched versus packet switched, because I think it's a very critical difference for you to understand. So let's go ahead and do that right now. So here's a picture of a circuit switched network. So if you think about an old school analog phone, right, the one that had a dial tone, right? When you lift up a handset on your old school analog phone, you would get a dial tone. That dial tone is provided by this particular switch in the central office. In the service provider central office, to be more specific. And if you were to dial digits, and if you were to successfully dial digits for the called party, the phone would actually start ringing on the other side, right? And before they would lift up the handset, you would actually have a dedicated channel all the way through the network. It's 100% dedicated. Nobody else can use this. It's completely dedicated to you when you make that call. And the minute the other person picks up the phone, that's it. This circuit is now busy. And that's why, if you guys recall, for those of us that have actually used analog phones, I'm pretty much giving away my age at this point. You know, with analog, what would happen is you would get a busy tone if you were to call someone who wasn't available, or if you didn't have enough bandwidth available within the core of your service provider. If any of these central office switches was busy or didn't have enough circuits left over, you would get a busy tone or a busy signal, right? So this is a circuit switch network where we have an entire path carved out. Now, the benefits of this is the fact that we have dedicated and reliable bandwidth because it's completely carved out. And we won't experience any degradation or anything because we have a dedicated channel. On the flip side, the downside of this is the fact that you have limited capabilities within the core of the service provider, right? You can only create so many circuits before you run out of capacity. And that was a huge problem for service providers. So to solve this problem, they came up with the other architecture that we're going to talk about in a moment. And that architecture is the packet switched network. In a packet switched network, it's the opposite of the circuit switched. Here, we don't nail up. So I have a server here, and I have a server here. This could be a client. Let's say this is Bob sitting on his desktop computer. He wants to talk to this server right here. Well, when Bob wants to connect with the server, his packets can take any path in this network. This could be one of the potential paths. The other path could be going from here to there to here to here. There are different paths this network could take for Bob to be able to connect. And then we have queues, right? And the queues are used for when the packets have to wait inside of the router or a switch for it to be processed. Traffic has to sit in a buffer, and the router then decides how that traffic should be treated. It's called QoS. I'm kind of getting ahead of myself. QoS is one of the topics that we'll discuss further down the road in this course. But just do understand that QoS and all that comes into play when you have a packet switch network. But here, the big benefit is we have a lot of different paths. We have a ton of capacity. And the more capacity we add, the more ability we have to be able to connect Bob to the server that it wants to connect to. The flip side is that there could be latency at times. So for example, at 9 a.m., Bob might connect to this server with, let's say, 30 milliseconds of latency. But at 3 p.m., when Bob connects to the same server, his latency might jump up to 90 milliseconds. Well, what happened there? What caused that 60 millisecond delta? That's huge. Well, unbeknownst to Bob, there's a lot of stuff happening inside the core here, right? The packets have to take a different path. So it just depends time of day when the Bob is accessing the destination. Inside the core of the service provider, our packets may take a different path. This is where QoS comes in and traffic engineering comes in. And we don't have to worry about that as a regular user, but this is something you have to keep in mind. That's what a packet switch network is. Now let's talk about a couple of different Ethernet technologies, in particular Metro Ethernet. This happens to be the most popular type of technology on the market today, Metro Ethernet, defined by MEF or Metro Ethernet Forum. You can Google MEF and you'll get to learn a whole bunch about MEF and what they offer. In particular, there are three different topologies that Metro Ethernet has. First, we'll discuss today is E-line or Ethernet line service. This right here, as the name suggests, is a point-to-point circuit. We call it Ethernet virtual circuit. So CE is a customer edge router, and PE is a provider edge router. These routers we don't have to worry about because service provider, AT&T, CenturyLink, whoever have you, Comcast, they manage this stuff. We don't worry about it. All we get is a circuit from them. We plug in the Ethernet port into our router and on both ends, and we're in business. They do all the magic in the middle. And here, like I said, in the E-line scenario, we have an Ethernet virtual circuit created by the provider edge in the core. Now with E-line, what we can get the next level up is we could get point to multi-point type of connectivity here, even though it's still point to point, because each circuit is considered unique, right? This is one circuit up at the top, and then at the bottom, we may have another site that we're connected to over a wide area network, and this is another point to point. So in reality, these are a bunch of more than point to multi-point. These are a bunch of point to point circuits, but it's more like a hub and spoke topology, right? If you think about it, because you got a hub on the left here, and you got these spokes to the right, and these spokes talk to the hub through these virtual circuits. This is the E-line. This is the E-line. Now let's talk about Ethernet LAN service. Now this happens to be the most popular because you have what's called a full mesh connectivity here. Full mesh means everyone is connected with each other through these virtual circuits that are created by these provider edge routers, and through the provider core, we have full connectivity. So if this is our environment, if this is San Jose, and this is Los Angeles, and this is New York, and this is Chicago, all of these sites are interconnected, and LA can talk directly to Chicago, LA can talk directly to New York, LA can talk directly to San Jose. You get the idea. That's what full mesh means. Everybody is fully connected with everyone else. That's full mesh. Now, a couple of interesting facts to know about is that with Metro Ethernet, this is where MPLS lives, and we'll talk about MPLS in a moment. And this is where VPLS lives, which is the Virtual Private LAN Service, and MPLS is Multi-Protocol LAN Service. Or Multi-Protocol, VPLS Virtual Private LAN Service, MPLS Multi-Protocol Label Switching. We'll talk about MPLS in a moment, but this is where these two technologies live. MPLS is a layer 3 technology, technically layer 2.5, but it's considered layer 3. VPLS is a layer 2 technology. And the final topology we get with Metro Ethernet is E-tree or Ethernet tree. This is truly point to multi-point. So here you got a hub and you got these virtual circuits that are spinning off of the hub, and you can have additional circuits as well. So this is like a tree where the hub becomes the core of the tree, and these spokes are the branches. Now let's quickly talk about multi-protocol label switching, or MPLS. In MPLS we have, let's talk about the terminology first. CE, that's customer edge. That's as a customer, that's what you have. PE is the provider edge. These are the routers that are in the administration of the provider, service provider. We don't touch them. We don't know about them. They're completely oblivious to us. The only thing we do know about them is when we get an IP address from our provider to use over this point-to-point connection, we have to make sure that we can ping the other side. If we can ping, that means we can get to the PE. That's the only thing we are aware of. And it's a layer 3 handoff. Like I said, it's a layer 3 circuit. And typically you would run some sort of routing protocol on top, but let's not get ahead of ourselves. Now, one thing that I want to bring to your attention is the fact that we have some semblance of transport independence, whether we have a T1, T3, we have a frame relay, or a Metro Ethernet. The handoff doesn't matter. How the circuit is delivered, whether it's a serial circuit or an Ethernet circuit or a TDM circuit, it doesn't really matter to us. MPLS works seamlessly and it's transport independent. So that's another reason why MPLS is so powerful. And MPLS has been around for over 20 years. It's a very, very successful wide area network technology. And what ends up happening is inside the core, here at the edges of the CE, it's all layer 3, like I said. But inside the core, these provider edge and provider core devices use labels. And using the labels at layer 2.5 or 2.5 of the OSI model, we can cut back on the expensive lookup that we have to do at layer 3. At layer 2, it's not that expensive for the router to do the lookup. At layer 3, it has to use a lot more resources to do the lookup. At layer 2.5, it's right in between, and this is where labels come in. These routers use labels to transport packets for different customers inside the MPLS cloud. And this is all seamless to you as the end user. You do not know what's happening in the core. All you know is you have a layer 3 circuit and you're running maybe BGP, for example, as a routing protocol. And that's how you're learning all the routes. But the service provider is using labels. PE is also considered an LER, or label edge router. And it puts the label on and takes the label off, depending on whether it's an inbound packet or an outbound packet. And that's called PHP, or penultimate hop popping, meaning right before the packet is about to leave the MPLS cloud, we pop the label so the router, when the CE gets it, doesn't get confused. And the CE does its layer 3 lookup, something for you to keep in mind. Now, a couple of benefits of MPLS, like I said, it's transport handoff independent, end-to-end QoS. Now, the big thing about MPLS is the fact that you get end-to-end quality of service. So if I were to go back to the diagram here, you got all these routers, PEs and provider core and provider edges. They have QoS configured on them, quality of service. So they treat your voice and video traffic or real-time traffic differently than your bulk traffic, like internet or email. Meaning your bulk traffic could be dropped, but your real-time voice and video cannot be dropped, right? And it also have to have low latency and all that. That's all built in to MPLS. Also, you have a better network topology control. MPLS lets you do point-to-point, hub and spoke, partial mesh, full mesh. You are fully in control, but the only drawback is you have to work with your service provider to make that happen. You cannot create your own topology. Your service provider has to create the topology for you on their provider edge router. So it's very, very important that you talk to your service provider about that ahead of time. And you have a reliable service with service level agreement, meaning the service provider who sells you an MPLS circuit, it's their job to make sure they meet their service level agreement. Service level agreement contains things like certain amount of latency that they promise that their network will not exceed, certain amount of packet loss and jitter and all that is all defined on paper. So when you sign the agreement, you're locked in, and if they violate any of the terms of the agreement, they actually pay you a financial penalty. For example, if your site goes down for longer than it's supposed to, then they will pay you, they may give you service for free for that month. So it's really cool from that perspective, and that's MPLS for you. Now let's quickly take a look at the SOHO, or the small office, home office, DSL architecture. That could be you sitting at home and you got a router and you have a DSL modem. Let's say if you're using a DSL service, it connects into what's called a DSLAM, or DSL aggregation multiplexer. It's a big router that has all these different modems coming into it from different households. And then it has a big uplink connected into the core through the internet, through the WAN service provider, and it connects you to your headquarters. So here at the headquarters, you might have something like a T3, or you might have a 100 meg Ethernet circuit, or maybe a 1 gig Ethernet circuit or something like that. And then at your home, you got the DSL, or it could be a branch location, doesn't have to be a home. But SOHO is small office, home office, right? So it's very, very lightweight. You have one user, maybe two users that need access to the corporate environment to access certain resources. And this is how the architecture looks like. Now let's look at another SOHO model. This is the cable. Instead of DSL, we have a cable modem. For most of us, that's true. Like, for example, here for me, I've got a Comcast cable connection coming in. I've got a 1 gig Comcast cable connection. So I've got a cable modem from Comcast. Then I've got my own router that's plugged in. And then that's me sitting here, right? So if I need to access resources of my company, I go over VPN, or virtual private network. We'll talk more about that later in the course. I establish a VPN connection into my corporate network, and I have access to it. Now, the big difference here is, instead of the DSL access multiplexer, here we have what's called Cable Modem Terminate System, or CMTS. Here's where you have all these different households with physical cable, coaxial cables coming in. And then this has, once again, a network uplink into the core of the service provider network to be able to connect all the way up to your company head office. What we have next in wide area network is wireless WAN. We got things like 3G, 4G, LTE, 5G, right? So here we have our cell phone directly connected to the cell tower, our laptop having a cellular card inside it, or our tablet with a card inside it that has the ability to connect directly. You can also get a router that has an LTE module inside it, which also connects to the cell tower. But here the key is the cell tower that we connect to. And once we're connected to the cell tower, then we gain access to the service provider or the ISP core, and they have internet connected on the back end of it. And then that allows you to access the internet. That's a wireless WAN. That's one of the access mechanisms of connecting to the wide area network. Now, one thing I want to talk to you guys about, and this might be kind of going beyond the course a little bit, but it's near and dear to my heart because I spent over a decade of my life working for global tier 1 service providers. And that's called the service provider POP, or point of presence. And what you have is you got all these customers. So this could be you have router 1 here and you got router 2 at the bottom, or you might have other routers here too, but these are the connections to you as a customer, as subscriber. And these routers then, are connected via circuits into the service provider access routers. And this connection right here is called UNI, or User Network Interface. User Network Interface. And this is how service provider interfaces with their end user. So to the right, we have downlinks from the routers down to the customer, and to the left, we have uplinks into the core of the network from these access routers. And there's another term that comes into play here. It's called NNI, or Network to Network Interface. And that means we have our internal routers within the service provider core connected together. And these backbone routers can also then connect to other wide area network POPs. So what that means is this could be a point of presence physical data center, or a physical point of presence for, let's say, AT&T here in San Jose. And I'm sure they have tons of POPs in San Jose because San Jose is so fiber rich. And then they have another POP in San Jose. They might have another POP down in LA, for example. And then that interconnects with these routers, and that interconnects with these backbone routers as well down in LA and New York and so on and so forth. And this is how the service provider POPs are designed and interconnected to allow you access as the end user to their wide area network. Now let's quickly take a look at the Cisco routing hardware portfolio. Before I show you the routers though, I want you to think about two things. When you think about a Cisco router, you got SD-WAN routers and you got the non-SD-WAN routers. So this is something you have to think about before you make the purchasing decision. SD-WAN is a centralized architecture with a controller, whereas the non-SD-WAN standalone routers, old school, kind of slowly going away. Pretty much everybody's jumping on the SD-WAN bandwagon, but something to keep in mind. And then you got a couple of things to consider before you make the purchasing decision. You have to look at the total router throughput. You have to look at what features, for example, if you need advanced security features on top of routing, you're going to need a beefier router. Interfaces, do you need copper and fiber? How many? What type? Single mode fiber, multi-mode fiber? Power, do you need routers with redundant power supplies if they're critical enough? And then scalability. Do you need routers that have the ability to grow as your business grows? So with that, let me take you straight to Cisco's website so we can do a quick analysis. So we go to cisco.com, click on products, networking, we click on routers. Once we get to routers, what I want you to look at is view all routers right here. You got a ton of options here. The ones that we're concerned with are branch routers primarily, but look at how many different options you have available to you, including service provider and all that. We're not worried about any of those. What we're worried about are the branch routers and the WAN aggregation and internet edge routers. These are the only two type of routers that we're concerned with for the purpose of CCNA. Now let's go ahead and click on branch routers. Within the branch routers, I want to draw your attention to a couple of things. What you want to focus on is the Cisco ISR. The integrated services router is considered ISR 4K series. That's a series you want to pay attention to, and the ISR 1K series you want to pay attention to. This is what Cisco has been pushing a lot lately. The 1900s, 1800s, some of these other ones are probably eventually kind of going away. Plus they're for much smaller size networks. ISR 1K is also for much smaller size networks as well, and a really robust type of device. And then you got the brand new series that just started. It's the Cisco Catalyst 8300 series Edge platform. These are absolutely amazing next-gen routers. Very, very powerful, and they're more geared toward like high-end branches with a lot of throughput requirements. And next, let's look at the WAN aggregation and internet edge routers. In particular, I want you to look at the ASR, or the aggregation services router, ASR 1K right here. And then once again, we got the Catalyst 8500 series showing up here. I think this Catalyst 8500 series is a better fit for data centers than it is for branch because of how big of a monster this series is. Now let's go ahead and take a look at the 4K series. So this is the 4K series. Let's look at the data sheet. You got a ton of different options here. And in particular, right here, we get to see product specifications. So for example, you get to see that Cisco 4221 is where it starts. Then it goes up to 4321 right here. Then 4331, 4351. You can see that right below the box is the throughput that it's capable of. With some additional licensing, you can take their throughput to the next level. But be cautious though, especially if you're going to use them as SD-WAN devices, the throughput might be very limited. And especially if you can also enable security on top, you're going to have to be very, very cautious with the throughput. And then it shows how many LAN interfaces you got and WAN interfaces, 10 gig ports, how many copper ports, how many fiber ports, and so on and so forth. Now let's quickly take a look at the Cisco ASR 1K series, and I'm going to pull up the data sheet here so we can review it together. So here's the entire portfolio. As you can see, they have fixed configuration routers as well, but they have a lot of modular routers. So what you get with the ASR 1K series, if I were to scroll down. So what you can see is, if you look at the ASR 1001X, it has the ability to go from 2.5 gig to up to 20 gig throughput. You got the next one up is 1002X. That goes from 5 gig to 36 gig in throughput. Then you got ASR 1001HX. These are high performance. H is for high performance. Goes up to 60 gig. That's a monster. 1002HX goes up to 100 gig. Then you got the ASR 1004, goes from 10 to 40, so on and so forth. So as you can see, ASR routers are more geared toward data center because these are high throughput boxes designed for aggregating connections from a lot of different branch offices. Because typically at the data center, you're going to have a situation where you got a ton of these branches that are constantly trying to access data that is located in a data center. And you're going to have a lot of traffic hitting your data center network from these branch locations. That's where these routers come in. Now let's shift our attention to the basics of CLI, or command line interface. In order to access a router or a switch, it doesn't matter whether it's a switch or a router, it's the same way to connect. You have two ways of doing it. You can either physically do it or you can do it virtually. What do I mean by that? Let me explain in a moment, but let me explain a couple of other elements along the way first. Cisco runs iOS. Whether it's a Cisco router or a Cisco switch, they run iOS, which stands for Inter-Network Operating System. Once you buy a router or a switch, you got to do something with it, right? Otherwise, out of the box, it's not going to do anything for you. You can connect things up to it, but nothing is going to happen. You have to configure things for it to actually work. This is where CLI comes in. Command line interface. And what we do is we connect to that device and we start configuring it. Well, you might ask, well, how do you do that? How do you connect? Well, I'm glad you asked. There's multiple different ways of doing it. What I want to draw your attention to is a couple of different types of ports. First, the console port. See this console cable right here, as you can see, the RJ45 piece of it interconnects into this console port. This is the RJ45 connector, plugging into the console port. And then the serial connection, we take it and plug it into our laptop. If we had an older laptop, a lot of the newer laptops don't have that. What we can do then is we can get an adapter that converts from serial to USB, plug that in, then install drivers for it, and then it will recognize that we're connected via serial cable. And then our laptop or desktop would be able to connect. There's also the auxiliary port. So with the auxiliary port, we can have a modem plugged into it, like a dial-up modem, which is very, very old school now. If you guys remember back in the day when we had modems, you still have them for out-of-band management, or OOB, meaning if our network were to go down for some reason, we can still access our device remotely. This is for remote access. So that's the auxiliary piece of it. And then either via the fast Ethernet or the serial ports, we have the ability to connect virtually to our device. So here, of the auxiliary and console, we're physically connecting, even though with auxiliary, that's also virtual too. But with console, you're physically, like literally have a physical cable plugged in to our device. Whereas with fast Ethernet and serial port, we're going to configure IP addressing, which is logical addressing. And then I may have a router here in San Jose, California, but I could be halfway across the world, somewhere in Sydney, Australia. And from there, I can connect to my router that is physically sitting in San Jose. Well, how is that possible? It's because I have configured virtual access to it using Telnet or SSH. We'll talk about that in a moment. But when you connect via the console cable, you have to use what's called a terminal software on your machine. So on Apple, on Mac, you literally have an application called Terminal. You open that up and you can start configuring these parameters down here at the bottom. 9600 baud rate, 8 data bits, no parity, 1 stop bit, and no flow control. These are parameters that you have to set up once you're connecting via the console cable through the console port to your router or a switch. And that's it. This is how you connect physically to your router. We'll also talk about virtual configuration, plus I will do some hands-on for you so you get to learn how all that works. Before we actually touch the CLI, I want to bring your attention to a couple of different things. When we look at the command line interface of the router, the first thing we're going to look at is we have a couple of different modes. The first thing we're going to get when we log into a router or a switch is we're going to get this prompt right here, which some people call right arrow or greater than sign. It's up to you, whatever you prefer calling it. But this is what we have. In this mode, we're limited to commands like ping, very limited show commands. We can type in enable. It means we have admin access, etc., etc. But everything is very, very limited here. The next level up is the privilege exec mode. Here, the prompt changes in the CLI. What you'll notice then is that the symbol will change from the greater than sign to the pound sign or hash sign. That indicates to us that we're in privileged exec mode. This is where we can type in all the user commands, debug commands, we can reload the router, configure it, etc., etc. One level deeper is the global configuration mode. Here, the prompt changes to config hash or the pound sign. And here we can do things like host name, enable secret, IP route. A lot of the configuration goes here. We can go a level deeper into the interface configuration mode displayed by config-if and the hash sign in front. And finally, we can have config router mode where we go ahead and configure things like the routing protocol and all that. So this is how hierarchically, as you can see, we have different options. We start at the exec mode, then we get to the privilege exec mode, then global configuration mode, and then we keep going levels deeper and deeper. Now I think at this point, you guys are ready to go ahead and do a quick deep dive into the basics of CLI, and can't wait to get my hands dirty. And you should do the same thing. As I'm typing in the commands on my end, you should do the same on yours, because you can easily find tools like Packet Tracer that is available for free, and that's exactly what I'm using here. So here's a switch and Packet Tracer, very similar to how you would look at an actual switch. And what's being represented here right now by the CLI is as if you're connected through a console connection physically connected to that switch. And what we can do here, this is, if you guys recall, called a user exec mode. Here we have very limited access. We can run commands like show version. This is an interesting command, shows us a couple of things. Here it shows us that this is a Catalyst 2960 platform. It shows us that this is the base Ethernet MAC address of this device right here. It's giving us the exact model number of this box. Once again, same information that we had up here. This is actually the part number of the switch. So you can literally go ahead and buy this switch with this part number if you needed an exact type of switch in your environment. And it also shows us the type of software version that we're running. We're running 12.2, and the software image that we're running, it's a LAN base image. You also have more advanced capabilities as well, but the LAN base image gives you the most basic capabilities you can get at a layer 2 level on this switch. We really can't do much in the user exec mode, so we're better off going to the next mode, which is called the privilege exec mode. So notice the prompt changed from the greater than symbol to a pound symbol or a hash symbol. Here we have administrative access to the box and we can pretty much do anything. But things get more interesting when we get to the next level. So I want to show you a couple of things here. If I say config and I hit tab on my keyboard, it automatically completed the entire command. Even though I had just typed in config, it went all the way to configure. And what we can do next is type in question mark, space question mark. That means is now we can see what the next potential command could be. So here we'll type in terminal. Once we type in config terminal, notice the prompt changes to config #. So now that means we're in a global configuration mode. Here we can change the host name. We can do a couple of different things. Well, now that we are here, might as well start configuring our device, right? So let's go ahead and change the host name. We'll call it switch1. So notice what happened. The minute I typed in hostname S1, the name changed from the generic switch, which was out of the box name, to the name that I gave it. I could give it any other name I want. For example, I can call it hostname. Let's say if I have my own company and it's called Najfar, and it happens to be switch 1 within my corporation, I can call it Najfar S1, for example. So, and it's cool, and this is considered a best practice. What you need to do is you need to identify your site name, your company name, your site name, and then the number of switch that it is. You need to basically create a spreadsheet, and you need to keep track of all the names and make the names as descriptive as possible. So when you're troubleshooting, you're not banging your head against the wall trying to figure out what's going on, where are you connected to the right switch. You don't have to constantly look at the documentation. The name should kind of give it away and demonstrate to you, for example, that you're connected to a switch in San Jose compared to a switch in New York, and you're connected to building 1 in San Jose instead of building 2 in San Jose. So as you can see, you can get pretty creative with the names and all. So that's the first thing we'll do here. Couple of other things we can do is, as you saw earlier, we didn't have to type in any password because this is a brand new configuration, right? What I would suggest is that we go ahead and type in a password. So we do enable. We have two different options, password or secret. Password is unencrypted, clear text, whereas secret is encrypted password. So we're going to go ahead and set up a secret, and we're going to go ahead and type in Cisco. What we do next is we type in line console 0 because we want to set up our password on the console port itself. So we're going to type in login. Then we're going to go ahead and type in password again. And we can say Cisco, we can say login again, exit, exit, exit. Now we are all the way back to the user exec mode. We type in Cisco, we type in enable, we type in Cisco again, and we went from user exec mode to privilege exec mode. We type in configure terminal, and it takes us to the global configuration mode, and this is where we had set up our password. So that's cool. We have learned how to set up a secret password and how to apply it to our console port. That's great. But we are not done yet. I also need to have the ability to be able to remotely connect to this device. What if I'm sitting on a beach in Hawaii and I get a call from someone that, hey, this router or switch is misbehaving, right? So I need the ability to be able to do that. The way we do that is we go ahead and set up the line VTY 0 through 4 on a router and typically 0 through 16 on a switch. And what that means is this is how many virtual terminal ports will be used to allow. This is how many connections will be allowed simultaneously into this device. When I'm connecting to it remotely, that's considered one connection. 0 through 4 means potentially 5 people can connect because 0 itself is a session. And then you can have up to 5 people that can connect to this particular box remotely. And that's a virtual terminal line. Line VTY 0 through 4. Here we can type in password again. And we can say password Cisco. Next, we would want to specify the transport protocol. So that's transport input. Do we want to do SSH or Telnet? Telnet is a non-secure protocol. It's clear text, so it's bad news if I'm in Hawaii and I'm connecting and someone kind of is sniffing traffic off of the switch, or there's a man in the middle. They can see all of my passwords and everything being exchanged between my laptop in Hawaii and the switch over the internet. That's bad news, right? My company can completely get compromised. So what I would want to do is set up SSH. Now to set up SSH, what we would want to have to do is there's a couple of different steps we have to go through. We have already set up a host name. That's step 1. Step 2 is we have to set up a domain name. So I'm going to go ahead and get that done right now. IP domain name. And I'm going to call it najkazi.com. We also need to set up a username and password. So let's just say username Naj, password Cisco. We also want to set up a crypto key, generate RSA, general keys, modulus. Let's see what's the best option we have. Let's use the best modulus we have available. And as you can see, currently the SSH version 1 was enabled. We don't want that. We actually want version 2 enabled. So we'll type in IP SSH version 2. Now this makes sure that we have SSH version 2 enabled, which is the most secure version. And by the way, the modulus, this is the strength of the encryption key. We would want to use the highest supported by our device because hackers are always figuring out ways to compromise devices, and the lower the modulus is, the higher likely it is for hackers to be able to break the encryption on your box and crack the code. So we don't want to give them that ability. And finally, what you would want to do, again, is you want to go back to the line VTY 0 through 4 and type in transport input SSH one last time. And that's pretty much it. Next time, if I'm in Hawaii, I can literally SSH into this box and I'll be connected to it. Now, we did a couple of things on this box today, right? And here's the deal though. Did I save any of it? The answer is I really have not, right? So let's look at where it's currently available. This is what's called show running config. So when I run the show running config command, it shows me all the changes that I've made to this device. So I've set up the host name, Najfar switch 1. I've set up a secret. As you can see, the secret, it's an MD5 hash. It's still breakable. It's not completely unbreakable, but it's better than showing Cisco, right? Then we got the IPSSH version 2 that I had set up, the domain name, username, and the password that I had set up Well, one thing that I'm not happy about is, first of all, I need to change the privilege. I need to make it privilege 15. Privilege 1 will give me very, very limited access to this box. That's not good. Privilege 15 will give me the full admin access to this box, and I'll show you how to do that in a moment. Plus, I can see the password in clear text. Ouch, that's not good. We need to fix that. And the rest you can ignore for now. You'll learn more about it as we continue going through this class. And then we applied it to the line console 0. Once again, the password is showing in clear text under console and also VTY. Ouch. Let's go ahead and fix that. How do we make these passwords be encrypted? Let's go configure terminal and type in service password encryption command. This command right here automatically encrypts. Once again, this is not uncrackable, but it's better than having your passwords in clear text. Let me show you what I mean. By the way, here is another cool trick. You can type in do show running config instead of having to exit and go back to the privilege exec mode to run the show command. The keyword do allows you to be able to run the privilege exec mode command from any subconfiguration mode that you're under. Right now we're under global configuration mode. By just typing in the keyword do in front of my command, I can run the show running config without getting any error messages. Now, let me show you right away. Well, the password that we had in the secret we had previously was MD5 hash to begin with, but let's look at what happened with our username. The password now is all kind of jumbled up. Now let's go down, space. Look at line console 0, password is all jumbled up, and line VTY 04, password is all jumbled up. That's better. But we are still missing one thing, and like I said, the username, nudge, privilege 1 and all that, I need to change it to privilege 15. So let's do username, nudge. Let's do privilege 15, password Cisco. So now if I were to do show running config, you'll see everything will be all jumbled up across the board. You shouldn't be seeing any type of password that's clear text. Once again, like I said, it's not like it's uncrackable, but it's better than nothing. And at least there's one layer of defense. Now, the best thing you can do is, instead of setting up these username and passwords locally, you should actually have an authentication server, like a AAA server, which is now called an ICE server. And on the ICE server, Identity Services Engine server, you go ahead and configure all the usernames and passwords there, and then point your device to that server so it can authenticate. That's the best way to do it. And then you're completely secure because everything is fully encrypted and all that. That's the best practice design. Now let's go back to the deck. I think that pretty much wraps up. That almost wraps up our configuration, but one last step though. If I were to go ahead and reboot the router now, when it comes back up, it's going to bring us back to the brand new prompt, meaning we're going to have no configuration saved. We don't want to do that. So what you want to do instead is you want to save the configuration before we exit the router. So that's the command copy running config to start up config. You hit enter a couple of times and that's it. Now you're safe. And this router reboots now, comes back online. It's going to remember all of its configuration that we just did. And that is really, really cool. So very, very important for you to know that. Now, a couple of additional shortcuts for this command. You can do copy, run, start. It's the same thing. It's a shorthand version of this command right here, very short version of it. And another one that you'll see out there is WR, which is write memory. This also used to be called write mem. You can also do that. These are all same commands accomplishing the same exact function, but for exam purposes, you want to memorize the show running config to startup config, or copy run to start, or copy running config to startup config. that pretty much wraps up the hands-on CLI portion of this. Let's go back now to the presentation so I can show you a couple of additional items. So these are the different, you can take a snapshot of this if you want. User exec mode, privilege exec, global configuration mode, interface configuration, line configuration. At this point, you guys kind of know what this is, but I have this handy dandy slide for you to take a snapshot of and keep it in front of you. You can use it as an exam cheat sheet, for example. Now, how does a router boot up? Well, a couple of things happen, and the same thing is applied to a switch as well, so it's the same exact process. The first thing that happens is that the router initializes by loading the bootstrap, and the bootstrap is located inside of read-only memory or ROM. After the bootstrap, what ends up happening is that the iOS is loaded, the operating system itself, and that's located on the flash. The flash could be a chip that's built into the router, kind of burned into it, or it could be a removable flash card that you install on it. And that has an iOS sitting on it. And then finally, the last step in the process after the operating system has been boot up is to go ahead and load the configuration file, and that's located in the NVRAM, or the non-volatile RAM. That's the third step. So just remember this process. Not sure if it's going to show up in the exam or not, but from a real-world perspective, kind of good to know how all this works. And it's no different than how your laptop works, right? You have a BIOS on your laptop or computer, and that's the POST. POST stands for Power On Self-Test. And what that means is when the device is coming up, it automatically tests itself to make sure that it's got all the right hardware parameters for it to be successfully able to boot up. So that's the first thing, right? That's a bootstrap. And then after that, you got the hard drive where the operating system sits and all of your files sit. This is sort of like the flash as the hard drive. And then the NVRAM is where the configuration file sits. A couple of additional items. As I mentioned, configuration file sits in the NVRAM. This is the startup configuration. Anytime you're making changes to the router, the configuration sits in the RAM, which is the random access memory, right? DRAM, whatever you want to call it. Unless you write the configuration using the copy running config to startup config, the config is not written to the NVRAM. It's stored in the RAM. But the RAM, the minute the device boots up, the RAM content goes away. So this is something you have to keep in mind. So this is how the iOS kind of processes the startup configuration versus the running configuration. These are the SSH steps that I walked you through. It's a 6-step process. I went through it pretty quickly. Here, you can follow these steps if you're doing a lab on your own, for example. I highly recommend that you guys follow me along. Whatever I'm doing on my end, you guys should do the same thing on your end to get the maximum value out of this class. And you can also take a snapshot of this and keep it handy dandy for exam purposes and also for doing labs. Welcome to CCNA 200-301 course. Today, we'll focus on Section 2, Part 1, Local Area Network, Wired and Wireless. In particular, we're going to focus in on LAN switching concepts. Here are the topics I plan on covering today: Ethernet overview, switching fundamentals, and finally, I'll wrap it up with VLANs, VTP, and trunking. So let's first look at Ethernet. So Ethernet is a layer 2 technology that allows us to send frames. It's defined in IEEE 802.3 standard. It was initially designed for LAN-based communications, even though it has been extended to work over wide area network as well as a last mile handoff. And copper happens to be the most common physical media used in providing Ethernet technology. However, fiber optic is also common in the data center and large campuses, and also service providers heavily utilize fiber optic due to the distance limitations of copper. Now let's quickly talk about Ethernet. It's more for revision than anything. If you guys recall, when we looked at the OSI model in section 1, part 1 video, layer 1 has some limitations. I'm not going to go through each and every element, but I'm just going to give you the gist of it. Layer 1 cannot communicate with upper layers. And what is layer 1? That's your electrical signals, that's your photons, that's your radio frequency for wireless connectivity. It's the medium. It does not have any smarts. It's, at the end of the day, it's all about sending bits and bytes at a binary level, zeros and ones. Layer 2 is where we start to add intelligence to our network. This is where things like MAC address come into play, also known as hardware address. We have things like LLC or logical link control, and we'll talk about those details momentarily, but that's why we need layer 2. We need higher layers in the OSI model because higher layers is where the intelligence gets added to the network. Now let's do a quick review of the OSI model. I'm not going to go through each and every element, but let me draw your attention to the second layer of the OSI model called data link. Data link is further subdivided into two different layers. One is called LLC and the other is called MAC. MAC deals with layer 1. Whereas LLC deals with layer 3, which is the layer above. Now let's discuss a very important technology from Ethernet perspective called CSMA CD. Stands for Carrier Sense Multiple Access with Collision Detection. That's a mouthful. What does that mean? Let's take a closer look. So what ends up happening with CSMA CD is that we have a shared media. So we got all these hosts, as you can see here, A, B, C, D, they want to talk to each other. If there's a collision that's detected, the frame has to be retransmitted. What that means from a layer 1 perspective is that when a collision happens, that means electrical signals got jumbled up because multiple hosts were trying to transmit data at the same time. And when that happens, the frame at layer 2 gets corrupted and it has to be retransmitted. And the second thing that CSMA CD handles is the carrier sense piece of it. Listen before you transmit. And that means each host on this shared media wait its turn, or the carrier signal, so to speak. And when it senses that the signal is idle, it goes ahead and sends data or frame. When the carrier is not idle, then the host waits its turn. That's what CSMA CD handles. The ability to be able to retransmit if there's a collision, and the ability for the host to listen before being able to transmit data. Now there are multiple flavors of CSMA CD. What I want to bring your attention to first is the top left portion. And what we have at the top left portion is what's called contention-based access. And this is where technologies like Ethernet and wireless come into play. Stations can transmit at any time, however, collisions exist. And whenever there's a collision, frames have to be retransmitted. CSMA CD is used on Ethernet networks, which are physical wired networks, on wireless networks, which are the 802.11 standards. We have technology called CSMA CA, and CA stands for collision avoidance, meaning we avoid the collisions to begin with instead of having to wait for the collisions to occur. On the bottom right-hand side of the screen, you're seeing controlled access. Technologies like Token Ring and FDDI, or Fiber Distributed Data Interface. Now, these are obsolete technologies, but they had an edge over Ethernet in a sense that only one station could transmit at a time, and the other devices had to wait until that station was done transmitting data. There were 0 collisions, and some deterministic networks use token ring. But like I said, this particular element is pretty much obsolete at this point. All the networks that today that are Ethernet based use either CSMA-CD or CSMA-CA. Here's the algorithm logic of CSMA-CD. First, station is ready to send frame. When it senses that the channel is available, if the channel is free, it goes ahead and transmits data. Now, if there's no collision, transmission is complete. However, a couple of things to keep in mind is when it senses that the channel is busy, it tries again to resend. However, while in the middle of transmission of the frame, if it detects that there is a collision, what it does is it sends a jam signal, which triggers a back-off timer. And this back-off timer is sent to all the stations that are on that shared media. So let's say if you have 10 hosts, part of the same shared media, all 10 hosts will get that back-off timer, and it's random. So that ensures that once a collision occurs, that no 2 hosts on the same network will be able to transmit data at the same time because it's a randomly generated back-off timer. That's how the algorithm works. On any particular LAN, there are 3 communication mechanisms. First, we have what's called simplex communication. That's a one-way communication mechanism where only one device can talk at a time. We also have something called half duplex. This is a 2-way communication mechanism. However, only one device can send or receive at a given time. You can think of it like, if you guys remember walkie-talkies, right? Only one person can talk. When they're done, then the other person is able to speak. That's a half duplex communication. In full duplex, what we have is it's also a 2-way communication, but you can think of it as a cell phone where both devices can send and receive at any given point in time. Now let's talk about a MAC address. What's a MAC address? It stands for Media Access Control. It's a 6-byte long address physically assigned to network interface cards or a NIC card. In layman's terms, what that means is any device that has a network interface card has a hardware address associated with it. It's also known as a burned-in address or BIA. It's usually written in one of the following 2 formats. You have either with colons in between each octet, or you have these dashes between each octet. Like I said, it's a 6-byte long string of MAC address, and it can be further subdivided into 2 halves. The first half of the MAC address is considered a manufacturer ID, and the second half of the address is considered a serial number. To give you an example, here is a MAC address on my Apple MacBook Pro. This is the hardware address right here that's assigned to my computer. Now, once again, the first part right here, this is the manufacturer ID, so that would be Apple. And the last 3 bytes is the serial number uniquely associated with my NIC card on my MacBook Pro. The combination of the manufacturer ID and the serial number combined together is what makes this universally unique. Theoretically, no 2 hosts on planet Earth should ever have the same MAC address unless you manually change the MAC address. None of the devices on your LAN, at least, if not globally, at least within your local area network, you should never find 2 devices with the same MAC address. They should be universally unique, at least within your LAN. All right, another element to keep in mind is that MAC addresses are made up of hexadecimal numbering. To elaborate how that works, you can look at the chart. I've got 2 different charts here, one on the left and one to the right. There's also binary numbers, which could be kind of intimidating if you have never dealt with binary numbers before. So to make it less scary, I will make the binary numbers go away in this example. But rest assured that we'll talk about binary numbers in a lot of detail later in the course when we cover the layer 3 subnetting. But right now, I think it will only confuse you, so I'm gonna just go ahead and make the binary numbers disappear. But it should be fairly easy to understand that if you look at decimal 0, the hexadecimal value is also 0, 1 is 1, so on and so forth, until you get to number 10. As you can see, number 10 in decimal equals A in hexadecimal, 11 equals B, 12 equals C, so on and so forth until we get to 15, which happens to be F. Now, to the right-hand side, it's still the same thing, but what we're seeing now is a little bit of a different representation. For example, when we're dealing with a decimal value 255, that's all Fs. And when we're looking at a decimal value 0, that's 0, 0. Because this is how hexadecimals are actually represented in the MAC address format. So if you guys recall, the MAC address that we just looked at on my machine, on my MacBook Pro, the multiple octets that it had, that's how they were represented. There are 2 values, so something to keep in mind. Now let's quickly take a look at the topology that we'll be working with today. What we have in this topology, and I'll use this topology to explain a lot of different concepts, but before we move forward, I want to make sure you understand the topology. We got host A at the bottom of the screen on the left. To the right, we got host B. Each of these hosts are connected to their respective access switches. So if you guys recall the last lecture I did on the campus switching architecture, we talked about access, distribution, and core. Here we're looking at a collapsed core with access switches. So host A is connected to access switch 1 over fast Ethernet 0/10. Host B is connected to access switch 2 over fast Ethernet 10 as well. Access switch 1 is connected to core switch over fast Ethernet 1. Access switch 2 is connected to the core switch over fast Ethernet 2. Core switch is connected to R1 over gigabit 01. And it's connected to R2 over gigabit 02. Now, how do devices talk to each other on a local area network? When this host right here, host A, wants to talk to host B, it sends a frame to host B at layer 2. And what do we have at layer 2? We have MAC addresses at layer 2, the hardware address. Just like the address we looked at on my machine a little bit ago, we got the same thing on our hosts. Now to take it a step further, when host A wants to talk to host B, it will send out a packet. And in that packet, let's say we're trying to ping host B from host A. We'll have a ping packet. Then we'll have a layer 3 header. And within the layer 3 header, we'll have the IP address of the destination machine. IP address of the destination. And we'll then also have a layer 2 header, which will have the MAC address of the destination host. That's how a packet is constructed and communicated. Now, if you guys recall, switches don't understand layer 3. So what ends up happening is switches don't look at this and this, right? They don't see if it's a ping application or whatever. They don't understand layer 3. All they understand is layer 2. So what they look at is the MAC address. And switches have what's called a MAC address table or a CAM table, which CAM stands for Content Addressable Memory Table, or a MAC table. These terms are interchangeably used on switches. And at the end of the day, what that is a database of all the devices that are on that switch, that are connected on that switch. In this particular instance, we should have the MAC address of the following devices on these switches: R2, R1, host A, host B. Let's go ahead and take a look at this topology that I've built in Packet Tracer on the command line interface to see if that is actually the case. And let's also go ahead and jot down the MAC addresses of these devices while we're at it. So here is host A, and if we were to look at ipconfig/all in order to be able to see the hardware address, this right here, physical address. This is the one. This represents the physical hardware address of this machine. So any other machine on this LAN that wants to communicate with this machine, the destination address should be set to this value in the layer 2 header. We'll talk more about the layer 2 header as we continue moving forward, but that's what we need to do. What we should do to make things easier for us is to identify the MAC address for each device so we can easily see things through in our topology. So I'm going to go ahead and do that right now. Just like that, I was able to go ahead and extract MAC addresses from all the devices. Now let's go ahead and look at the database of our switches to see if they're seeing these MAC addresses in their MAC address table or CAM table. Here is access switch 1. Let's look at its MAC address table. Currently, it's only seeing one MAC address, it seems like. That means the ARP process, or the address resolution protocol, hasn't taken place across the entire network yet, because I just configured this lab and had these devices turned on. That said, let's jump right back into the presentation. Here's how the Ethernet frame looks like. If you were to zoom in at layer 2 into the Ethernet frame, this is how it looks like. We have a couple of different fields here that I would like for you to quickly take a look at. We got the destination MAC address field. So this is where we would put the MAC address of the machine that we're trying to access. Source is ourselves. So if I'm host A, this would be my MAC address. I'll call it MAC A. And if I'm trying to get to host B, the destination MAC would be MAC B. Ether type is the type of traffic we're dealing with. Payload contains whether it's IP packet, ARP, etc. And the data is up to 1500 bytes. And then the checksum, CRC checksum, which is 4 bytes. But what's most important is the MAC header size. That's 14 bytes in length. That's 6 bytes for the destination MAC address, 6 bytes for the source MAC address, and 2 bytes for the ether type. So 6 plus 6, 12 plus 2, 14. That's 14 bytes right there. That's your MAC header size at layer 2. And on top of it, you got the data payload, which is 1500 bytes. So typically an Ethernet type 2 frame is around 1518 bytes. Once again, because 1500 bytes happen to be the data, plus 14 for the header, plus 4 for the trailer or the CRC checksum. At the end of the day though, guys, I want to bring to your attention that all we care for is the data, the payload. We need to make sure our job as network administrators is to make sure that whatever the actual payload is, the application payload or the message that we are trying to deliver, that it gets delivered from source to destination. Everything else that we have to deal with is something we have to deal with as network engineers. That's why we get paid the big bucks, relatively speaking. But at the end of the day, it's about delivering the message that's encapsulated within all those headers. Just want to make sure that you guys keep that big picture perspective in mind. Now let's go slightly deeper into the switching fundamentals. So what is switching? Switching is a process of sending frames across a network from a source to destination. And there are a couple of things that I would like to talk about that led to the evolution of switching. In the beginning, in the olden days, like we're talking 1970s and 80s, we had hubs. And hubs primarily transmitted electrical signals at layer 1. They were layer 1 devices. They were called multi-port repeater because you literally had a single wire that would connect all the ports. So for example, here you're seeing all the ports up front. Every single host that would be plugged into these ports was actually sharing a single piece of wire, which created a lot of contention, which means there was a single collision domain and a single broadcast domain, and the bandwidth was shared across the entire device. Because once again, imagine if there's a single piece of wire that is split that allows multiple hosts to be able to connect to it. And then it was a half duplex communication at the end of the day, meaning only one device could speak or listen to, or could send or receive data at any given point in time. Then that led to the evolution of a layer 2 switch. Layer 2 switch, it forwards and receives frames. It's a layer 2 device. There's dedicated bandwidth per port. So if you have a 24-port switch, each port has its own dedicated bandwidth. There's no single wire concept here that all the hosts are sharing. Here, each host has a separate port dedicated to it, and it's a dedicated bandwidth. There's a single collision domain per port. However, there's a single broadcast domain per device by default. But we could change that broadcast domain. We can have multiple broadcast domains, but by default, there's only a single broadcast domain to begin with. But collision domain-wise, you're looking at a collision domain that's per port. And it's a full duplex communication device, meaning if it's a 100 meg port, the host is able to send and receive at 100 meg. So it's able to send data at 100 megabits per second, at the same time able to receive data at 100 megabits per second. And that led to the evolution of layer 3 or multi-layer switch. This inherits all the features of layer 2, but it's capable of layer 3. So it's a layer 3 device. It also has layer 4 intelligence, hence the name multi-layer switch. Most of the switches you'll see in networks today have layer 3 capabilities. Now, whether or not the end customer ends up using that switch as a layer 3 device is their choice. But most of the switches that you will see today in the network have layer 3 capabilities. Now, let's talk about a collision domain versus broadcast domain. Once again, looking at these hub devices, hub was a layer 1 device. As I said earlier, you can think as if all the ports that were available, they were all part of a single wire. And then every time multiple hosts started talking to each other, the frames would collide and be corrupted, and then the frames would have to be resent or retransmitted again. Whereas with the switch, you got a different situation going on. Each host is physically plugged into a switch with a dedicated port. And each port has its own unique collision domain. However, at the end of the day, we could have all these devices part of a single broadcast domain. Once again, that's a default behavior. We could create multiple broadcast domains on a switch, and we'll talk about that momentarily. Now let's quickly talk about how does a switch build its table or database or MAC address table or CAM table. Every single time devices want to communicate on Ethernet, they have to send each other ARP messages to be able to discover the MAC address of the other device. So what does that mean? So if we were to zoom into the MAC address table of the switch, there are two fields, port number and the MAC address. Here in this example, what we're seeing is host A is connected to port 1 and it has a MAC address of all A's. Host B, on the other hand, is connected to port 2 and it has a MAC address of all B's. Switches at the end of the day, like I said, guys, are devices that are responsible for forwarding frames based on MAC address. Switches operate at layer 1 and layer 2 of the OSI model. So that's another thing to keep in mind. Switches also deal with electrical signals because at the end of the day, each port has a device plugged into it, and the host that's plugged into the switch via that port and cable is sending electrical signals. So it's a device that is capable of communicating at layer 1, which is electrical signals, And then on top of it, it's capable of communicating at layer 2. By the way, switches forward frames using specialized hardware called ASIC, Application Specific Integrated Circuit. These are specialized chips that are built into the switches, and they allow switches to be able to process information at a wire speed. They provide extreme low latency, low cost, and high port density. Now let's talk about one of the most important concepts you'll come across in your networking career, and that is ARP, or Address Resolution Protocol. What is it? How does it work? As I mentioned earlier, every single time you have a device that's on an Ethernet network and it comes online for the first time, what it has to do is it has to discover other devices on that network via the process of ARP, so it figures out how to communicate with them. Now, at the end of the day, ARP is where we already have the IP address of the other device. So let's say, for example, if router 1 wants to communicate with router 2, router 1 has the IP address of router 2 already. Okay. Once again, IP addresses are logical at layer 3. MAC addresses are hardware specific. They're burned in hardware addresses at layer 2. So R1 wants to talk to R2. It has to be able to construct a frame that has R2's MAC address. Otherwise, it won't be able to communicate on Ethernet. So it sends ARP. And what it is you already have the IP. You need the MAC address of the other device. MAC is the question mark. And the way it works is R1 constructs a frame. And this is how the frame looks like. Let's do a quick whiteboard. So R2 constructs a frame, looks like this. It has the IP source address. It has the destination IP address. It has the source MAC address, and it has the destination MAC address. So if we were to go back to the diagram, let's quickly take a look. So R1, if it's constructing the ARP frame, it's going to put its own IP address, which is 10.10.100.1 in the source field. So let's go ahead and do that. 10.10.100.1. The destination IP that it's trying to reach is 10.10.100.2, which is the IP address of host 2. And then the MAC of source A would be its own MAC, so R1 MAC. And then it's going to have the destination MAC of R2. Now, interestingly enough, the very first time these devices communicate with each other, R2 and R1, they're not going to know each other's MAC address. So how do they discover each other's MAC address? Through this ARP process, what ends up happening is that if router 1 does not know R2's address, what it will do is it will, instead of putting in this field, it will modify this field. Here in the destination MAC, it's going to specify all Fs. And that's known as the flooding procedure. And let me explain. Let me go back to the diagram. So once you have all Fs in the destination MAC address field, when that frame is sent to core switch, the core switch is going to grab that frame. It's not going to look at layer 3 because it doesn't have layer 3 intelligence at all. It only looks at MAC addresses, right? And it's going to see the destination MAC set to all Fs. To this core switch, this means that it's a broadcast. It needs to flood this packet out everywhere. That's what's called the flooding procedure. So it's going to send this frame out fast Ethernet 01, fast Ethernet 02, and gigabit Ethernet 02. What's going to end up happening is that host A is going to get it. Because the destination IP doesn't match host A's IP, it will discard that frame. Host B is going to do the same thing. However, when router 2 gets it and it looks at its IP, the destination IP field in that packet, it's going to realize that, hey, it's destined for me. It responds back with its own MAC address. And when it does, the core switch is going to learn the MAC address of R2, put it in its table. Once again, what we have is port and MAC. So it's going to say, gigabit Ethernet 0/2 has R2 on it. And it's going to say gigabit Ethernet 0/1 has R1 on it. It's literally going to have R2's MAC on it and R1's MAC. And this way, it builds its table, its MAC address table or content addressable memory table or CAM table. And it's able to now allow these two devices to talk to each other. R1 and R2 are also going to end up adding this information to their ARP tables. So let's go ahead and take a look at in command line in Packet Tracer so you understand what's going on. We'll also take a look at a pretty cool simulation in Packet Tracer. So what I'm going to go ahead and do is I'm going to go ahead and shut off all the interfaces and re-enable them. And we'll quickly go ahead and then do a network simulation. And in this network simulation, we're going to just look at ARP. So you guys get to see how this works. As you guys can see, core switch got that ARP message from R1. It sent it to everybody. And as you can see, host A and host B discarded that message. And let's see, when core switch received it, what did it see? It actually saw that the destination field was set to all Fs, as you're seeing here. And then it had the source IP of itself, 10.10.101, and the destination IP of 10.10.100.2. So this is how you can do a packet analysis. Now, because this is Packet Tracer, I can't run a debug ARP command. For some reason, it's not supported in this version of the Packet Tracer that I have, even though it's the latest version. But if you had access to real gear, or if you had GNS3, you could quickly fire that up. But I wanted to show you the network simulation piece of it because I think it's really cool. And you get to see at a much deeper level via a GUI how that looks like, which I think is pretty cool. And one last thing to think about, guys, is ICMP is a bidirectional communication. It's composed of two messages or two packets. One is where R1 is sending a ping or ICMP echo response. That's the initial message that's sent. What ends up happening is R2 then is supposed to respond back to R1, and that's called ICMP echo reply. So it's a bidirectional communication that happens. Let me quickly go back to the command line interface again to show you the ARP, how to look at the ARP table on a router, and also how to review the MAC address table quickly. Here I am on router 1. I'm going to go ahead and quickly take a look at the interfaces on this router, and I'm going to go ahead and shut off gigabit 000. And what that does is it goes ahead and resets all the layer 2 and layer 3 processes. And I'm going to go ahead and bring it back up by typing in no-shut. By the way, when you type in do in front of any command, you don't have to be in the privilege exec mode to be able to run the show command. You can do it from any mode you're in. So it's a pretty cool trick. I believe I shared that with you in some of my previous videos, but I wanted to bring that up again. I'm going to go ahead and look at my ARP table. I should only have my own IP address. If I'm going to go ahead and ping router 2, which is 10.10.102, watch what happens. You see, we lost a packet, and then after that, we had a successful ping. So we dropped the first packet, and then the other 4 packets were successfully delivered. What was happening in the meantime was that the frame was sent to the switch with all Fs inside it. And what the switch did with that frame here, in the core switch in our example here, was that it looked at, let's quickly take a look at it, show MAC address table. And it looked at it, and assuming it didn't have an entry for the MAC address of router 2, it's sent out a broadcast out all the ports except the port that it initially received the ARP on, and then when router 2 responded back to it, it added router 2's MAC, plus it added router 1's MAC when the initial request came in for ARP. And by doing that, it was able to build its MAC address table. So it's a hop-by-hop communication idea. Each device has to do that within an Ethernet network. Each switch and router has to do that. And as a matter of fact, even a PC has its own ARP table. So if you were to ping again, you're going to see we're not going to drop the packet. Because if I were to look at show ARP, as you can see before we did the ping, we only had our own IP. But after we did the ping on router 1, we now also have router 2's MAC address in our ARP table. And as long as we have that in our ARP table, we should now be able to construct frames and send directly to R2 through the switch in the middle. Because remember, R1 and R2 are not directly connected. They're connected with each other through the core switch in the middle. VLAN stands for Virtual Local Area Network. VLANs live on layer 2 of the OSI model. They have the ability to slice a single physical switch into multiple logical switches. And they logically segment a physical switch into multiple broadcast domains. So a couple of things I talked about, let me explain. So first, they slice a physical switch into multiple logical switches. So if you look at what I've drawn up here, up at the top, this is a single switch. It has green ports, red ports, and a blue port, and also a white port. Now the white port here is the trunk port, so forget about that, we'll talk about it in a moment. But blue port is a voice VLAN, red port could be sales VLAN, green port could be marketing VLAN. By assigning different VLANs to different ports, we're able to take a single physical switch and make it appear as if it's part of multiple logical switches. What does that mean? By default, this host, let's say if this is host A and this is host B, they cannot talk to each other because they're on different VLANs. Host A is on the green VLAN, host B is on the red VLAN. They're different VLANs. They cannot talk to each other. Also, switches by default, like I said, have what's called a default VLAN. And default VLAN is VLAN 1, which means all the ports by default are assigned to that VLAN. But we have the ability to change that. Now, all the ports that belong to the same VLAN, they create what's called a single broadcast domain. So for example, in our case, these two ports, the green ports, and these two green ports combined together, these 4 green ports are part of a single broadcast domain. These red ports right here are part of another broadcast domain. So what that means is, so remember we talked about how all Fs are sent when there's an ARP communication that happens? When you have logical segmentation like that, the broadcast is contained within that broadcast domain. So the green ports are part of a single broadcast domain, and hosts attached to those ports can only see and send broadcasts within that domain. The red ports or any other VLAN, the blue one, they do not get affected. They never see the broadcast. They never get impacted by it. It's a nice way of reducing the broadcast domain, because broadcast is a good thing because that allows us to discover devices. It's also a bad thing because it takes CPU cycles and memory not only on the switch, but also the hosts that receive those frames that they don't care for. So this is a way of kind of bringing order to the chaos, if you will. And in a traditional layer 2 network, like I said, devices in one VLAN can't talk to devices in another VLAN. Also, one VLAN equals one subnet. That's a 1-to-1 ratio. So when we talk about IP addressing later, when we discuss layer 3, that's section 3 of the course, you'll get to learn what that means, but just remember that one VLAN equals one subnet at layer 3. And finally, VLANs can also be used for security to control access. Now, it's a very rudimentary level of security. You cannot consider it by today's standards and by today's sophisticated type of attacks that are being launched. VLAN is not going to cut it. It's a very small, minute piece of the puzzle that security is. But nevertheless, it's poor man's security at a very basic fundamental level. That said, now let's look at the command line interface. Here I am on the core switch in Packet Tracer. Let's take a look. Show VLAN brief. That's a command you guys want to memorize. Okay, so now we're getting our hands dirty. That's how we become a network engineer, right? Got to gain confidence, got to do hands-on stuff. That's what it's about. So as you can see, all of these ports that you're seeing on the switch are automatically part of VLAN 1. That's also called a default VLAN. Okay, so I want you to keep that in mind. That's also an exam question. What's a default VLAN? VLAN 1 on a switch is considered a default VLAN. All the ports are automatically assigned to it. Now there's a couple of additional reserved VLANs, 1002 through 1005. We don't care for them because they're legacy, they're obsolete. We don't care for them. The only one we care for is the default one and the ones that we will create. Now, one thing you want to keep in mind though is do not use the default VLAN. Cisco suggests that as soon as you get a switch, create new VLANs and make sure that all of your ports are outside of VLAN 1. Because VLAN 1 is a low-hanging fruit for hackers, right? Bad actors. Anybody and everybody on planet Earth knows that every single switch on planet Earth, whether it's Cisco or non-Cisco, has VLAN 1 by default. So they can construct frames, they can do things that can cause havoc within your switching environment using VLAN 1. But if you didn't allow the bad actor to do that, that's good security to begin with. That's good practice. So that said, let's go ahead and create our first VLAN. So we'll do configuration terminal. We want to type in VLAN, let's say 20, and we'll call it sales. And what we'll do next is we'll create VLAN 30 and we'll call it marketing. Exit, show VLAN brief, and voila, here we go. We got sales and marketing VLANs created. Now, as you can see, there are no ports in front of these VLANs, which means these VLANs exist on this switch, but as long as there are no ports associated with them, they're useless. Like they're not doing anything. They're not participating in any function on this switch. So what we have to do next is we have to assign ports to these VLANs. And we have different types of ports, and we'll get into the port types later, but let's take a look at how to configure a switch port to begin with. Interface range fast Ethernet 0/11-15. That means port 11 through 15. We'll be able to take this configuration. Switch port mode access. That means that these are access ports. So if you recall, access distribution core, access is where we have end devices and end hosts plugged in. We'll type in switch port access VLAN, let's say 20, which is the sales VLAN. This command assigned fast Ethernet 11 through 15 to the sales VLAN. Now let's do this next. Fast Ethernet 16 through 20, we're going to go ahead and say switch port mode access and switch port access VLAN 30. Exit and show VLAN brief. And what you will now see is that sales has ports assigned to it and marketing has ports assigned to it. So what that means is if you took port 11 and plugged a desktop into it or an IP phone into it, it's automatically going to belong to this VLAN, sales VLAN. And if you have marketing folks, you can go ahead and plug in marketing folks in marketing VLAN, and you can have different types of configuration like DHCP server and TFTP and other things for their phone and other types of configuration that their host can automatically get by being part of this VLAN. And we'll talk through those design details later, but these are the fundamental pieces that will help you understand how this works. Now, if you wanted to delete VLANs on a switch, what you have to do is there's a very specific command. You have to type in a command, delete VLAN.dat, and you have to hit enter twice, and then you have to type in reload. So I went ahead and rebooted the switch so we can take a look. Let's take a look, show VLAN brief, and voila, all those VLANs are gone, but the rest of our configuration is intact. The next thing you want to talk about is VTP, which stands for Virtual Trunking Protocol. Now, in my opinion, it's a bad name because it's not about trunking. Instead, VTP has to do with VLAN propagation. Here's what it means. So when you have a brand new switch that you pull out of the box, it has VTP revision 0. When you create VLANs on it, it automatically changes the revision number. And when you have other switches on the network that are connected to that switch where you made the VLAN changes, they automatically inherit those VLANs that you created. That was a very rudimentary form of automation back in the day. It did have its positive sides, but because it was able to also create chaos in the network, meaning not every single switch in your network needs to have the same VLANs. Maybe on floor 1, you have salespeople. On floor 2, maybe you have marketing people, but perhaps those two switches are connected with each other through a distribution switch. You don't want to delete a VLAN within the sales realm that somehow ends up causing changes to the switch in the marketing realm. So because of its negative aspect, VTP is not really utilized much. Here's a trick though. If you want to add an old switch to your network, most likely it will have a very high revision number. Make sure that you change the revision number by changing the VTP domain name and then changing it back to the original name. So that's a bit of a trick if you wanted to avoid adding an old switch to your environment and then that switch completely ruining your configuration throughout your entire environment. Ideally, you should disable VTP. Some of the newer switches have the ability to actually type in a command that allows you to disable VTP. In the olden days, you would actually have to use a very specific mechanism to disable VTP, and let's talk about that. VTP has 3 different modes: server, client, transparent. Server is the default mode on all Cisco switches. It's the most powerful mode. You can add, delete, change, propagate VLANs. In this mode, switches can send and receive updates. This allows VLAN configuration to be saved. In the client mode, it doesn't allow you to configure VLANs. It's a read-only mode. It can send and receive updates though, but VLAN information cannot be changed. Transparent mode, on the other hand, is the same as the server mode, with the exception of the fact that a switch in this mode does not listen to VTP advertisements. Okay, so this was the way of disabling VTP, meaning if you're a transparent switch, you're transparent to VTP, meaning you don't care for VTP updates. You're not going to change your database. You're not going to pass on the updates to somebody else. You're just a transparent device. They do forward updates to other switches though, in VTP version 2 only, but they do not accept changes. It's being deprecated. Most likely it's not going to be on the exam, but it's good for you to know from a real world perspective in case if you ever have to troubleshoot VTP. There's another concept related to VTP called VTP pruning. So what that means is, I'll give you a very quick example. It stops unnecessary broadcast traffic from being propagated. So for example, if you were to look at the diagram that I have here, you got all these different switches. We have these different VLANs configured. As you can see, the bottom switch does not have the yellow VLAN. The yellow VLAN is the sales VLAN. Because the bottom switch does not need to see the yellow VLAN, we can type in switch port trunk pruning VLAN command on this port right here, connecting to the bottom switch. So the middle switch right here will configure VTP pruning for that particular VLAN. And any messages, any broadcasts that are sent on that yellow VLAN will never be propagated down. So it saves the switch at the bottom from having to deal with unnecessary broadcasts, and all of its hosts are also spared as well. Now let's quickly take a look at the command line interface for the VTP configuration. Let's look at show VTP status. So as you can see, it says we are on VTP version 2, revision 0, maximum VLAN supported locally are 255, number of existing VLANs is 5. Once again, this is the default behavior, right? We haven't created any new VLANs or anything like that. The switch is in its default state. And as I alluded to earlier, by default, we are in server mode. Switch is most vulnerable in the default mode. Reason is, it can automatically pick up VTP parameters from other switches in the environment. So if you're not going to use VTP in your environment, you should go ahead and change it to transparent mode. And like I said, some of the newer switches now have the capability of disabling VTP to begin with. And the way we can change the VTP configuration is you go to the global config mode, type in VTP space question mark, and it will give you the ability to make changes. Here we can change the mode and we can change it to transparent. If we do that, the device ends up becoming transparent, which means it can forward VTP information, but it's not going to accept it. If we did that on all the switches in our environment, this essentially disables VTP across the board in our entire environment. Now let's talk about trunking. So what trunking is it's a mechanism that allows switches to allow multiple VLANs to be sent across switches. It's also known as tagging. So what that means is it's a layer 2 technology, trunking. And as you can see, this right here is a trunk port. So a port that interconnects switches together is called a trunk port. Doesn't have to be the case, but for the most part, when you interconnect switches together, that's where the trunk link is configured. You can also have a trunk link configured between a switch and a router, for example. There are some exceptions to the rule, but for the most part, when you interconnect switches together like that, the links that interconnect the switches are called trunk links. And as you can see here, if the switch at the top has green and red VLAN and same as the bottom switch, they need to be able to send frames that belong to both VLANs, the red and the green one. So the trunk link carries multiple VLANs inside it. There are two different VLAN tagging protocols. The first one, ISL, which has been deprecated. It's obsolete now. It's called Inter-Switch Link Protocol, Cisco proprietary. It used double tagging and all that. Whereas .1Q, that's the industry standard. It uses an internal tag. It's much more efficient because it has a single tag. And it also has a concept of native VLAN on a trunk. What's a native VLAN? Any VLAN, anytime a switch receives untagged frames, they're handled by the native VLAN. They're not encapsulated with tagging. Bottom line, the native VLAN allows untagged frames to be carried across switches over .1Q trunk. By the way, 802.1Q is also referred to as .1Q. So something to keep in mind. Here's the structure of the frame. Up at the top is the ISL, which had a 26-byte header. That's a huge overhead. Contrast that to the 802.1Q header, which is only 4 byte in length. And if you were to zoom into the 4 bytes, you'll see we have the TP ID, we have the priority. What you care for are the two fields in here. Priority, this has to do with class of service, COS, or class of service, or quality of service. We'll discuss this later in the course. And VID, or the VLAN identifier, or the VLAN ID. And it's a 12-bit field, which means it goes from 0 through 4095. Another thing I want to talk about is DTP, or Dynamic Trunking Protocol. It auto-negotiates a trunk between switches. So what that means is when you have a switch, let's say switch 1, and you have another switch, switch 2, the minute you connect them together and they start talking to each other, they will auto-negotiate a trunk over this interlink between the switches. And it's a Cisco proprietary protocol, and it uses either ISL or .1Q. If both ends support both types, then ISL is favored because it's Cisco proprietary. Now, another element which is very important is switch port modes. A Cisco switch can only be in one of the following 5 modes. You've got yourself the access mode. So if you guys remember, we did switch port mode access, right? So this is where the end stations are plugged in. Your PC, your IP phone, things like that. Trunk is a switch to switch or a switch to router connection. And the way we configure that is switch port mode trunk command. Then what we have is the DTP that we just discussed, right? Dynamic Trunking Protocol. These are the 2 elements that come into play with DTP. Either we have the dynamic auto mode or dynamic desirable mode. Dynamic auto is a passive mode. And the way it works is if both sides of the switch has switch port mode dynamic auto configured, then the link will never become a trunk because it's a passive mode. One side has to be active. Dynamic desirable, however, on the other hand, is an active mode. So if you had one side that was dynamic desirable and the other side that was dynamic auto, then they will form a trunk. If both sides are dynamic desirable, they will still form a trunk. But if both sides are dynamic auto, they won't form a trunk. So very important distinction to keep in mind. If you wanted to disable DTP, you can just type in switch port no negotiate command. So you can disable the dynamic trunking protocol. Now let's go back and look at the CLI and see how we can configure trunks. I'm on the core switch. I'm going to go ahead and go to global configuration mode and modify interfaces fast Ethernet 1 and 2 and make them trunk links. So I'll go switch port mode trunk. So now I've essentially made these ports trunk ports because that's what I have, right? My fast Ethernet 1 and 2, if you were to go back and look at the diagram, my fast Ethernet 1 and 2 are trunk links because they're connected to access switches, because I'm the core switch. And the next thing you want to type in is switch port trunk allowed VLAN. So here we can specify if we want certain VLANs to be allowed or to be removed from the list. Here we can, once again, this is another kind of a security element where you're being very specific in terms of what VLANs you want to allow across a certain trunk link. You can do that here. Let me go all the way back to the user exec mode. Here, let's look at a couple of additional commands. Show DTP. So this shows that we actually have DTP running. Another important command to look at is show interface trunk. This shows us the type of trunk we have. So we got 2 links that are connected to switches. Fast Ethernet 1 is connected to switch 1, access switch 1, fast Ethernet connected to access switch 2. Here we have encapsulation set to .1Q, and we are successfully trunking. As I mentioned, we also have this concept of native VLAN. Once again, the whole idea of native VLAN is if you ever receive untagged frames, which we should never in an ideal scenario, but if you had like an old school hub or some non-Cisco switch that does not understand tagging for some reason, and if you were to receive that frame, it can be handled by native VLAN. It's a mechanism for allowing untagged traffic to be sent across switches. That's what native VLAN does. So Ideally, according to Cisco, we should never have native VLAN set to VLAN 1. Native VLAN should be set to something other than VLAN 1. So to show you how to do that, we'll go to Configure Terminal. We'll go to Interface Range Fast Ethernet 1-2, and we'll type in switch port trunk native VLAN, and we'll call it VLAN 10. So we made the native VLAN VLAN 10. It's no longer the default VLAN. Now let's make sure we also have show VLAN brief, that VLAN created. See, we don't actually have that VLAN here, so it's not actually going to work. What we have to do is we have to go to Configure Terminal and type in VLAN 10. So we actually have that VLAN. That's why we received this native VLAN mismatch message, because we didn't actually have VLAN 10 configured on our switch. Now let's look at show VLAN brief. We have VLAN 10, that's good. And now let's look at show interfaces trunk, and the native VLAN is set to 10. We should stop seeing that error message that we saw earlier where Cisco Discovery Protocol, or CDP, was complaining that there was a mismatch. Speaking of CDP, that's also a pretty powerful way of looking at our topology. So we can type in a command show CDP, and it shows us whether or not we're running CDP. And if you did show CDP neighbors is a cool command because it quickly shows you who our neighbors are, the name of the device, and the port over which we're connected with them, and also the platform. It's really, really cool. It's a very, very powerful command, especially if you're a consultant and you walk into a brand new environment, you have no idea how it's set up. If the customer has shared the diagram with you, the diagram is fine, but this is how you verify the diagram to make sure at a physical level, the diagram represents how things are connected together. Because remember, guys, when you're troubleshooting or you're building or architecting a network, every single link and how it's interconnected matters. That's how you figure out whether or not things will work as predicted. Welcome to CCNA 200-301 course. Today, I'm going to discuss Section 2, Part 2, LAN, wired and wireless. In particular, we're going to focus on advanced LAN switching concepts. Here are the topics I plan on covering today. First, CDP. Second, STP, PVST, and RSTP. Third, STP Optional Features. Fourth, EtherChannel. And finally, I'll wrap it up with inner VLAN routing. So what is CDP? CDP stands for Cisco Discovery Protocol. As the name gives it away, it's Cisco proprietary, meaning only Cisco devices speak this protocol. The whole purpose of this protocol is to help discover neighbors. So for example, if I'm a switch and I have other switches and routers plugged into me, when CDP is enabled everywhere, I can see who are the neighbors that are connected to me. Typically, network engineers and consultants use CDP to verify physical connectivity of a network. And I'll give you an example of how that works on a switch CLI in a moment. The way CDP allows discovery to happen is through CDP messages. And these messages are sent across all ports on all routers and switches by default. Another interesting tidbit, Cisco IP phones use CDP to learn both the data and voice VLAN IDs that are configured on that access switch port. And finally, LLDP, or Link Layer Discovery Protocol, is a competing standard to CDP and is defined in IEEE 802.1ab standard. If you happen to have any non-Cisco switch in your environment, whether Arista, Juniper, or you name it, any other switch, it runs LLDP for the purpose of discovering neighbors. So what you would have to do in that instance is, if you have a mixed environment, Cisco and non-Cisco, you should actually run LLDP everywhere instead of running CDP. Because this way, whether you're connected to a Cisco neighbor or a non-Cisco neighbor, you can discover and see what's going on. Now, just by looking at these bullets, it's probably not sinking in much. Let me jump right into the CLI so I can help you crystallize how CDP works. Here I am on switch 1. Here's the magic command you want to know. Show CDP neighbors. On switch 1, what I can see by running this command is that I've got 3 different devices that are plugged into me. And those 3 devices are, I've got switch 2 plugged into me over fast Ethernet 0/12. And the capability flag here corresponds to a switch because it's a switch. And the platform is Catalyst 2960. And the remote port ID, the port ID of the remote switch that's plugged in is this. Similarly, S3 right below it is connected over fast Ethernet 0/13. The flag is also S. And platform is Catalyst 2960. Remote port happens to also be fast Ethernet 0/13. Finally, R1. Our local interface is Gigabit Ethernet 01. Flag is set to R because it's a router. It's an ISR 4300 router. And the remote interface on that router that is pointing toward us is Gigabit 000. Now, another interesting command that gives us a lot more detail about our neighbors is show CDP neighbors detail. Now, one thing I would like to draw your attention to here is that so here we're looking at router 1, and I can see the IP address of router 1, so that's pretty neat. Right? So as you can imagine, if I've got other devices plugged in and I'm walking into an environment completely cold as a consultant, I had never worked in this environment before. I have no clue how this environment is set up. By using show CDP on different switches and routers, I can start to map out how the network is set up. I can actually create a diagram with physical connections so I can see how it's all interconnected. In addition, as a bonus, I can also specify the IP addresses of the devices as well. So really, really cool feature. Now I'm going to warn you, it works wonders if it's a small environment. But the minute you start looking at gigantic global environments, it's not going to work. If you have hundreds of switches or thousands of switches, it's insanity to go to each switch and start mapping things out. You're going to go crazy. Instead, there are other tools that you can use for monitoring purposes and things like that. But at the same time, typically larger networks, the network engineers that manage those environments have really good documentation, or they're supposed to have really good documentation. That includes really nice Visio diagrams, some additional documentation that talks about the purpose of each device in the network, and things of that nature. Now, if you want to disable CDP on a switch, we type in no CDP run command. And when we do that, this essentially kills CDP on the entire switch, which means we're not going to be able to see our neighbors and vice versa. Our neighbors are not going to be able to see us because the CDP packets, CDP messages, CDP frames have been killed. CDP basically, just so you know, runs at layer 2. This disables it at a global level on all the ports. But let's say if we didn't want to do that, we would do CDP run. So we enable it again on this switch. But what we can do instead is we could go to a particular port, and at the sub-interface level, we can do no CDP enable. And what that would do is kill CDP on this interface only. So there are two different ways of doing it. One at a global level with no CDP run, or we could do it at a per interface level by typing in no CDP enable. Now, if you wanted to enable it back on this interface, all you would have to do is just delete that keyword no in front of the command. Just type in CDP enable and boom, it's gonna enable CDP again on fast 01. Now, that being said, if you wanted to set up LLDP on our switch, we can do that by first disabling CDP and by enabling LLDP run. And when we do that, it's going to enable LLDP on the switch. Now we're going to have to type in the same command on all the other switches and routers to make sure we have a standardized environment and we're sending same type of packets and we're able to see each other. So you're going to have to go to all the remote devices and do the same thing. I'm not going to go much into LLDP because it's very similar to CDP. I just wanted you to understand conceptually how that works. Now, let's talk about STP. What is STP? It stands for Spanning Tree Protocol. It's a layer 2 protocol, and the entire purpose in life for Spanning Tree Protocol is to create a loop-free topology by blocking redundant links. Why do we need to do that? Well, in a network, we need redundancy. Without redundancy, we find ourselves in a bad place. So to give you an example, let's say we have a couple of switches here. So we got switch 1, switch 2, switch 3. They're all connected to each other back to back in a daisy chain style. And we got host A here connected to switch 1, and we got a server 1 connected to switch 3. Now, if this guy, let's say Bob, wants to connect to the server, he's going to have to go this direction. Well, what if this link fails? The entire communication fails. What if this link fails? The entire communication fails. That is unacceptable. So what we do is we create redundancy by having a scenario like this where we have redundant links. So if any of these links went down, we still had another path to go from source, from Bob to the server, from source to destination, right? That's the entire idea of having a network. But the issue is that when we do this type of redundancy in a layer 2 network without running Spanning Tree Protocol, we run into some major issues. And there are 3 big issues that I would like to bring to your attention. Issue number 1, broadcast storm. Issue number 2, CAM table instability. Issue number 3, transmission of multiple frames to the destination. Well, what does that mean? Let me explain on the next slide. In a scenario like this, where we have host A connected to a switch, host B connected to another switch, and these two switches are connected to each other via a single link, that's not a problem. They can talk to each other all day long, even without running spanning tree, not an issue. But the minute we add this second link into the picture here, well, we got ourselves a problem if we're not running STP. What's going to end up happening is when host A wants to talk to host B, it's going to send an ARP message, Address Resolution Protocol. So remember, ARP, we already have a layer 3 IP address of the device you want to talk to, in this case, host B. But what we do not have is the layer 2 MAC address. That's the question mark. So what we end up doing is we construct an ARP frame and we send it out. And at layer 2 of this ARP frame, if you were to zoom into it, what we'll see is that the destination MAC address field is set to all Fs because host A does not have the entry of MAC address for host B in its ARP table. That's why it sent the ARP message to begin with. When that happens, this switch in the middle, let's say switch 1, and the top one is switch 2, switch 1 is going to get it. And it doesn't understand layer 3 at all. So it's only going to look at source and destination MAC address. When it looks at the source MAC, it goes ahead and puts the MAC address of A in its CAM table or MAC address table. However, when it looks at the destination field, it realizes that it does not have that in its CAM table or MAC address table. So it sends out a broadcast. So this is the port that it initially received the request on. It's not going to send the broadcast out here. However, it will flood this frame out all the connected ports. So switch 2 is going to get that frame twice over each link, and host B is going to get that frame. Now, when host B gets that frame, it's going to respond back with its MAC address, because when it looks at the layer 3 destination IP field, that IP address will match its own IP. So it responds back to host A with its MAC address. When it does, switch 2 learns that MAC address and puts it in its CAM table or content addressable memory table. We have redundant links, so the frame is being sent out both links in all directions. When switch 2 gets that frame that was initially sent by switch 1, it's gonna send it back out to switch 1 again. It creates this kind of broadcast storm where the frame keeps looping around the network over and over and over again. And unfortunately, at layer 2, we do not have what's called a TTL value or time to live value, which we do at layer 3, but at layer 2, we do not have TTL at layer 2. So what that means is the frame can literally loop around forever and ever, bringing the network to its knees unless you turn off the switches or you break one of the links or you do something manually to stop that from happening. So that's the first problem we get. The second problem we have to deal with is the CAM table instability. So let me explain. Let's say if this is port 1 and this is port 2. When switch 1 sends that frame out to switch 2 with the source MAC address of host A, not only switch 1 is going to learn it, but switch 2 will also learn it because of the fact that that source MAC address is in that layer 2 header field. So it's going to grab it and insert it into the CAM table. That's what switches do. They learn MAC addresses. Let's say if that frame arrived maybe a few milliseconds before arriving over port 2, switch 2 is going to have confusion in its MAC table. It's going to say, well, I've got MAC address A available over port 1. But when the same frame arrives a few milliseconds later, it's going to get confused and go, no, it's not over port 1. It's actually on port 2 is where MAC address of A lives. And when it does that, it's going to keep switching back and forth as it continues to get frames. And this causes MAC instability because you're going to keep switching back and forth between port 1 and port 2. And finally, because we have these redundant ports and multiple frames, the host may end up getting multiple copies of the same frame, and it would cause issues. The application that host B is running might actually crash because it may not know how to handle duplicate frames. So these are the 3 big issues that occur in a network when there's no spanning tree running. Now let's jump into STP fundamentals. As I mentioned, it's a link layer protocol. It's a layer 2 protocol designed to ensure loop-free topology. It's defined in IEEE standard 802.1d. So it's an open standard. It's not proprietary to Cisco, which is good. Switches use special frames called BPDUs or probes to exchange information about bridge IDs and route path costs, and we'll talk about those details momentarily. You'll be an expert in a few minutes. But before we get there, what are BPDUs? They are Bridge Protocol Data Units. BPDUs are essentially spanning tree advertisements. BPDUs are sent out all active ports on a switch every 2 seconds by default. However, on the non-root bridge, BPDU hello messages are sent based on the timer configured on the root switch. So let's say if on the root switch you change the timer to a non-default value, the non-root bridges will adhere to that non-default value. And remember, the main function of STP is to do what? To discover loops in the network and find the most efficient way back to the root and block the redundant links. Now let's talk about bridge ID. Each BPDU frame contains within it two major fields, a bridge priority and switch's MAC address. Combined together, it's called bridge ID or BID. So here we get to see that we have a bridge ID of 8 bytes altogether at layer 2. We're basically looking at a layer 2 header of the BPDU. We got the bridge priority here, which is 2 bytes, which means it's a value anywhere from 0 to 65, 535. Default is right in the middle. And the other piece of it is the MAC address, which is 6 bytes. And that MAC address is derived from the backplane of the switch or the supervisor. So if it's a fixed switch, this MAC address is derived from the backplane. If it's a modular switch with supervisor modules in it, it's going to derive its MAC address from the supervisor module. Default bridge priority is 32,768, and it can be modified in the increments of 4096. Now, one thing I want you guys to keep in mind is when it comes to bridge priority, lower value is better. One more thing about BPDUs, there are two different types of BPDUs. You have configuration BPDUs and you have topology change notification BPDUs. Configuration BPDUs are originated by the root bridge and they flow outward away from the root, whereas the topology change notification BPDUs flow toward the root bridge for providing topology change updates. Now let me explain what I mean by that right here. If this guy up at the top ends up becoming a root bridge of our network, what that means is all of these switches here in our environment are going to try to find a way back to the root without causing loops. So what that means is this link will get blocked, this link will most likely get blocked, and access switch 1 at the bottom will go through distribution switch 1 up to core switch 1. And access switch 2 is going to go to distribution 3 up to core switch 1. So the idea is that we always want to have a single path toward the root bridge, and this inherently helps us avoid loops because we're only going in one direction and there is no opportunity for the same frame to kind of boomerang or loop back around to us because we're only going in one direction. So that's the whole idea of STP. So we have this root bridge and everybody kind of gravitate towards this root bridge and it becomes the center of the universe for our STP domain. Now, as I mentioned, there are two different types of BPDUs, config BPDUs and topology change notification BPDUs. Now, configuration BPDUs are sent by the root bridge. So the root bridge actually sends configuration BPDUs, and they're sent down this way, downstream. Another terminology I want you to understand, when we go up toward the root, that's upstream. When we go down from the root down to the other switches, that's called downstream. So the core switch sends configurations BPDUs downstream, whereas the topology change notification BPDUs are sent upstream by the non-root bridges to inform the root bridge of any change that happened in the network. Now let's talk about 3 steps of initial STP convergence. Very, very critical to understanding STP. First thing that happens is we must select or elect one root bridge. So as soon as you have these multiple switches in your environment connected together, they come online, the first thing they want to do is they go through a series of steps. And the very first step in the process is to elect one root bridge, or the king of the hill, if you will. All switches exchange BPDUs, and the switch with the lowest bridge ID ends up becoming a root bridge by default. So for example, in the topology that we have here, this bottom switch ends up becoming a root bridge. And the reason for that is because it has the lowest MAC address. So remember, the bridge ID is composed of two components. We got the bridge priority and we got the MAC address. And this right here is the bridge priority. So if you were to look at all these, the reason switch A became the root bridge is because from a hexadecimal perspective, A is lower than B or C. Because A in decimal is 10, whereas B in decimal is 11, C in decimal is 12. So this guy becomes the root bridge. However, root bridge election can be manipulated by changing the priority in bridge ID since MAC address is hard-coded into each switch. So because we can't change MAC, the only way to influence the election process is by changing the bridge priority. And I'll show you that on a CLI in a moment. By the way, a pro tip, because the lowest number MAC address ends up winning the election, what that means is the oldest switch in your network that you bought in 1990s that is still out there sitting in a closet somewhere most likely will end up becoming a root bridge if you don't define a root bridge yourself. So it's a bad place to be, something you have to keep in mind. And I've seen some networks and very, very ugly designs where network administrators didn't really pay attention to what was happening and they let spanning tree do its thing. By default, it's not good. It's very bad. And I'll give you a couple of examples, including a visual example to show you how bad it is. All right, step number 2. After electing the root bridge, we want to elect root ports. Root ports are elected on the non-root bridges. It's the closest port to the root bridge. Every non-root switch needs to have one root port and only one. The third step in the initial convergence is, so first we elected the root bridge. Second, we elected the root port. Third, we want to elect designated ports. After the root ports are assigned, switches allocate one designated port per link. Designated port equals forwarding port. So if you were to look at the topology here, considering the bottom switch is the root bridge, both switch B and C will have a root port pointing to the root, and then switch B will have a designated port pointing to switch C. However, the port on switch C going toward B is going to be in a blocking state. And one thing I want to touch base on when it comes to this blocking port is that the data plane traffic on the blocking port is dropped. Only control plane traffic is allowed. Because control plane is a spanning tree, right? And I actually did a video on the topic of control plane versus data plane. Watch my SDN video, software defined networking video, to learn more. But once again, on the blocking port, there's no user data traffic that's sent. Because again, the idea is we want to avoid frames from looping around the network. Quickly, here's our network topology that we'll be working with today when it comes to spanning tree. As you can see, we got a couple of switches connected in a triangle, and we got each switch has a router hanging off of it. Now, before I jump into CLI, let me finish talking about the election process and then jump into CLI, because I think that will help crystallize some of the concepts that we just talked about. So how STP elects the root port per switch. First, as I mentioned earlier, we must elect a root bridge. And this is the switch with the lowest bridge ID. It ends up becoming the root bridge. Once that happens, that's out of the way. The next thing you want to focus on is the root port election. First step here is the lowest cost to the root bridge. In case of the same cost on multiple links, so for example, if the switch at the top is the root bridge and the switch at the bottom is a non-root bridge, if I have two links like that, both are 100 meg links, the cost is the same on both links. So I can't use that criteria to elect a root port, the most efficient port going to the root bridge, right? I cannot do that because the cost is the same on both links. What we do is you look at the lowest sender bridge ID. And if that is also a tie, then we finally look at lowest port priority. Now this is very, very random. This is an absolute tiebreaker, and you will absolutely finish the election process here because each port has a unique port priority. That said, so as I mentioned, the cost, there's an inverse relationship between the bandwidth and the cost. So for example, a 10 meg link is a 100 in STP cost, but a 100 meg link is 19 in STP. A gig E link is 4 in STP, and a 10 gig link is 2 when it comes to STP cost, which means the lower the STP cost, the better and the more preferred the link would be. That said, let's jump right into the CLI. So here I'm on switch 3. Let me go ahead and quickly look at a couple of commands. Show spanning tree. That's the first command I want to look at. Here, what it's showing me is that this bridge is the root. What that means is that I am the root bridge. So S3 in our topology is the root bridge. This guy right here. And a couple of things I would like to bring to your attention here. First, like I said, this bridge is a root. That's important. Here's the bridge priority. And the MAC address, which is right here, should be the same as here because we are the root bridge. And we see things like, the hello timer, like I said, 2 seconds. The max age timer is 20 seconds. There's a forward delay of 15 seconds, and then aging time is 20 seconds. A couple of other things I want to draw your attention to is that we're connected to a couple of different devices here on our network that are also running spanning tree. So because we're the root bridge, we've got Fast Ethernet 13 specified as a designated port, which means it's in forwarding status. And the cost is 19 because it's a 100 meg link. And we see the port priority number here, 128.13. And Fast Ethernet 0/23 with the cost of 19, which is also a 100 meg link. We also have a gigabit Ethernet link connected to our router. And the cost there is 4. There's no point in running spanning tree to the router, because routers don't speak spanning tree. They understand layer 3. So we can ignore the bottom link, but the key is the first 2 links. Now let's see what we see on the other switches in our environment. Here I am on switch 1, and let's do show spanning tree. And what I see here is that you're running spanning tree, which is the IEEE version. This is, once again, open standard, meaning if you had a non-Cisco switch, we would be able to speak that to them. Root ID priority is set to 32.769. This is the MAC address of the root bridge, and our cost to get to the root bridge is 19, and we're using port 13 to connect to the root bridge. Whereas the bridge ID piece shows us our own properties as a local switch. So as S1, my priority is 32.769. As switch 1, my MAC address is this, and then all these different timers, STP timers. Another thing to note here is on S1, once again, forget about the bottom one because that's router. So we don't need to worry about spanning tree with the router. You can just ignore that. Let's just focus on the top 2. So Fast Ethernet 0/12, that's my connection to switch 2. That's a designated port, meaning I'm able to forward traffic on this link. And the cost is 19, which is once again 100 meg. Fast Ethernet 13 is a root port. That's the port I'm going to use to connect and communicate back to the root. And the port cost is 19. Looking at this diagram here, S1 makes this the root port and makes this the designated port toward S2. Well, why is that? Couple of things. Well, the guy at the top, S3, is the root bridge, right? So as you can visually see, S1 is physically plugged into S3. And this port right here, this link, is 100 meg. And 100 meg, if you remember the chart that I showed you earlier, is 19 STP cost. So that's the cost of going to S3. Now, what's the cost of S1 connecting to S3 via S2? Well, that's 19 here for this link and 19 here for this link. Well, that's 19 plus 19 equal 38. So that's a total cost of 38. So of course you're going to prefer the lowest cost because lower is better. Plus you're physically connected to it, so it makes sense. So this is one way of visually looking at and making sense of how STP operates. Another is to do a bit of a deeper dive. But before I do that, now let's go ahead and jump on the CLI of switch 2 so I can show you spanning tree there, and then I'm gonna do a deeper dive. Let's quickly look at switch 2 and see what's going on here. So show spanning tree on this switch shows me that the root ID is this MAC address. It's not us because it doesn't say this is the root bridge, right? So remember that, right? So the keyword, this is the root bridge, here in this portion verifies that us locally are the root bridge. But in this case, this switch is not the root bridge because we can clearly see that there is a MAC address and there's a cost associated with that, and it's showing us the bridge is available over port 23. And our bridge ID, another visual verification is that the MAC address here is different than the MAC address here. So this is our local MAC address, and the MAC address above here is the root bridge's MAC address. So that's another visual verification that we're not the root bridge, somebody else is in the network. Now something really interesting is happening here. Once again, forget about the router, right? We don't want to look at that because that will only confuse us. Let's only look at the other two switches that are connected in this environment. Switch 2 is connected to switch 1 over fast Ethernet 12. The role here is blocking, and the cost is 19. So this link right here is actually being blocked, meaning no frames are going to be sent, no data is going to be sent, no data plane traffic at all. Only BPDUs will be received, but no traffic. User traffic will be received. Fast Ethernet 0/23, on the other hand, which is switch 2's connectivity to the root bridge. Going back to the diagram here, this is the root port, and this is in blocking state, this right here. Because remember, in STP, we must have a port that's blocked. Otherwise, we'll have a situation where frame goes out and loops around the network forever and ever and ever and brings the network down to its knees. Completely kills the CPU and memory and chews up pretty much all the capacity on all the devices, and that's a bad place to be because there's no TTL value at layer 2. So the frames never die. They'll live forever. That said, let's quickly figure out why in our topology this guy became the root bridge and this guy had a designated port allocated to it in this direction and this guy had a blocking port. Why is that? How did this happen? Well, remember, it goes back to the bridge ID, which is a combination of two things: bridge priority and the MAC address. Well, bridge priority by default is set to 32.768. That's a default value on all Cisco switches. And the MAC address is the only tiebreaker at that point. And remember, the older the switch is, and the lower the MAC address is, the more preferred, and the lowest MAC address ends up becoming the root bridge. Now, let's find out if that is the case. Now, let's go ahead and grab MAC addresses of all of these switches and do the math and figure out how they decided to do what they did. So if we were to go to our topology here And here are all the MAC addresses that I grabbed off of these switches. I did the hexadecimal math in my last video, so check that out. But I'll give you a quick walkthrough of it again. If we were to do an eyeball comparison, you can clearly see that in all of the MAC addresses in the first octet, the first two values are all zeros. Where things start to differ is the third value right here. So as you can see, switch 3 became the root bridge. So the reason it became a root bridge is because if you look at the values here, 3 is the lowest out of all these. 3, then 9, and D in hexadecimal is actually 14. That's why it's all based on the MAC address. Because once again, we only have two things to choose from, either the bridge priority or the MAC address. Because bridge priority is the same on all the Cisco switches by default, the tiebreaker comes down to the MAC addresses. That's why switch 3 was elected as a root bridge. Now let's quickly talk about spanning tree switch port states. There are 5 different switch port states. Number 1, blocking. In order to avoid loops, switch puts a port in a blocked state. Makes sense. We just looked at a blocking port a moment ago. It takes 20 seconds for STP to transition a port from blocking to listening state. The next state happens to be the listening state. Here, the port stays in this mode for 15 seconds before next step. Switch sends and receives BPDUs when it's listening. In the learning state, port stays in this mode for about 15 seconds. Switch populates the CAM table in this mode. So meaning it's learning the MAC addresses. Then the next up is forwarding state. Port starts forwarding traffic here. Another state which is not officially part of the port state, but it's definitely there, is disabled. When port is manually shut down, when you type in the shutdown command, it's considered to be disabled. And at that point, it's not participating in STP because it's been manually shut down. Now, let's add up all the timers to see how long it takes for the port to come up. So we're in blocking state for about 20 seconds, listening for 15, learning for 15 seconds. Finally, we're forwarding. If you were to add it up, 20 plus 15 is 35. 35 plus 15 is 50. Total transition time is 50 seconds, believe it or not. When you have a link failure in a spanning tree environment, it takes 50 seconds for the existing links to reconverge. What does that mean? Let me quickly visually explain this to you. If I have a switch here, and if I have a switch here, and a switch here, they're interconnected like this. If this is the root bridge, and this has a designated port, and this is blocking, right here. If this link goes down, which is the root port, if this goes down toward the root bridge on this particular switch, let's say this is switch 2, this is switch 1, and this is switch 3. If this root port goes down for whatever reason, it's going to take us 50 seconds to reconverge and reroute traffic across switch 1 to get to switch 3. Now, by today's standards, 50 seconds is bad. It's really, really bad. To fix that, there are enhancements that were made to the STP protocol. Now, keep in mind, STP has been around since 1990s, so it's been around a long time, so enhancements had to be made. Finally, I've got this real-world behavior for you when it comes to STP. So let's say you just set up a brand new network and you had some old switches and you got a bunch of new switches that you kind of put together and created this network, and you connected them up like the way you're seeing in this picture. What's going to end up happening is that through the magic of STP, the switch all the way up at the top is going to end up becoming the root bridge. Reason for that is because it has the lowest MAC address, right? All the other values are the same when it comes to the priority, root bridge priority. That's the same. The only difference is the MAC address. Well, The next step that happens is we're going to have root ports that are going to go toward the root, and then we're going to have a bunch of blocked ports and designated ports. Well, if I were to eliminate all the redundant links that were blocked, look at how suboptimal this network looks when we let STP do its thing. First of all, this switch up at the top is an access layer switch. Access layer switch should never be a root bridge, because root bridge is the one that is, remember, at the center of the universe. So all the traffic must go through the root bridge to get to the other switches. So in this environment, we're sending all the traffic to a closet switch, an access layer switch. That's a bad idea. Plus, this switch might be 20-year-old. Okay? Whereas these switches right here could be the latest Catalyst 9500 switches. Well, if that's the case, this is such a waste, because we have switches that are worth hundreds and thousands of dollars versus a switch that was bought 20 years ago that's virtually worthless at this point and is a choking point in the network. Because remember, it only has 100 meg links, whereas these guys here could have 1 gig, 10 gig. Switches these days have up to 100 gig type of connectivity. We are right on the heels of 400 gig. So that's a bad design. You do not want to let STP do its thing by default, because, like I said, it automatically picks the lowest MAC address. And if you look at how the manufacturer IDs work with MAC addresses, whenever a manufacturer starts producing switches, it starts off sequentially. So it starts off with a number, and then from there, it continues to add more values to it. So by that token, what that means is the newer switches are going to have a higher MAC address, and the older switches will have a lower MAC address. So that's a huge problem. Instead, we should manually pick these core switches, make one the root primary, and make the other the secondary root, and go from there. Now let's quickly shift our attention to PVST. It stands for per VLAN spanning tree. All new Cisco switches run PVST out of the box. It's a Cisco proprietary protocol. That is something you have to keep in mind. Only Cisco switches run PVST by default. And they utilize ISL trunking. PVST creates a spanning tree instance for each VLAN. So here, the idea is that it's per VLAN spanning tree. So instead of having a single spanning tree for all the VLANs, now we have a VLAN specific spanning tree. And what that does for us, and before I get into the functionality of it, let's kind of discuss first the layer 2 frame header architecture of PVST. So from a layer 2 standpoint, what we have here is a couple of things. So if you recall, the spanning tree, the regular spanning tree, which is called CST or common spanning tree, this whole field, if you guys recall, was called a bridge priority. There was no VLAN idea there, right? This whole field, which is 2 bytes or 16 bits, was bridge priority, and then to the right was MAC. But here, we have a bit of a different story. With PVST, we still have the bridge priority field, but we also insert in the middle a VLAN field. It's a 12 bits field, and altogether the bridge priority still happens to be from 0 through 65,535. We typically use the default value on all the switches, 32,768. And then the MAC address, which I mentioned previously, is derived from the backplane on fixed switches and from a supervisor module on the modular switches. Finally, PVST Plus is the same thing as PVST, but it's supported over 802.1q trunking. Since 802.1q trunking is the default standard in the industry these days, most likely on Cisco switches, you're going to see PVST plus being ran by default. So that is something you have to keep in mind. How does PVST work? So let's quickly talk about that. Here's an example. This switch right here, if this ends up becoming a root bridge for all traffic, what's going to end up happening is whether the traffic belongs to VLAN 38 or it belongs to VLAN 77, everything, all traffic is going to be funneled through switch A. But what we can do is to better utilize the switch at the bottom, because everything is going through switch A, switch B for the most part is going to be sitting idle, right? And that's not good because we spent money and in networking. We also want to utilize our resources efficiently. So what we do is we say, instead of using switch A as primary, as root bridge for all the VLANs, how about if we went ahead and made switch A primary for VLAN 38, and we made switch B primary for VLAN 77. This way, if host A, which happens to be on VLAN 38, wants to talk to host C on VLAN 38, the traffic will flow this direction. However, if the hosts at the bottom of the screen, host B wants to talk to host D, the traffic can flow this direction because we now have two different root bridges. So as you can see here, this allows us to create a very efficient layer 2 network. That's why PVST was designed by Cisco to create efficiency in our layer 2 LAN. Now let's talk about RSTP. What is it? Stands for Rapid Spanning Tree Protocol. It's defined in IEEE standard 802.1w. It's industry standard. Anytime you see the word IEEE, that's industry standard, meaning Cisco, non-Cisco, pretty much all networking devices support that feature. RSTP has the same underlying concepts that I've just finished covering from a regular spanning tree perspective, or the old school spanning tree perspective. However, it has fast convergence time. So that's why I have the picture of this jet, right? Anytime you hear the word rapid spanning tree, it means fast convergence time. And if you guys recall, it took us 50 seconds to converge on a regular spanning tree. Here, it's much, much faster. And we'll talk through those details. And another important element that I want to bring to your attention is that in a traditional spanning tree, when the port is blocked, we don't worry about the BPDUs. We don't listen to the BPDUs. We still receive BPDUs, but we don't store any information. So the drawback of that is if you have two switches like that, and the top guy is the root bridge, let's say switch 1 is the root bridge, and switch 2 is the non-root bridge. Let's say if this link is in blocked state or blocking state, what ends up happening is if this link goes down for some reason and we have to reconverge, we'll have to wait about 50 seconds for this port to come up. Why? Because until then, we'll keep dropping anything we're receiving here. We're not going to remember anything, and we're going to have to run the entire spanning tree. We're going to have to go through all those different port states, listening, learning, and all that, and eventually get to the point where we're forwarding traffic. Whereas with STP, the big difference is that it's proactive in nature. And what we do is the blocked ports still keep the information that it's getting from the BPDUs in its database, and it significantly accelerates the convergence. We go from 50 seconds down to either 1 to 2. Most of the new switches are capable of converging under sub-second. That is really, really amazing, significant improvement. And that's where RSTP comes in. Now, there's a difference in switch port states. Instead of 5 different states that we talked about previously when it comes to common spanning tree or the traditional spanning tree, in rapid spanning tree, we got 3 different port states instead of 5. The first one is called discarding. Here, what's happening is all incoming frames are dropped and no MAC addresses are learned by the switch. Discarding equals disabled plus blocking plus listening. So if you guys recall, these are 3 separate port states previously in the traditional spanning tree. Here, they're all combined together and are called discarding. The next is called learning. Here, it's pretty much the same as the traditional STP learning state. Here, the switch is populating its MAC address table, but the incoming frames are still being dropped. And finally, once we have learned the MAC addresses and the database has been successfully populated, we start forwarding the frames, and that's called the forwarding state. So keep this distinction in mind. Most likely they will hit you on the exam with this question. Difference between traditional STP versus rapid spanning tree. What is the difference between the switch port states? So keep this in mind. Some of the port roles when it comes to rapid spanning tree, we have what's called a root port. You guys already know at this point, all the non-root bridges have to have one root port and only one back to the root. Then we also have a designated port. It's the best root path cost to the root on a non-root bridge. After we identify the root port, we then specify a designated port. And by the way, it's also considered a forwarding port. On the root bridge, all the ports are designated ports because they're all in a forwarding state all the time. None of the ports on the root bridge ever get blocked. That's the whole point of having a root bridge. And then we have an alternate port. In STP, this is called a blocked port, but the difference in rapid spanning tree is that the alternate port remembers the blocked port as an alternate route back to the root. And finally, we have an edge port, and that's the one that connects to the end device. So if you see in the diagram here to the right, the host at the bottom of the screen would be considered that port pointing to that host or connected to that host would be considered an edge port. So let me quickly walk you through this animation. So let's say if the bottom switch is the root bridge, then what's going to end up happening is the top 2 switches, their directly connected ports are going to become root ports. One of the switches is going to have a designated port. The other one is going to be an alternate port, which used to be called a blocking port, but now it's called alternate. And the port where the end host is plugged in is called an edge port. Now let's quickly talk through some of the optional features of spanning tree. First, we're going to discuss port fast. This is a feature that allows a port to immediately start forwarding as soon as it comes online. It doesn't have to go through all the different spanning tree timers. Significantly enhances the speed. It's used in the access layer facing the end hosts, which are called downlinks, right? So all the downlinks where the hosts are plugged in, that's where we would enable port fast. There are a couple of commands I want you to take a look at, and we'll also check these commands out momentarily on the CLI. One is in a global configuration mode, the command port fast default, spanning tree port fast default. And the next command is at a sub-interface level. Under the interface, you can also specify if you want to set up the port as a port fast. Typically, a good practice is to go with the second option, where at the interface level, you define whether or not you want to enable port fast instead of globally enabling port fast on all the ports on a switch. Because what if that port is not being plugged into an end device? Instead, if it's connecting to another switch, that would cause issues. Another feature that I want to talk about is more of a security feature, kind of related to PortFast. It's called BPDU Guard. It's linked to PortFast in a sense that once you have PortFast enabled, let's say on a global level, on a switch, on all the ports, you would also want to enable BPDU Guard, because what it protects you against is if most of the ports on that switch are going to be plugged into an end host, if any of the end hosts, let's say if there is a bad actor or a hacker connected to a PC on one of the downlinks and pretends to be a switch, and they start sending BPDU messages. Remember, only switches send BPDU messages. End stations cannot, because these are STP advertisements, right? So you should never receive STP advertisements ever from a downlink. BPDUs are always exchanged on the uplink level between the switches, or trunk links. So what ends up happening is if you do end up receiving BPDU messages on a port that is facing a host, then that port will actually be put into an error disabled state, because you should never receive a BPDU from a port that is an end device facing port. And this feature should be enabled on all the switches in your environment to protect you against receiving BPDUs on ports that have PortFast enabled on them. Once again, you have the global configuration command. You can type in spanning tree PortFast BPDU Guard default, or you can do it at a sub-interface level. And you can say spanning tree BPDU Guard enable. Once again, the difference is the first command enables it globally on all the ports. The one below it will only enable it on the port that you want to have it enabled on. So let's say if you have a 24 port switch, if you specified the last command under a very specific port, let's say fast Ethernet 0/1, then that's the only port that will have BPDU Guard enabled, and no other port on that switch will have that enabled. Now let's quickly jump into a command line interface, because I want to show you a couple of things. All right, I'm on switch 1 in our topology. Let's go ahead and quickly look at show spanning tree detail. I want to show you something real quick. One quick thing I want to draw your attention to here is I'm on switch 1. And why would switch 1 choose port 12 compared to port 13 as the designated forwarding port, and then choose port 13 as the route forwarding port, right? What decision criteria did it use? So one thing I want to draw your attention to is if you see port 12, which is facing S2, our path cost to reach that destination, or the route bridge, is 19. And the designated path cost, this right here, 19, which is advertised to us by the remote neighbor, which happens to be S2 in this case, is also 19. So our path cost here is 38. Compared to the path cost that we have on port 13, which is only 19. So once again, lower cost is better. The reason it's 19 is because it's 100 megabits per second link. So if you guys remember the chart that I showed you, 38 means I have 2 links that are 100 meg each, or 2 hops to get to the route bridge. And remember, in networking, guys, less hops are always preferred over more hops, right? Because more hops mean more latency, more chances of the traffic being dropped, more chances of the delay in the network, more points of failure. So the way all the layer 2 and layer 3 technologies have been architected are to use the least hops possible to get to their destination. The next thing I want to talk about is, as you guys can see, if I do show spanning tree again on this guy, we're not the root bridge because, first of all, it should say right here that we are the root bridge. We know we're not because the MAC address here is different than the MAC address that we have here. Plus, we can tell by looking at the output here of the trunk links that one is the designated and the other is the root port. Remember, on the root bridge itself, all the ports are always forwarding and none of the ports are root ports. All the ports on the root bridge are designated ports. So that's a quick check. Now, a couple of commands we can run. Let's say if I wanted to make switch 1 the root bridge of our network. How would I do that? I'll go to Configure Terminal to go to the Global Configuration mode, and I'll type in spanning tree, VLAN, and then whatever VLAN we're using. Now, in this case, we haven't really manipulated or changed any VLANs, so we're actually using VLAN 1 on all the switches right now. And there's a couple of things I can do here. I can either say root, and I can say primary, and that's it. If I hit enter, what ends up happening is the switch will look at the priority of the root bridge and then automatically adjust that value to make it lower so that this switch, S1, will become the preferred root bridge in the environment, or will take on the role of a root bridge in the environment. Or instead of saying root primary, I can also specify a priority in the increments of 4096. So let's say if I type in 4096 and I give it a moment, I do show spanning tree. And as you can see now, it says this bridge is the root. And the MAC address here is identical to the MAC address here. That's another quick visual check to see if you're the root bridge or not. And as you can see now, all the ports are in designated role. There are no root ports anymore on this switch because we are now the root. I also want to show you another really interesting command, show spanning tree summary. I really like this command because what it does for us is it shows us what's going on our switch. So our switch is in PVST mode. So remember, we didn't manipulate the mode our switch is in right now. By default, all the Cisco switches are in PVST mode per VLAN spanning tree. And we're the root bridge right now, and we have what's called extended system ID enabled. So let me talk about that in a moment. And then there's a bunch of different features that we just finished talking about. We talked about the port fast and the BPDU guard. We didn't talk about some of the other features. We can cover those in the CCNP course. Right now, they're beyond the scope of the CCNA exam. And if you see here, we only have one VLAN configured on this switch, and all the ports are in forwarding state right now, and STP is active. And these are the different port states we talked about: blocking, listening, learning, forwarding. Now let's talk about the extended system ID. So if I were to type in show spanning tree again, I know some of you guys may have noticed that I kind of skipped over the priority field. When I typed in 4096, why did it switch to 4097? It should have been 4096. Well, the reason it's 4097 is because if you guys recall, the new BPDU frame header at layer 2 for the PVST has the following fields. It's got the bridge priority, plus VLAN ID, plus MAC. So bridge priority, because I manually typed it in, remember 4096, plus what's our VLAN ID? I just showed you guys that we only have one VLAN on the switch, and that's VLAN 1. Well, 4096 plus 1 equals what? 4097, right? That's what we have right here. And we also have the MAC address right below it. So That's how it's displayed. And that these are the advertisements. Remember, BPDU is an STP advertisement. So as switches are talking to each other, they're sharing these values with each other. And they're learning about the network. And that's how they identify who the root bridge is versus the non-root bridge and all the rest of the jazz in terms of how different ports are going to come up and things of that nature. All right, couple of additional things we can do. So let me go back to configure terminal, go to the global configuration mode and type in spanning tree mode rapid per VLAN spanning tree. As soon as I do that, this will enable rapid spanning tree on the switch, but it's rapid per VLAN spanning tree. So as we talked about the fact that we have different VLANs, you want to specify different root bridges for different VLANs for load balancing purposes and all that. This command enables those fast convergence timers. So instead of having to wait 50 seconds, as soon as we enable rapid PVST, we now will experience less than a second or maybe 2 seconds at the most to reconverge when our root port goes down. A couple of other commands that are not related to spanning tree but important to understand on a switch are show interfaces status. So on a switch, that's an important command because you can see a couple of different things. You can see what VLAN a port is assigned to, layer 2 status, whether or not it's up or down. You can see the duplex. You can see the speed, and then you can see the type of media. 100 base TX is copper media. Anytime you see the word TX at the end, that's a copper media. And what we see on this switch, we see fast Ethernet 12 and 13 being connected, which means these two ports are up. And we also see gigabit 01 connected. We also see this up. All the other ports are physically down. We can also type in the command show IP interface brief. Two important things you can see here. So for the ports that are up, you can see if they're up. So the first up refers to the status, the physical condition of the port, the electrical signals and the physical function, whether or not physical cable is plugged in. The second up refers to layer 2, whether or not the layer 2 connection is up end to end. So we should always see up. We should never see down or up down. Those are two bad conditions. And when you see something administratively down, that means we have manually shut down that particular port, which in this case is VLAN 1, which is a virtual port. It's not a physical port. It's a port that's located on the switch, but it only exists in a virtual realm, not in a physical realm. Now let's quickly jump into ether channels. Well, what is an ether channel? It's a link aggregation mechanism. Meaning, if we take a couple of links and we bundle them together, we call that an ether channel. And why is that? Why do we need an ether channel? Well, in a typical spanning tree network, if you think about it, guys, spanning tree is very inefficient. If there are two switches that are connected with 4 links in between, what's going to end up happening is spanning tree is going to block how many links to avoid loops? It's going to block 3 links. It's only going to leave 1 link up while the other 3 links are going to be blocked. And the total bandwidth that we'll use is going to be 100 megabits per second, assuming these are all fast Ethernet interfaces. But in reality, we have the ability, we have 4 100 meg links. We have 400 meg worth of capacity available to us, but it's a shame that STP is only allowing us to use 100 meg. So with ether channel, what we end up doing is that we kind of bundle all the links together. We aggregate them together, and we're able to utilize full throughput capacity of that link. And even though physically there's still 4 separate ports, but through a configuration, we can make them logically appear as if it's one big pipe or one big link with a lot more capacity. And it's very, very powerful. In real world, ether channels are utilized quite heavily in the data center realm. Also at the server farm level, very heavily utilized. All right, now let's quickly talk about the different ether channel negotiation protocols. When it comes to ether channel, there are two protocols. First, PAgP stands for Port Aggregation Protocol. It's Cisco proprietary. Port modes that are available in PAgP are auto. That's a passive mode. If both sides are set to auto, the link will never become an ether channel. Desirable. This is an active mode. Link actively tries to become an ether channel. And the third is on. This mode forces the link to become ether channel and kills auto negotiation. The next one up is called LACP. This is the industry standard. Stands for Link Aggregation Control Protocol. It's defined in IEEE standard 802.3 AD. Port modes in this are passive, active, and on. As you can see, they correspond exactly to the PAgP. Now, PAgP is a Cisco proprietary protocol. You might be asking a question: why do we always have these competing standards with Cisco, like CDP and then LLDP, PAgP and LACP? Well, what ends up happening is Cisco is a thought leader in the industry, right? So they're the industry leaders in networking. They're the ones that typically come up with an idea first. And then a couple of years later, the industry catches up and the other companies express interest in deploying that piece of technology on their networking equipment. So then they come up with an open industry standard. And that's why you see all these competing standards against Cisco to be able to allow non-Cisco devices to work in a friendly manner with Cisco devices. Basically, the whole idea is to create this ecosystem in the industry so the users are not locked down to certain vendors. So it fosters a better business environment for different networking vendors. That's the whole idea. Another important thing I want you guys to keep in mind is, let's say if you have a server, this right here is a web server, and you have two NIC cards inside of the server. Both are 10 gigabit Ethernet cards. And then you have a switch that has these two 10 gig links plugged into two different 10 gig ports on the switch. Well, if you didn't use EtherChannel, if you let Spanning Tree do its thing, it's going to kill one of the links, right? It's going to block, and which means we can only utilize 10 gig worth of capacity. But with the magic of EtherChannel, you can combine these two. By the way, this right here is a symbol of EtherChannel. So wherever you see in network diagrams a sort of like a circle drawn over the links between two devices, this right here is a symbol of EtherChannel. So when we enable EtherChannel on our switch, and by the way, on the server, we would also have to enable an EtherChannel using LACP. Remember, server, depending on the server, you're going to have to enable LACP, Link Aggregation Control Protocol. So assuming you have LACP enabled on the server itself and LACP is enabled on the switch, and they're in the appropriate groups and all that, and we'll talk about the configuration in a moment, all of a sudden, we can now utilize a full 20 gig worth of capacity between that switch and the server. So that's a very beautiful thing. And you can imagine why it's such a powerful technology when it comes to data center networking. There are two different types of ether channels. We have layer 2 ether channels. So here in this example, we have a couple of links between two different switches. And as we can see, there's an ether channel configured. And here's how we would actually configure. Here are the commands we type in. Under the global configuration mode, we go to those interfaces that we want to participate in an ether channel. Then we go ahead and under the interface configuration mode, we specify the channel group. And the channel group should match on both ends. It's a must thing. If it doesn't match, ether channel will not come up. So let's dive right into the CLI. All right, here I am on a switch on the left-hand side. Let me go ahead and do show spanning tree real quick. And I can see that, first of all, I'm not the root bridge because it doesn't say that here. Plus it shows that there's a cost of 4 to get to the root bridge. So whenever you see a cost associated as well, that means we're not the root. Plus the fact that the MAC address is different than us. So all these things are an indicator that we're not the root. Plus you can see the roles here, root and alternate blocking. So our Fast Ethernet 21 is the root port, and the other one became the alternate blocking port. That said, we want to configure EtherChannel, meaning we want to combine these two links together so we can fully utilize the capacity. These are 2 gigabit Ethernet. So there's a difference in the diagram here. I'm showing Fast Ethernet, but on the device that I'm using, I actually have gigabit Ethernet links, so I apologize for the confusion here, but I'll make sure that I use the gigabit Ethernet interfaces in my configuration when I am configuring these devices. But the key here is I want to make sure that you guys understand the concepts. Concepts are important, more important than necessarily just understanding the commands. So let's go ahead and jump right in. So we'll go to configure terminal mode. Well, another thing you want to think about is we need to do show interface trunk. We need to look at whether or not we have a trunk link. Now, interestingly enough, though, on some of the switch platforms, switches do not form trunk automatically unless you specify whether or not they are on a particular trunk link. Because if you guys remember in the last video, I talked about the fact that you have different type of modes when it comes to trunking. And the passive mode does not allow either of the switches to come up. So if both sides of the switch are in passive mode, which some of the switches are by default, then they do not form a trunk link between them. So to fix that, what I'm going to do is I'm going to take both of these ports, go under these 2 interfaces. So also get used to the interface range command. That's a cool command. Instead of having to separately go under each interface, you can just use a range command. When you use a comma in between, that means this port and this port. But if you use a dash in between, then that means this port through this port. So there's a distinction, but it's an important distinction. Here we only want these 2 ports to be trunk links. So what I'm going to do is I'm going to type in switch port mode trunk. And switch port trunk encapsulation.1q. By typing in these 2 commands, if I now look at show interface trunk, I should be able to see that I actually now have 2 trunk links going to switch 2. And what I want to do next is that under these 2 interfaces, I now want to set up an ether channel. Okay, so let's go ahead and set up an ether channel. So I'll say channel group 13. We'll just match what we have on the screen here, so there's no confusion. And it says specify the mode. We can say active, auto, desirable, on, passive. Remember, there are 2 different protocols, PAgP and LACP. We talked about both. They're all specified here, right? What I want to do is I don't want to use the LACP or PAgP per se. I just want to make sure that this becomes an ether channel. So I will go ahead and use the on mode. I prefer this personally, because I think it makes it a lot easier to do it this way. And you don't leave things up for negotiation. Because this way, if you set up a passive mode on both sides, the ether channel will never come up. Similar to like a trunk link, when you have passive on both sides, trunk will never come up. So I like to be in control. As a network engineer, you always want to be in control. You don't want to be at the mercy of devices. So let's go ahead and also look at the other switch. On switch 2, let's go ahead and do the same thing we did on switch 1, we're going to go under interface, range, and we'll specify gigabit 1/021 and gigabit 1/023. We'll go ahead and first type in switch port mode trunk. And it says command is rejected because you got to specify the trunk mode. So let's do switch port trunk encapsulation. Let's go ahead and define the encapsulation first. And then type in the command switch port mode trunk. And let's verify that we have our trunk links come up. And indeed they did. Let's also do quickly show CDP neighbor to see who the neighbor is that we are connected with. So it shows us that we are connected with switch 1 over 2 physical ports and then 1 port channel. And we haven't specified our port channel yet, so the port channel is not up yet. What we need to do right now, though, is go ahead and configure our port channel. So while we're still under the interface range mode, we'll type in channel group, and we'll specify our group. We'll say 13 to match what we have on the other side, and we'll say mode on. Now, as I mentioned earlier, this ensures that the port channel comes up on both sides. We have a couple of different commands we can run to verify our port channel. One is show interface trunk. Now, as you can see, before we were showing physical ports, but those physical ports have now been displaced with a single port channel. So that's really cool. There's another really cool command called show EtherChannel summary. This quickly shows us the summary of our port channel. So what we would want to see here is the number of the port channel kind of should match the other side, right? And the way we can tell whether or not our port channel is up is by looking at S and U that we see here. And what this S and U corresponds to is S means, let's match it here in the flags. S means it's a layer 2 ether channel, and U means it's in use, meaning it's up. So it's layer 2, that's the S component of it. And the U specifies that it's in use, meaning it's up. That's what this right here corresponds to. So that's pretty cool. And then it shows the physical ports that are part of this. So Gigabit Ethernet 1021 and Gigabit Ethernet 1023. And the P flag here at the end of these ports represents that they're part of that this port channel 13. We can also run a command show EtherChannel port channel. This shows us the port channels that are currently in use and the port state and the type of protocol you're running, if it's PAgP or LACP, and then all the different physical ports that are part of this ether channel and how long has this ether channel been up. And another cool thing you'll notice is when you type in show interface status now, you'll actually show a port channel come up. It says connected, it's up. And it doesn't show the type because remember, this is not physical, it's virtual. Something to keep in mind. So as I mentioned earlier, there are 2 different types of ether channels. We just finished discussing layer 2. Now let's discuss layer 3 ether channel. Now I know this is still a layer 2 section, but bear with me here because there are some concepts that kind of overlap. I want to touch base on some very basic layer 3 concepts here that are still very much attached to layer 2, but no worries at all because in the next section, section 3 of this course, I'm going to go super deep into layer 3. So all of your concepts on layer 3 will be completely clarified once you go through those sections, and you're more than welcome to come back to these videos again and quickly glance over some of the layer 3 things that we're talking about right now that may not register with you at the moment, but once you have viewed all the videos in section 3, which is the next section, and then you come back to this, it's going to be a lot easier and simpler for you to understand. But let's quickly talk about it. So there might be scenarios where we would want to define layer 3 port channels instead of having a layer 2 port channel, depending on our design. And we have that flexibility available to us. Here are the commands that we would want to type in when we have a scenario like that. So let's jump right into the CLI again. So here I am on switch 1. Let's quickly take a look at our port channel. So let's quickly take a look at show run on the switch to see the port channel configuration. So as you can see, it's a layer 2 port channel right now. There's no layer 3 configuration on it. So what you would want to do is go under global config mode, configure terminal, go under the interface port channel 13 and say no switch port. This would make it a layer 3 interface. The minute we say no switch port, that means we want to enable layer 3 functionality on that port. It's no longer a regular switch port. It almost starts behaving like a router port, okay? Because we can now specify layer 3 IP addressing on it. So I'm going to go ahead and type in IP address 172.30.1. Let's take a look at our diagram here. On the left, I've got ones, and we have /24, so that's 255.255.255.0. I'm going to hit enter, and I'm done here. Next thing I want to do is I also want to go under the interfaces. I'm going to type in interface range command and go under gigabit 1021 and gigabit 1023 and say channel group 13 mode on. As a matter of fact, we should say no switch port here first. As you can see, we are running into a bit of a catch-22 situation here. We keep getting these different error messages regardless of the command we are typing in here saying you can either be a layer 2 or a layer 3 ether channel. So I think to do this right, what we would have to do is we would have to blow up all the configuration that we have done so far on these physical interfaces and redo this. So to do that, there is a very interesting command called default interface, and then you can go gigabit 1021, and then you can do default interface gigabit 1023 and hit enter. And what this command does is that it blows up all the config that you had done previously. It brings the port to its default config. And now we're going to go back under the interface range command again. And the first thing we're going to do is we're going to say no switch port. So it knows right off the bat that this is going to be a layer 3 port. And we then want to specify the fact that we want these ports to be part of a channel group. Now at this point, if I were to do show interface status, as you guys can see now, the physical ports say they are routed ports. They're no longer part of a VLAN. You see this column right here shows us VLANs, right? But now you see these are routed ports. They're no longer participating in switching. Spanning tree is off and all that. We're now running routing. And the port channel also says it's routed. Let's verify a couple of additional elements. So let's do show EtherChannel summary here. And we're now RU instead of an SU. S was layer 2. now it says R. It says layer 3U, meaning we are layer 3 and we are up and operational. If I were to do show EtherChannel port channel, I still see the same information that I saw before. But we are not done yet, because remember, we need to do the same thing on the other side. So now I'm on switch 2. Let's quickly go to global config mode, go under interface, range. Well, first of all, let's blow up all the config, right? So if you guys remember, we ran into an issue, so we'll blow up those configs. So default interface gigabit 1021, and then we'll do default interface gigabit Ethernet 0/23. And then we're going to do interface range gigabit 1021 dash gigabit 01 or 1023, and we'll say no switch port, and we'll say channel group 13 mode on, and we should also go to the interface port channel now and do no switch port there first. I think that's why this command was rejected. And then specify IP address there. So 172.30.10.3, 255.255.255.0, because it's a /24. And we should go on back under the interface range command again on the physical interfaces and type in channel group 13 mode on. And once again, we're going to run a couple of commands here. Show interface status. This shows us that we are now routing on the physical ports. And if you were to look at the port channel, that's also routed. And now do further verification via show EtherChannel summary command. It says it's RU. So now it's routing. And from here, we should actually be able to ping the other guy. So as you can see, we're able to ping now. So we have layer 3 connectivity from switch 2 to switch 1 over this Ether channel that's now giving us a combined of 2 gig worth of capacity. Because these are gigabit Ethernet links that we're using, right? So 1 gig plus 1 gig equals 2 gig. So that's really cool. Why do we need intra-VLAN routing? So if you guys remember, why do we create VLANs to begin with? Well, we want to reduce the scope of the broadcast domains, right? You want to isolate subnets. By default, stuff in one VLAN cannot talk to another VLAN. We know that. Well, if that is the case, then how do we allow 2 different devices that are part of 2 different VLANs to talk to each other? Well, we have to introduce a layer 3 device in the middle. That's what's called inter-VLAN routing. There are multiple ways of accomplishing this task, though. 3 particular elements I want to bring to your attention. Option A is where we have physically dedicated links between our switch and router for each VLAN. So each VLAN is a separate interface. Now, it's not a great design in a sense that you're burning up and using way too many ports on your switches and on your routers. And in a typical environment, in a corporate environment, you'll see dozens of VLANs, if not hundreds. You'll see dozens of VLANs configured. So this could get ugly pretty quickly. So typically in real world, you won't see this being utilized much unless you have a very cornered case scenario where you're forced to use something like this. You're not going to see this. What you see in real world utilized mostly is option C. But before I get to option C, let me quickly touch base on option B, because this is also very heavily utilized in the traditional networking, and that is a single physical link between the switch and a router, and we actually make this a trunk link. Now I know so far we have discussed that a trunk link is a link that's between two switches. Here we have a router on one side and a switch on the other side. What are we talking about? Well, what we do here in this instance is we specify different VLANs that are allowed across this link, and we have to do some special configuration on the router, which is called router on a stick configuration, to allow for those VLANs to be processed separately on this router. And we'll talk through those details momentarily. But what we mostly see in the real world today is if you have a multi-layer switch, which are most of the newer switches are multi-layer switches, we actually have SVIs configured, which are called SVIs, or Switch Virtual Interface configured. And the inter VLAN routing happens right on that switch. The traffic doesn't have to leave the switch and go through a different device. It all happens here. It's all about speed, efficiency, and low latency. That's the beauty of the multi-layer switch. And that's why most of the real-world environments that you'll see today have option C configured. Now let's quickly talk through the router on a stick scenario. So what is it? So like I said, it's a legacy type of thing. If you're stuck with a layer 2 switch, then this is the only way to do it, right? But there's a couple of drawbacks. Here we have a single point of failure. As you can see in the design here, this is a single point of failure. If this goes down, that's it, we're toast. Introduces latency and delay. So if this thing is choked, if there's too much traffic going across it, packets will get delayed. Buffering becomes a challenging thing. This becomes a bottleneck. So like I said, this is more of a legacy type concept, but it's still there. And in some networks, you have to use it to be able to get the job done. With that said, let's go ahead and quickly get this piece configured. So right now I'm connected to the switch that you're seeing in your diagram here down below. I'm going to quickly take a look at show VLAN brief. Well, it seems like we do not have VLAN specified. So I'm going to put these VLANs or these ports in the appropriate VLANs as we see here in this diagram. So I'm going to go ahead and go to global config mode and put in, the interfaces are different than what you're seeing there. The interfaces for me are interface gigabit 101 connects to VLAN 50. So I'm going to go ahead and say switch port mode access. And the next thing I want to say is switch port access VLAN 50. So this right here creates a VLAN 50 and then puts this port under that VLAN. And I'm going to repeat the same commands for the other ports. So we're going to go to gigabit 102, type in switch port mode access, and then we'll type in switch port access VLAN 60. And finally, we'll say switch interface gigabit Ethernet 103, switch port mode access, switch port access VLAN 70 here. And if you go all the way back and type in show VLAN brief, we can now see that these ports have been allocated to the specific VLANs. So now what we'll see is that these hosts are not going to be able to ping each other because they are in completely separate VLANs. So right now I'm on a host on VLAN 50. Let's quickly take a look at ipconfig. And as you can see, I am on VLAN 50. This is my IP address. My IP address is 172.20.50.200. If I wanted to go ahead and ping the host in VLAN 60, which is 172.20.60.200, you guys will see that the traffic is not going to go through and my pings will fail. And the reason for that is we don't allow VLANs to talk to each other. That's the whole idea of creating separate broadcast domains. So let me go ahead and set up our trunk link and then show you what commands you need to type in on the router for you to allow this to happen. So I'm on the switch here. I'm going to go ahead and set up a .1Q trunk link. Let's first of all look at our CDP neighbor and see what port we're using to connect to R1. So this is our port. Let's go to global config again. Type in interface gigabit 104, gigabit 104. Once we are under this interface, we go ahead and say switch port trunk encapsulation.1Q and switch port mode trunk. And this would force this link to become a trunk link. So now we're trunking with the router. So if you were to do show interface trunk, this link is now a trunk link that is facing the router. Now let's quickly jump on the router and finish the rest of the config. So now I'm on router 1. Let's quickly go ahead and look at show CDP neighbor and see what port we're using to connect to S1. It seems like we're using gigabit Ethernet 000. What we have to do now is set up 3 sub interfaces on our router to allow these different VLANs to be processed over that trunk link that we just created. So what that means is we go ahead and type in interface gigabit 000 and we type in .50 for VLAN 50, and we type in encapsulation .1Q 50. And we also specify the IP address of 172.20.50.1. So that becomes our gateway. That's that. Next thing we do is we now specify the other .1Q trunk, which is 60. So we create another subinterface, gigabit Ethernet 000.60. These are all virtual interfaces that we're creating. Now we want to type in encapsulation.1Q 60. And here we specify the IP address 172.20.60.1 because that's our gateway IP here on this router. And finally, what we want to type in is gigabit Ethernet 000.70. And you want to say encap.1Q70. And you want to say IP address 172.20.70.1. And 255.255.255.0, which is /24. And now if you were to look at show IP interface brief on this router, what we're going to see is that we have these sub interfaces created. And these sub interfaces have IP addresses assigned to them. And if things are set up correctly, from the router at least, we should be able to ping the hosts in each of these VLANs. So each host, remember, has an IP address of 200. So let's see if we can actually make that happen. So as you can see, we were able to do that on VLAN 50. Let's verify VLAN 60. We were able to do that on VLAN 60. And now let's go ahead and do that on VLAN 70. And as you can see, at least from R1 perspective, all the hosts are reachable. Now let's go ahead and check out the situation on the hosts. So as you guys remember earlier, our ping failed to host in VLAN 60. Let's try it again. And as you guys can see, we're now able to successfully reach that host. Let's also verify the host in VLAN 70. See if we can actually reach that from the host in VLAN 50. So 172.20.70.200. And we're able to hit all of the hosts in our environment at this point. So this is how you go ahead and set up router on a stick configuration. And the final thing I want to talk about is SVI, which stands for Switched Virtual Interface. It's a logical interface or a virtual interface on a switch with layer 3 capabilities. So like I said earlier, We have different options. This is the most preferred option that you'll see in most of the environments today. And what we'll do is we'll go ahead and get this configured now on our switch. And one last thing that I want to draw your attention to is, as you can see all the way to the bottom of the screen, is that you have to enable on your switch IP routing, because switches do not do routing by default. So you have to enable IP routing by typing in command IP routing in a global configuration mode to allow the switch to act as a router. At that point, you might as well call it a swouter, because it's a switch and a router, right? But let's go ahead and get this quickly configured. So I'm on the switch right now, and let's look at show VLAN brief. As we can see, all the VLANs are there. If I were to do show interface, show IP interface brief, you guys can see I have no IPs configured besides just the port channel that we had configured earlier. But that was for a different purpose. Forget about the port channel at this point. Let's just focus on the SVIPs. And here the idea is that we've got different hosts in different VLANs, and we want to allow them to talk to each other without introducing a separate layer 3 device. We want to do that right on our switch. So the way we do that is we go to global configuration mode, and we go under interface VLAN 50, for example. We go under each interface, VLAN interface, and we specify the IP address of the gateway. So 172.20.50.1/24. And the next thing we will do is do interface VLAN 60, do the same thing, but change the IP to 60, of course. And then interface VLAN 70, type in IP address on 172.20.70.1, 255.255.255.0. And when we do that, let's go ahead and double check show IP interface brief now. What you'll see is that we've got a bunch of interface VLANs. And remember, we have to enable IP routing, otherwise it's not going to work. So we'll have to go to global config and type in IP routing. And now we should be able to, from this switch, ping these different hosts. So if you guys recall, our host IPs are in the last octet. Instead of 1, they're 200. So I'm able to hit the one in VLAN 50. How about VLAN 60? We can reach the one in VLAN 60. And then how about the host in VLAN 70? We can also reach that guy as well. And the hosts are also going to be able to reach each other again, just like we saw in an example a moment ago. So at this point, we have full-blown end-to-end connectivity. I'm not going to get into the IP details, IP routing table details, because that's going to only confuse you. I will save that for the next section. But here, I just wanted to let you know how you can allow different devices to talk to each other in different VLANs conceptually. Welcome to CCNA 200-301 course. Today, we're going to discuss Section 2, Part 3. LAN, wired, and wireless. Today's session is all about wireless technology. We're going to do a deep dive. Here are the topics I plan on covering today. First, wireless LAN overview. Second, we'll look at different topologies. Third, we'll look at different standards and channels. Fourth, we'll look at different architectures. Fifth, we'll look at different deployment models. And finally, I'll wrap it up with wireless LAN security. Let's go. Wireless LAN overview. Wireless lives on layer 1 and 2 of the OSI model. In wireless LAN, we have radio frequencies that are radiated into the air from antennas that create radio waves. One of the things about the wireless LAN is that it behaves like a hub. And in a hub, if you guys recall, we have what's called a shared signal, meaning everybody that's connected into the hub, they're all sharing the same piece of wire, if you will. And the communication happens to be half duplex when it comes to the hub, meaning only one device can send data and it can only send or receive. It cannot both send and receive at the same time. It can only transmit in one direction. Either it's sending something or it's receiving something. That's half duplex. So the pictures at the bottom of the screen are showing us to the left of how a wired Ethernet hub looks like. And to the right, we see how the wireless access point operates. It's the same idea. The only difference is you're changing the medium. Instead of a wired connectivity, we're now on the wireless radio frequency. Wireless technology uses CSMA-CA, which is Carrier Sense Multiple Access Collision Avoidance. And what that means is only one device transmits at any given point in time, and other devices use random back-off timers and have to wait their turn before they're able to transmit data. And each frame must be acknowledged by the access point before the next one is sent. And if the acknowledgement is not received, what ends up happening is we retransmit data. That's why on the wireless network, the actual throughput that we end up experiencing is a lot less than what's advertised by the access point manufacturer. And here are the two biggest challenges of the wireless technology. First, things like interference. So if your access point is behind a wall, for example, there's an obvious interference there. If there's a metal, there might be another type of interference there. Even things like moisture and dust in the air, believe it or not, could also potentially cause interference, and we'll discuss more details momentarily. And the second big Achilles heel of a wireless LAN network is security. If you think about it, guys, anybody who happens to be within the range of the wireless access point can communicate with each other. That includes everybody, good guys and the bad guys. And a lot of the bad guys actually exploit this because shared airspace is no different than you communicating in open public. Let's say you go to a coffee shop and you have a phone conversation and it's supposed to be a private conversation. Well, if you're speaking in a public space like a coffee shop, other people can listen to you. Similarly, on a wireless network that is publicly available to everybody, as you can imagine, everybody who's connected to that wireless network has the ability to eavesdrop and listen into anybody else's conversation. So that's a pretty scary thought. Security has come a long way since wireless was introduced back in 1999. Today, we're looking at really high levels of security. But one thing I want you to keep in mind is it has to be implemented properly for you to take advantage of it. Some additional basic terminology. SSID in the wireless network stands for Service Set Identifier. That's the name we connect to. So for example, if you fire up your wireless card on your laptop or your phone or your iPad for the first time, I'm sure you've noticed that you'll see a collection of different wireless devices that you can connect to. And then you'll find the one, for example, that happens to be your home access point. You'll pick that SSID, whatever you called it, that assures me that I'm connected to my own personal access point and not somebody else's access point. So this is how the wireless networks are differentiated. The service set piece here means group of wireless devices. One thing you need to keep in mind when it comes to SSID, both the receiver and the sender must have the same SSID for them to be able to communicate with each other. And there's another term that's used kind of behind the scenes is BSSID, or Basic Service Set Identifier. That essentially is a MAC address of the access point. Multiple access points can have the same SSID, but each access point has a unique BSSID. So what that means is, like I said, SSID is a logical identifier. So I can have an access point where I'm advertising different SSIDs. So on 2.4 gigahertz, and we'll talk about the different bands in a moment, but on 2.4 gigahertz, I might have one SSID. On 5 gigahertz, I may have a different SSID. However, both of those SSIDs will have a single BSSID because BSSID is a MAC address. And there are 3 different basic types of wireless sets, and there are 2 different modes. First one is called IBSS, or Independent Basic Service Set. Here's how it looks like. So in this scenario, we have direct communication between clients. There's nothing in the middle. There's no access point or wireless router or whatever have you. What you have here is a bunch of clients, laptops, PCs, whatever, or wireless devices talking directly to each other. That's considered ad hoc mode. Then there are 2 additional service sets. There's basic service set. It's considered infrastructure mode. And in this mode, all wireless clients form a membership with the access point. So as you can see, all these laptops here are communicating with the access point and they form a membership. This membership is called association. So essentially, a client associates with the access point. Finally, there is ESS, or Extended Service Set. It's also considered infrastructure mode, similar to BSS. The only difference here is when you combine multiple basic service sets together via a wired LAN infrastructure, that's what makes up an ESS. And wireless clients associated with multiple APs using the same SSID. And ESS facilitates transparent roaming. So let's unpack this ESS a little bit. So like I said, multiple BSSs connected via a wired LAN infrastructure. So as you can see, there are 2 access points that are connected to a single switch here. Wireless clients are all using the same SSID as shown here. Both access points are advertising the same SSID. And this is what facilitates transparent roaming. So the roaming component, we'll talk more about it momentarily, is when this laptop, let's say A, moves into the territory of this access point to the right. When it does, we want this to be very seamless. We don't want the connections to drop because, as you can imagine, this is year 2021. Most of the people are on Zoom calls and WebEx and all that, and they might be communicating with somebody in real time. We do not want that call to be dropped or that WebEx session to be timed out. So we set up this transparent roaming where the user just walks around. Here you are only seeing 2 access points, but in a real world environment, in a large enterprise, you may have a ton of access points on a particular floor, for example. And as a user, as you walk around the floor, you don't even notice a blip. But in the background, you're experiencing transparent roaming that is facilitated by ESS, or Extended Service Set. Now let's look at a couple of design basics in real world when it comes to wireless LAN. So a cell is an area range covered by an access point. And one thing that I want to explain before I move further here is very quickly how a wireless client is able to connect to the access point. So the way it works is, first step is when the Wi-Fi client comes online, so let's say this guy A comes, you enable the wireless card, it issues a probe and sends it to the access point. The access point responds back with what's called a beacon, and the client associates with the chosen SSID. So at that point, let's say the SSID here is NOJ. So when this laptop connects to this wireless SSID called NOJ, initially it sent a probe. In response, it received a beacon back. Then it associated itself with the SSID. The last step in the process is that the access point adds this client's MAC address in association table. So this is how the access point is able to keep track of the different devices that are connected to it. Now back to the design. So as I said, cell is an area or range covered by an access point. And best location for an access point can be chosen by performing a site survey. So if you have no experience working with wireless networks before, what we do in real world, in a corporate or enterprise type environment, if you want to deploy the access points in the correct fashion, what you would do is you would perform a site survey. It's an investigation process in which an access point is placed at its desired location and the client moves around. And as the client is moving, the signal strength is measured in real time. There are some special purpose devices too, but the cheapest method is to actually just place an access point where you would like it to be placed, and then you take your client, could be your laptop or iPad or whatever, and then you start moving around and see if you're getting the best possible coverage. As you can see at the bottom of your screen here, this guy Z is outside the range of this access point. So if the wireless signals are not getting to this Z guy, it's not going to be able to connect. So we would want to find the most optimal place for the access point. The clients outside the cell coverage, at the risk of stating the obvious, are unable to associate with the access point, right? Because they're not getting the signal. A couple of other elements I want you to keep in mind. In real world, clients roam from one cell to another. So in order to provide coverage, service areas should have 15% overlap. So let me quickly explain. So as you can see, these are all different access points, right? So this is an access point, this is an access point here, so on and so forth. And we got a client A at the bottom here. As this client is moving around or roaming, when we place multiple access points in our environment like this, we want to make sure that there's at least 10 to 15% overlap of these signals to allow for transparent roaming. Because if you can imagine, if there's no overlap, then there might be a point where as this client at the bottom is moving around, as they move from one cell to the next, there might be a dead spot or a dead zone. To avoid the dead zone, we need to have this overlap. If repeaters are being used to provide extended coverage, service areas should have 50% overlap. We'll talk about repeaters in a moment, but if you're using repeaters, then the overlap should be more because repeater repeats the signal. In order to provide extended coverage as shown below, the adjacent APs cannot use the same frequencies or channels. Once again, we'll talk about frequencies and channels momentarily, but you cannot have APs that are right next to each other or adjacent to each other and be in the same frequency range, because those frequencies are going to start canceling each other out. They're going to create noise and the signal is going to get lost. And you might have certain times when the signal just gets completely scrambled and collisions occur. That's the whole idea with the collision avoidance, right? We want to avoid collisions. And once again, the act of moving between APs is called roaming. Now let's focus on wireless LAN topologies. First topology I want to discuss is repeater. To extend wireless range or cell area, what we do is we add another access point. So here in this diagram here, typically an access point is connected to a LAN switch. And one thing I want you guys to keep in mind is the primary purpose in life for an access point is to provide connectivity between the wired Ethernet and a wireless Ethernet environment. So here, if you guys remember, 802.3 is the Ethernet, right? So that's a wired connection here. And this wireless right here between the access point and the laptop is 802.11. And we'll discuss more details momentarily. But what ends up happening is as this laptop wants to go out to the internet, for example, the wireless signal, which is encapsulated in 802.11, gets decapsulated by the access point. And then the access point encapsulates the same message into 802.3 message and sends it across the LAN out to the internet, for example. And then the same thing happens in reverse, the encapsulation and decapsulation, as the data comes back from the wired LAN infrastructure back into the wireless environment. That is something I want you guys to keep in mind. Now back to the repeater. What happens in the repeater scenario is we have an access point already, but then we have another client, let's say this laptop 1 at the bottom of the screen, which is outside the range of our primary access point. And let's just say for argument's sake that we do not have the ability to provide a wired connection into this laptop because it's not feasible. Either financially or physically, it's just not possible because it's out of reach and we don't have an infrastructure to support that. So what we would do in that scenario is we would add a repeater. And repeater is essentially a lightweight version of an access point. As a matter of fact, you'll find some access points on the market that allow you to change the functionality to a repeater. So you can, when you log into the GUI of that access point, you can just select the option that says, I don't want to use it as an access point. I want to use it as a repeater. And then when you do that, then it no longer acts as an access point. It takes signals from an access point and then repeats those signals for the clients to connect into. Now, it looks great on paper, but the reality is that when you repeat wireless signals, the quality degrades. And once again, the whole idea here is to increase the signal strength because the signal is dying, and at a certain spot, you might have a dead spot. So instead of having that dead spot through repeater, you can enlarge that area. But the drawback is that when you do that, it can significantly reduce the throughput of your wireless network because you're now repeating the same signals. And there's also a lot of interference that could potentially happen between the repeater and the access point as well, especially if they're on the same channel. So something to keep in mind. Not an ideal scenario, but something you can do. The next topology I want to talk about is work group bridge. To bridge the wired and wireless network together, we have this work group bridge scenario. And you can think of work group bridge as an external wireless card for a legacy wired-only device. So here's what I mean by that. So you got this access point that's connected to the LAN infrastructure, but then you have this legacy client at the bottom. And this could be a legacy medical device, for example, right? And let's say that medical device only comes with an RJ45 connector at the back of it. It doesn't have any wireless capabilities, zero wireless capabilities. Well, how are you going to connect to the wireless environment? And let's say for some reason you can't bring a wired connectivity into that legacy client. And what if that legacy client has to move around? For example, if it happens to be on a cart that gets rolled from one room to another room in a hospital, for example. Well, you cannot have an Ethernet cable dangling off of it, right? So what you would do then is you would have this device, which is a special purpose device called workgroup bridge. It has one leg in the wired world and it has another leg into the wireless world. And it bridges the two together and allows for this legacy Ethernet only, wired only device to be able to connect to the wireless network. And like I said, it's fairly common in a hospital type scenario, also in some legacy environments where you do not have clients with wireless capabilities. The next up is outdoor bridge, point to point and point to multi-point. So you could also have outdoor bridges. You could have, for example, two buildings that need to be able to connect to each other using special purpose antennas. And there are two different types of outdoor topologies. One is called point-to-point, the other one is point-to-multipoint. Let's talk about the point-to-point first. So as you can see here in this picture, I've got this building A to the left and building B to the right. And I've got this LAN switch that sits inside this building. And then I've got this bridge that has one connection into the switch and another connection that connects to a directional antenna. And this directional antenna is on both sides. And by pointing them toward each other, we can create this wireless connectivity between the two buildings. Now, in an ideal world, you would want to have some sort of like a fiber optic, physical wired connection between the two buildings. That's the most ideal scenario. But in some instances, it's not possible. And this is where this outdoor bridge point-to-point connectivity comes into the picture. Next, let's discuss point to multi-point. So here, it's very similar to point-to-point, but as you can see, there is another building in the middle here. So let's say this is building A, this is building B, and we got building C. Building B in the middle here has this what's called an omnidirectional antenna. And what that means is it's a type of antenna that is capable of transmitting its signal equally in all directions, so it can reach the other buildings simultaneously. So it kind of radiates its signal equally in all directions and allows those directional antennas to kind of amplify the signal, if you will. And this allows all three buildings to be connected with each other. Next up, we got the mesh network. This is a specialized type scenario. So in a very large environment, we can create a mesh topology to allow wireless traffic to be bridged from one access point to another until it reaches the wired LAN infrastructure. So let me show you here. So as you can see here, we got all these different access points, and only one is connected to the LAN infrastructure, but the rest are all connected to each other as repeaters. And it's what we call daisy chaining of APs, and it offers transparent roaming. And typical use case is a university campus or a sports stadium with thousands of potential people that want wireless connectivity. Now, when you think of a mesh network, you might think, oh, repeaters are bad ideas, so mesh networks must be horrible. That is not true. Cisco uses its own proprietary mesh network protocol for wireless connectivity, which is pretty intelligent, and it figures out how to collect all the traffic and then bridge it across all the way to the wired infrastructure in a seamless fashion. Plus, it has some interesting auto-healing capabilities. So let me explain. Let's say if this guy dies. Well, if you're using a mesh network configuration, what's going to end up happening is this access point right here and this access point right here, they're going to automatically increase the power transmission of their radio frequency. So the signal strength increases, and they're going to end up making up for the slack of this access point that just died on us. So it's really interesting. It's really cool. And in a large environment, that's what you would typically see set up, where you don't have the ability to connect each access point physically back into the LAN. In an ideal world, you would want every single AP to be able to connect back into the LAN infrastructure with the physical Ethernet cable. But that's not possible in some scenarios. And that's where the mesh network comes in. Now let's discuss different wireless LAN standards and channels. First, let's discuss radio frequency. RF, or radio frequency. That's what the wireless local area network is all about. So when I think of radio frequency, what I think of is radio in your car, and you have this FM stereo player in your car. What you do is you have either AM or FM channels, and you can connect to 92.3, and you might connect to hip hop. And if you switch it to 96.6, you might connect to jazz. And if you switch it to 99.7, you might connect to classical music. So what you have as you switch from one frequency in FM to another frequency, you're basically hopping channels. You're tuning into different channels. And that's exactly what we do in the wireless LAN network. And what we have in the wireless LAN network, two different unlicensed frequencies that are dedicated for wireless communication. The first one is 2.4 gigahertz band, and it's a range that starts at 2.400, goes all the way up to 2.485 gigahertz. And the other one is 5 gigahertz band, and the range starts at 5.150 all the way up to 5.825 gigahertz. Once again, these are different. You can think of these as different radio channels. Lower frequency translates to longer range, but the data rates are lower. So for example, 2.4 gigahertz frequency has a higher, longer range, but the data rate drops because it extends the signal. So the longer you extend the signal, the less it has the ability to deal with high throughput data. And the inverse is true, or the reverse is true. Higher frequency equals smaller range, but the data rates are higher. So the 5 gigahertz band, for example, that's higher frequency. The range is smaller with 5 gigahertz, but the data throughput is higher. And radio frequency signals are negatively impacted by a couple of different things. And there's a whole slew of different things we can talk about, but the ones that I wanted to highlight are things like reflection. So if you have like a mirror or metal, wireless signal kind of bounces off of it, right? So that's reflection. And refraction is where the signals bend after they hit either the water surface or certain type of surfaces, the signals bend. Absorption is like signals going through the wall. If the wall is made up of certain type of material, your signals may not make it to the other side of the wall. So that's absorption. And finally, scattering, where the signal just kind of scatters everywhere. So these are problems, these are issues that the wireless LAN suffers from, and we have to be cognizant of that as we're designing our wireless network, because these things can have an impact on the overall quality of our wireless LAN. Now let's dig a little bit deeper into the two different bands that we talked about, 802.11 bands in particular, 2.4 gigahertz and 5 gigahertz. First, let's focus on 2.4 gigahertz. So 2.4 gigahertz has 14 channels. These are called wide channels. Each channel covers a frequency range that is allocated to more than 4 consecutive channels. So let me explain. So if you look at this channel 1, for example, it has this frequency that kind of bleeds into some of the other channels. So for example, 2, 3, 4 are all impacted by channel 1. And then as you can see, channel 6 starts, and channel 6 then also kind of bleeds into different channels. It's bleeding into 5, it's bleeding into 7, 8, 9. And then we have channel 11 here. And channel 11 also bleeds into 12, 13, 14, and also partially number 10. So what does that mean for you as a consumer? It means at a 2.4 gigahertz level, you only have 3 non-overlapping channels, meaning you have 3 clean channels that you can use in your environment. Why is this important? Well, if you have an environment where you expect a lot of devices to be connected, also known as high density environment, then you may not find that 2.4 gigahertz is sufficient enough for you because it doesn't offer you enough non-overlapping channels. And like I said, you do not want channels to overlap. If they overlap or bleed into each other, then they cause interference, and interference results into collisions, and collisions are bad, right? Which means drop packets, and we can have a lot of retransmission going on our wireless network, and we don't want that. So that is something I want you to keep in mind that this is a limitation with the 2.4 gigahertz band. And the only channels that are your friend are 1, 6, and 11. You should avoid using any other channel altogether on a 2.4 gigahertz band. Next up is the 5 gigahertz band. Channels here are narrow, as you can see in the picture here. Using 20 megahertz, we can have up to 24 non-overlapping channels. 5 gigahertz offers better throughput than 2.4 gigahertz because you have more channels available to you. And there's also a technology called channel bonding that allows us to bond multiple channels together. Let's say at 5 gigahertz, if each channel is 20 megahertz, if we bond 2 channels together, that would be 40 megahertz. And if we bond 4 channels together, that would give us 80 megahertz. And when we do that, what that does for us essentially is it increases the throughput quite a bit. And that's what we're experiencing with the technologies that we have in place today. Now let's look at different 802.11 standards that are out there. In the beginning, 1997 is when the wireless technology was introduced. Can you imagine a life before wireless? I cannot. So it's kind of humbling looking at this table here. It was at 2.4 gigahertz, 5 gigahertz wasn't supported, and the maximum data rate at the time was 2 meg. Then in 1999, 2 years later, we had 802.11b. And once again, it supported 2.4 gigahertz, did not support 5 gigahertz, and it was quite a significant jump, 11 megabits per second in throughput. Then 802.11a came out the same year, but it was on the 5 gigahertz band, and it offered a much better throughput, 54 megabits per second. But the reason 802.11a never took off is because at the time when B and A were introduced, there was a special silicon chip inside the access points that needed the 802.11a technology to be implemented. That was actually in shortage on a global scale. And because it was in shortage, 802.11b standard took off, even though technologically it was a lot less superior than 802.11a. Then 802.11g came out in 2003. It also supported 2.4 gigahertz, but then the maximum data rate went up to 54 megabits per second. Then in 2009, N standard came out. It supported both 2.4 gigahertz and 5 gigahertz with a total maximum throughput of 600 meg. Then in 2013, standard AC came out. Did not support 2.4 gigahertz, only supported 5 gigahertz and a maximum throughput of 6.93 gigabits. And finally, the IEEE standard 802.11ax came out in 2019. This is the latest standard available today, supports both bands, 2.4 gig and 5 gig, and is 4 times the data rate of 802.11ac, which is absolutely insane. But to take advantage of this kind of throughput, you need all the wireless clients on your network that support 802.11ax. And that is the biggest challenge. In real world, your wireless clients are always going to be a few years behind. So if you think of your laptop or your desktop or your phone or your watch or any device that needs Wi-Fi connectivity, you're going to find that most of those devices you bought a few years ago, they probably support an older standard. Even if you buy the latest and the greatest access point, that doesn't magically mean that everything is going to start communicating at 802.11ax. Both the client and the access point must have the appropriate hardware and software capability to support 802.11ax. Now, to further crystallize these 802.11 standards, because I know when I was a student for the very first time and I heard about these standards, I mean, it confused the heck out of me. So I want to help you understand these in a much simpler manner. So think of it as your cell phone. A couple of years ago, we were all on 3G, and then 4G came along, and most of us are on 4G today. And some of us are lucky enough to live in metropolitan areas that actually have 5G connectivity, and we're enjoying the higher throughput of 5G. But the idea is that as we move from the previous generation to the next, 3G to 4G to 5G, it's inherently understandable and understood that 5G is better than 4G and 4G is better than 3G. So with this in mind, I want you to relook at the table we just looked at a moment ago. So here's that table again, but pay attention. To the left, there's more information. So a nonprofit organization called Wi-Fi Alliance introduced this idea of Wi-Fi Gen or generation. And the reason they did that is to make it simpler for people to understand. Because as you can see, these IEEE standards have no rhyme or reason. Like we start at B, then we went to A, then we went to G. I mean, what happened to everything in between? Then you went to N, then AC, and now AX. There's kind of no rhyme or reason behind these different 802.11 IEEE standards. So the Alliance, the Wi-Fi Alliance, took it upon themselves to make it easier from a marketing perspective for people to understand how these different Wi-Fi standards operate. So very similar to 3G, 4G, 5G we just talked about a moment ago. If you have an access point that supports Wi-Fi 4, then you know it's 802.11n and these are the capabilities. And if you have Wi-Fi 5, then you know the capabilities, and so on and so forth. But where it makes the most sense is when you are talking to your upper management. Let's say your boss wants you to upgrade the wireless infrastructure. When you're talking to your upper management, instead of talking about all this technical mumbo jumbo, you can just say, I'm currently investigating Wi-Fi 6 solution. Because I believe in order to protect our investment, we need to be on the latest and the greatest technology so we can be protected for the next 5 to 7 years, if that happens to be your refresh cycle. And a couple of other things Wi-Fi Alliance did that I think are really cool and worth mentioning. If you see this symbol with the digit 4, that signifies Wi-Fi 4. If you see the symbol with 5, that's Wi-Fi 5. You see the symbol with 6, that's Wi-Fi 6. If you see these icons on a box, when you purchase an access point, then you automatically know that access point you just bought has that capability, or it belongs to that particular Wi-Fi generation, if you will. And anything that's Wi-Fi certified, you'll also see this logo on there. And if it's Wi-Fi 6 certified, you'll see the Wi-Fi 6 certified logo as shown on the screen. Now let's talk about wireless LAN architectures. First architecture I want to talk about is autonomous AP. Autonomous AP is a standalone access point, and it has a brain of its own, meaning it has all the required intelligence it needs. It's capable of being completely self-sufficient. It has the hardware and software. It also has the ability to send wireless signals, and at the same time has one leg into the wired network. It's suitable for small environments. However, it gets harder to manage in large environments because you have to touch each access point individually, one access point at a time. And if you happen to have dozens or hundreds of access points, it could be painful to manage them. And autonomous system access points connect wireless SSIDs to wired VLANs at the access layer. So let me explain. So if you have these SSIDs that you see here at the bottom, 401 and 501, each access point typically also has a management IP that you use to be able to manage that box, like via a GUI or CLI or whatever. You need to be able to connect and configure that box, right? So that's pretty obvious. Then what you do is the physical link between the access point and the switch, you would want to run it as a trunk link with these VLANs allowed, which is the management VLAN, VLAN 17, and then VLAN 401 and 501 map to these SSIDs at the bottom. and then same trunk link with the allowed VLANs up into the distribution. And at the distribution level, we have these switched virtual interfaces or SVI set up for layer 3. And then we have core all the way at the top. So this is the typical access distribution core model. And this is how the autonomous AP interconnects into our 3-tier architecture. Next one is a cloud-based access point. So if you guys are familiar with Cisco Meraki solution, that's what we're talking about here. It's internet-based centralized management platform. It's a single web dashboard for the configuration management, monitoring, and troubleshooting. It decouples the control plane from data plane. Control plane traffic is the traffic between the access points, and data traffic is the actual data that the users want to send. Could be an email or web browsing or whatever they want to do. That's the actual data, and that's the data plane. Control plane traffic travels to the cloud, whereas the data plane passes through the access point, stays local. So let me explain. Here you can see, as you can see, these Meraki access points, what ends up happening is we can no longer configure them from within the organization, meaning all of these access points go talk to the Cisco Meraki cloud, which is basically a controller available over the internet. And all these access points go and talk to and register with that controller. And we log into a GUI dashboard. And in that dashboard, we configure, manage, monitor, and troubleshoot all of these Meraki access points. However, one key thing to keep in mind is as the data travels, so let's say if there's a PC here, A, wants to talk to PC B, the traffic here will physically go from the access point to the switch here, to the distribution, then across the distribution, back to the access switch, down to the other access point, and eventually over the wireless signal, down to this laptop on the left. And the reason I drew this is to show you that the data traffic, the data plane traffic stays local. It never goes to the cloud. The only traffic that goes to the cloud is the management traffic or the control plane traffic, but the actual data stays local. Next up is the split MAC architecture. This architecture is composed of two main ideas. One, that we have a central controller that manages all access points. It's called Wireless LAN Controller, or WLC. And the second idea is that it separates management functions from real-time functions of the access point, known as the lightweight access point. So here is the idea. If we were to take this access point, which is the autonomous access point, and split the functions where the wireless LAN component, wireless LAN controller component has all the management functions, the RF management, radio frequency management, association and roaming management, client authentication, security, and QoS. All these are separated out and handled by a central controller called wireless LAN controller. And the guy at the bottom becomes a lightweight access point. It's not a full-blown autonomous access point. It doesn't have a brain of its own. It has very basic real-time functions such as radio frequency, transmit and receive, MAC management, and encryption. These are the only things that it's responsible for. But then all the other functions are offloaded to the wireless LAN controller because it's a much bigger, beefier box that has the ability to handle and process information in a much more better way. But more importantly, the reason we decouple the two functions is so it's easier for us to manage everything centrally. Instead of managing each access point separately by hand, we can go ahead and define the template on our controller And then as we add more access points to our network, those access points can talk to the wireless LAN controller and download their appropriate configuration accordingly. CAP/WAP, or Control and Provisioning of Wireless Access Points Tunneling Protocol, it encapsulates data between lightweight access point and wireless LAN controller within new IP packets. So what that means is that a tunnel, this right here, you can think of it as a tunnel that gets created between the lightweight access point and the wireless LAN controller. And all the data is encapsulated within this tunnel. And we can either switch this data at layer 2 in our network or route it across our network at layer 3. Going deeper into the split MAC, CAP/WAP that we just talked about is composed of 2 tunnels. There's a control tunnel that operates at UDP port 5246, and there's a data tunnel that operates at UDP port 5247. So here are the 2 tunnels that get created. And one thing to note here is that there's a control tunnel. This is the one that gets established first because control channel is the communication between the lightweight access point and the wireless LAN controller. And then the data tunnel gets created later. This is for handling the actual user data that has to go across. CAP/WAP control messages are encrypted and authenticated. CAP/WAP data packets are not encrypted by default. However, if encryption is enabled, DTLS is used. Datagram Transport Layer Security. Going even deeper into split MAC, CAP/WAP tunneling allows the lightweight access point and wireless LAN controller to be logically separated without needing layer 2 in the network transport. So as you can see here in this diagram, we got these SSIDs on the lightweight access point at the bottom that are mapped to the VLANs up at the top on the wireless LAN controller, but these VLANs aren't required in the middle of the network. So that significantly reduces the overhead in our network. Traffic on SSIDs 301 and 401 from clients is transported across the network infrastructure and encapsulated inside the CAP/WAP data tunnel. The tunnel exists between the IP addresses of the access point at the bottom and the WLC at the top, hence allowing the tunnel packets to be routed at layer 3. And finally, no trunk link is needed in the transport as all VLANs are encapsulated and tunneled as layer 3 IP packets rather than individual layer 2 VLANs. So once again, this could be all layer 3. This link could be layer 3. This link could be layer 3. All kind of layer 3 in the middle, for example. And we're able to kind of tunnel all this information, this layer 2 information, if you will, across a layer 3 tunnel because we have the ability to encapsulate the information in a CAP/WAP data tunnel. Now let's look at the different wireless LAN deployment models. First, Unified Wireless LAN Controller. Unified WLC is located centrally at the core of the network. It's purchased in the form of dedicated physical appliance or appliances because typically you would want to have redundancy and high availability, so you would have multiple of these. Unified wireless controllers can support up to 6,000 APs. However, they do scale out, meaning if you need more APs than the maximum required, you would add more wireless LAN controllers to your network. And here's our physical appliance, and all of these lightweight APs at the bottom come and register. And once again, this all happens across the CAP/WAP tunnels that we talked about a moment ago. And once again, why do we need this type of controller model? Is to have scalability. 6,000 APs. That's a lot of APs. If you had to configure each and every one of those APs, that could take you months or years to complete if you did them by hand. But you can simplify the process. You can log into the wireless LAN controller, set up templates, and then as these wireless LAN controllers come online, they call home to the WLC and auto-configure themselves over the network and create those tunnels and be connected. That's the beauty of it. Next up is the wireless LAN controller, cloud-based. And here the idea is, instead of like a campus environment, we could have that located in our private cloud, aka data center. And typically these are consumed in a form of virtual machines or VMs. And of course, like I mentioned earlier, you wouldn't want to have just a single VM. You would want to have redundancy in your network. Cloud WLCs can support a maximum of 3,000 APs. And once again, it's a scale-out model, meaning if you need more APs to be supported, you simply add more VMs. The next one up is embedded wireless LAN controller. In this deployment model, the WLC is co-located on the switch hardware. So here, for example, if you look at the new Catalyst 9K series, you could have these wireless LAN controllers integrated and embedded right into the switch. And that's what an embedded WLC is. These are suitable for small environments. Maximum number supported is about 200 APs. If you need to add more, you would want to add those wireless LAN controllers to other switch stacks in your environment. We could also have a Mobility Express type of deployment model. In this model, the wireless LAN controller is co-located on the access point itself. It's suitable for super small environments, typically can support up to a total of 100 APs, and the scalability is limited here. If you need to add more APs, you're not going to be able to add simply more Mobility Express wireless LAN controllers. Instead, you're going to have to look at one of the other models we just discussed a moment ago. And so that's why it's important as you're designing your network that you take a step back and think about how your environment is going to look like in the next 6 months, or maybe a year or 2 to 3 years down the road, because it's not like you can constantly add more wireless LAN controllers to your environment. Most likely, you would want to add a wireless LAN controller that sits in your environment for at least 5 to 7 years, so you don't have to keep messing around with it, right? The idea is to set it and forget it. So take a step back, think about what you want, and then move forward. However, if you're working for a smaller company, it's okay to start out small with a Mobility Express type controller, and then as your company grows, then you look at things differently. Now, here's a summary of everything we just wrapped up talking about. All the different models that are available to us, unified, cloud, embedded, Mobility Express, and autonomous, it's all about the placement of the wireless LAN controller. Remember, the whole idea is we want a centralized placement where we have this intelligence that is capable of managing all the different access points, so we can configure them, we can see what's going on, correlate, and all that. And what's interesting here is the unified model supports up to 64,000 clients. The cloud supports up to 32,000. Embedded up to 4,000. Mobility Express, 2,000. And the typical use is, once again, large enterprises use the unified model. Large enterprises could also potentially use the private cloud model, and the smaller organizations would want to use embedded and Mobility Express. And as you can see here, the cost of each solution is directly proportional to the number of APs and clients supported, which makes sense, right? So the more clients you have and the more APs you need supported, the higher the cost of the solution is going to be. Now let's look at the last section of our discussion today, wireless LAN security. Wireless network is considered untrusted by default and is inherently insecure because wireless devices communicate with each other over the air. If you have two people that are talking in an open public space, even if they're having a private conversation, you cannot consider it a private conversation because it's in an open public space. At a coffee shop, two people are talking about some secret stuff. Well, it's no longer a secret. What if somebody's recording the data? Or what if there's a bad guy sitting there who is looking for that secret? Well, you just give it away, right? So wireless LAN has some of these inherent insecure and untrusted attributes by default, but we can fix that. Anyone within the access point's wireless signal range can potentially listen in on any conversation happening over the air unless we do something about it. And that's where API comes to rescue. Now, what is an API? Well, here's the deal. I'm not talking about application programming interface. Do not confuse it with that. It's a different mnemonic, okay? And it's a memory aid for you to remember for exam purposes and CCNA certification purposes that wireless LAN security is composed of three distinct components. First of which is A in API stands for authentication. So what we do here is we verify users' identity before we letting them connect to the access point. How do we do that? Well, if you think about it, the most common way of doing that is by providing a username and password credentials. And the advanced methods may require bidirectional authentication. What do I mean by that? One directional is where we trust that the access point is a trusted device and the wireless client has to authenticate to the access point. But what if you have a bad guy who is using a fake or a rogue access point and maybe using the same name as your home network? And when you connect to that access point, all of a sudden, that bad guy is now running a man-in-the-middle attack on you. To avoid that, with bidirectional authentication, the client also authenticates the access point to make sure it's connecting to an access point that it's supposed to be connected into and not some random rogue access point. And an example of authentication in real world at home could be a pre-shared key. So I'm sure you're familiar, if you have an access point at home, you have an access key or pre-shared key, right? So you have to type in every time you want to connect a laptop or your phone or tablet, you have to plug in a key to connect. That right there is a pre-shared key. That's what you're using to connect to your access point. Now, in this case, let me explain the authentication piece. So here we got this employee, his name is Bob. He's connecting to the network. And when he initially establishes communication to the access point says, "Who are you?" Well, Bob says, "I am Bob," by providing username and password credentials. And those credentials could either be verified by the AP itself, or those credentials could potentially be verified by a solution like Cisco ICE, Identity Services Engine, or Microsoft Active Directory, or a Radius server, or an LDAP server. Any of those solutions are possible, but some sort of authentication server may be involved in the process. And then at that point, you are connected. But like I said, this guy at the bottom here, Mr. Robot, might have a malicious intent. Mr. Robot might have an AP that is also advertising an SSID called private. And let's say if you're also using the SSID private, when Bob wants to see which SSID to connect to, he's going to see both private SSIDs on his laptop. He's not going to be able to decide which one to connect. What if mistakenly he connects to this SSID right here? Well, it's a good day for Mr. Robot because that's what he wanted to do. At that point, Bob's information is being completely captured. Bob might be completely oblivious to this. He might be thinking, well, I'm good because I can connect to Google and I can do my job. But little did Bob know that there's a man-in-the-middle attack happening. And the reason it's called man-in-the-middle is because you literally have a man who's in the middle with this access point, because the other side would be internet, right? So a smart hacker or a bad actor would make sure that you do get internet access, so you don't get to realize that you're connected to a device that doesn't have any access to anything. By giving you internet access, when you're connected to the internet, you may not realize for hours or potentially days that you're connected to a rogue device while Mr. Robot is doing a number on you and you're completely clueless. So, very important that we have authentication in place, especially bidirectional authentication, where not only the AP authenticates a client, but the client also authenticates the AP. Next one up is privacy. So in our API, that's the P. The idea here is we encrypt all the data between wireless devices for privacy. And what is encryption? If you're not familiar with it, it's the process of converting plain text into a ciphertext using a mathematical algorithm. And only authorized parties can decipher this data. So let me explain. So as you can see, Mr. Robot is listening in on the same, because he's within the same wireless range as Bob. Mr. Robot, we're using the same shared space and same channel and signal. Mr. Robot has the ability to listen in on what's going on with Bob. If Bob says in plain text, "My password is COVID-19, Mr. Robot can hear that, and then next time Mr. Robot can pretend to be Bob and then wreak havoc on our network by connecting into our LAN and basically injecting worms and viruses and all kinds of nasty things in our network. To protect ourselves, we can use encryption. And what that means is, as the wireless laptop is communicating with the wireless access point, what the laptop can do is, instead of using the password in plain text, it can run a mathematical formula on COVID-19, and it might end up being 3129137. And these digits get transported across over to the access point, and then the access point can run the same algorithm to compare and then decrypt this data. When we do that, what ends up happening is Mr. Robot, when he looks at this number, he goes, "Huh? What is this?" Mr. Robot is oblivious to he doesn't understand what these numbers are. So it's important that we encrypt the data. This is also called confidentiality. You'll see different terms being used in security for privacy, but you might see this term privacy being interchangeably used with encryption or confidentiality. These are all the same thing. And the I in our API stands for integrity. So what that means is we want to avoid data tampering by running an algorithm or a hash that matches on both sides, the sender and the receiver. So the example that I was talking about earlier, we want to make sure that the information that Bob sent to the AP is the original packet that Bob intended to send, instead of Mr. Robot pretending to be Bob. And the way we do that is by running a hash or a mathematical algorithm, and by adding a little hash value at the end of the password. Could be E7, for example. And then when the other side gets it, which is the AP in this case, it would run the same formula based on the algorithm that they decide to use, and then match those hashes. And if the hash is an exact match, then it means that the information was not tampered with. You can think of it as a secret little stamp that's put in on that packet when it's sent across. That stamp has to match on both sides. And once again, if we do this right, we can kick Mr. Robot out of the picture here, and he cannot inject malicious traffic into our network. Now let's look at a couple of different authentication methods. There are a couple of legacy authentication methods I want you guys to look at. First, called open authentication. Any client can join the AP without authentication. Now that sounds pretty pathetic, right? But think about it. Coffee shop, airport, stadium type venue, shopping malls. You want the ability to have access to the internet. And this is where open authentication is used on the access points to just give you free guest access to the internet. Next up is PSK, also known as WEP or Wired Equivalent Privacy. Same secret key used on both access point and the client. Now WEP is deprecated and not recommended anymore. We still use the pre-shared key, but the WEP technology is no longer in use. And I'll dig more deeper into the WEP technology momentarily so you understand why it's no longer recommended. Here are the new authentication methods. We have this authentication method called EAP or Extensible Authentication Protocol. This is used for port-based authentication. And here, the idea is we've got three different players into the mix. We've got the supplicant, who's the client to the left. We got the authenticator, who's the access point, could be a wireless LAN controller in the middle of the network. And we got the authentication server to the right of our diagram. And what ends up happening here is when the supplicant wants to join the network, credentials are sent. So let's say Bob uses his username and password. Those credentials are seamlessly passed through the authenticator over to the authentication server. Authentication server either accepts or denies the credentials. If the credentials are denied, communication stops. On the other hand, if the credentials are accepted, the authentication server generates an encryption key for both the supplicant and the authenticator. And it's the same key on both sides, and it's only good for that particular session. So as long as the supplicant continues to communicate after being authenticated, they'll have the same key. Now, if the session drops and a few hours later, if the same supplicant wants to rejoin, the whole process has to happen again, and a fresh pair of encryption keys are generated by the authentication server. So this is how the security is maintained. Now, within EAP, we have different additional components that add more enhancement. First one up is LEAP, or Lightweight Extensible Authentication Protocol. This is Cisco proprietary, and you should not use it anymore because it's insecure. Next level up is EAP. That stands for Extensible Authentication Protocol, Flexible Authentication via Secure Tunneling. This is an enhancement over LEAP, and you'll see some networks implement that. Next level up is PEEP, or Protected Extensible Authentication Protocol, developed by Cisco, Microsoft, and RSA. It uses a TLS tunnel to protect the authentication transaction. And finally, EAP TLS. TLS stands for Transport Layer Security. It's open industry standard protocol. It's considered the most secure, and the end users on various servers authenticate each other by using each other's digital certificates. Now, as you can imagine, when we talk about digital certificates, we're now adding another layer of complexity in our network, which means we now need to maintain PKI, or public key infrastructure, meaning we need to add a CA, or certificate authority server, in our environment and within our infrastructure, and then distribute certificates to all the devices. And that significantly increases the complexity of our network. But in a typical enterprise network, it's a must. Next, let's discuss privacy and integrity methods. Very first type of privacy and integrity method we had was TCP Temporal Key Integrity Protocol. It's a legacy protocol. It's deprecated and not recommended anymore. Then came along CCMP, stands for Counter CBC MAC Protocol. It's more secure than TCP. It's used in WPA2. Then came along GCMP. GCMP stands for Galois Counter Mode Protocol. It's a robust authenticated encryption suite and is better than CCMP. It's used in WPA3. Now let me walk you through the evolution of security. As you can imagine, all these different pieces I talked about, it's probably getting you pretty confused right about now. So you may be asking, how do I choose the best security suite? Because we need to make sure we have the right authentication mechanism, coupled with integrity, coupled with encryption or privacy. How do I kind of put all the pieces together? Well, thanks to the Wi-Fi Alliance, they created what's called a WPA, or Wi-Fi Protected Access Certification process. And it significantly simplifies how we look at the different options that are available to us to protect and secure our Wi-Fi network. And here's a table that shows an evolution of these technologies. First, we had WEP, or Wired Equivalent Privacy. Don't be fooled by the name. It's very insecure, naturally, because it was the first security suite that was introduced. And it used an encryption method of RC4 or Rivest Cipher 4. Very, very weak. You shouldn't use it. Data integrity of CRC32. It had two authentication mechanisms, either open or shared. And finally, is it okay to use today? I would say no. Now, moving on. WPA came out in 2003. It used TCP with RC4. As I said, RC4 is bad news, so naturally this should mean you should avoid it. However, it used a better quality data integrity protocol called MIC, Message Integrity Check. And authentication-wise, it used pre-shared key and 802.1x with EAP variant. So the different variants of extensible authentication protocol we just finished talking about, it used that, which makes it very, very secure from an authentication standpoint. But I say that you do not use it today because of the fact that it's known to be vulnerable and it's hackable. As a matter of fact, there are tools available that you can use today to easily crack either WEP or WPA. Next up is WPA2. This was introduced in 2004, and it uses the encryption method of CCMP and Advanced Encryption Standard, or AES. AES currently is the most popular encryption method used on wired and wireless networks today. And from a data integrity perspective, it uses CBC MAC. From an authentication perspective, it uses pre-shared key and .1x with EAP variant. Once again, if you have WPA2 at home, you'll be using pre-shared key. But in an enterprise environment, you'll use 802.1x with EAP variant. I say that if you're using WPA today and that's all you have supported on your access point and wireless devices and clients, then go ahead and use it. But it's a partial yes. Okay. Finally, we have this WPA3 standard that was introduced in 2018. It also uses advanced encryption standard, but instead of the 128-bit being used here, WPA3 uses AES 192-bit. That's the biggest difference. Makes it much, much stronger. It uses SHA, or Secure Hash Algorithm, for data integrity. Very popular and strong data integrity protocol. And from an authentication perspective, it uses what's called SAE, or Simultaneous Authentication of Equals, and it still supports .1x with EAP variant, and whether or not you should use it today, I would say, heck yeah. That's the protocol and the suite that you should be using in your environment today. Welcome to CCNA 200-301 course. Today, we're starting a new section. Section 3, Part 1, IP addressing and routing. Today's session is all about IPv4 subnetting. Here are the topics I plan on covering today. We'll first discuss IP overview. We'll then get into IPv4 binary to decimal conversion. Then talk about IPv4 private versus public addresses. And finally, I'll wrap it up with IPv4 subnetting. Let's go. First, IPv4 overview. IPv4 is the most widely deployed protocol globally, and that's the dominant protocol on the internet today. IPv4 is defined in IETF publication RFC 791. So if you Google RFC 791, you're going to come across the original specification of IPv4. It was published in 1980s, I believe 1981 to be exact. And it's been around since then. Let me quickly touch base on IETF. IETF stands for Internet Engineering Task Force. They've been around a long time as well. It's an open standards organization based in the United States. They're located here in the Silicon Valley, and they're responsible for the enhancements to the TCP-IP protocol. And IPv4 happens to fall within that realm. IP address is a 32-bit long binary string, and I'll show it to you in a moment. But a couple of things to keep in mind. You have to read it from left to right, very much like mathematics. Total number of IP addresses provided by IPv4 address space are 2 to the power of 32, or 4.3 billion roughly, give or take. Now, given the current population of 7.8 billion people globally, you may think that this is not nearly enough number of IP addresses to be able to serve all the people on planet Earth, given the fact that over half of the world's population today happens to be on the internet. Well, you would be correct in thinking so. We're actually running out of IPv4 addresses, believe it or not. However, there are some interesting techniques and hacks that we can use to extend the life of IPv4. We'll talk about that as well. An IP address is divided into 4 different octets of 8 bits each, or 1 byte each. 8 bits equal 1 byte. And let me show you in a moment what an octet looks like. But the word octa comes from Greek, and octa means 8. So 4 octet naturally means 4 pair of 8 different values of binary. And each decimal number is 1 byte. That means it's 2 to the power of 8, or 256. And the decimal range starts from 0, goes up to 255. And let me show you what I mean. If you look at an IP address, you may find an IP address that looks like this, 192.168.10.1. It's also known as dotted decimal format. And if you were to look at the binary of this IP, that's what you're looking at the bottom here. So let me explain. If I can go slightly deeper here, you see this 192 here and this IP address. This right here is translated to this binary code at the bottom in the first octet. And each octet is delineated by a dot. As you can see, there are 3 dots, right? And you can see the same dots down below. Up at the top, we have the decimal format, which we're familiar with, right? But computers understand binary. And that's why we need to understand binary as well, because we need to understand the binary math in particular to be able to deal with IP addressing. So as I mentioned, first octet 192 translates to 11 and a bunch of zeros. Then the next one, the second octet, translates to 168. That is 10101 and a bunch of zeros. And then the third octet is 10. And this translates to a bunch of zeros followed by 1010. And then the final and the fourth octet, which happens to be 1 in decimal, it translates to a bunch of zeros followed by a 1 in binary. So as you can see, in binary, we can only have either a 0 or a 1. That's what binary means. You're either off or on. 0 in binary means off, and 1 in binary means on. Now, if you feel a little lost at this point, let me help you out here real quick. So what we'll do is, on my Apple Mac Mini, we'll go up to the top, Apple menu, top left, go to System Preferences. We'll then click on Network and click on Wi-Fi, Advanced, and then finally click on the tab TCP-IP. And what we're looking at here is the IP address that's assigned to this machine, along with a subnet mask and a router. Now, why is this important? Well, the reason I believe it's important to talk about this quickly is the fact that I guarantee you, pick any device in your network at home and it has an IP address. And specifically, as you can see here, it says IPv4 address, right? And then there's a subnet mask and the router. But the bottom line here is every single device on your network has an IP address in your home or your office or any other environment where you have devices connected to the internet or to a network. They must communicate via IPs. That's why it's important and relevant to understand IP addressing. And hopefully this provides a real-world perspective on this. Now back to IPv4 overview. Now each IP address is accompanied by a subnet mask. And without a subnet mask, IP really doesn't give you any information. So it's almost a requirement that you understand the subnet mask when you're looking at an IP. So here's an example. You got 192.168.10.1, and the subnet mask is right below it, which is 255.255.255.0. And what this does for us when we have a subnet mask, it helps us differentiate and delineate between the network portion of the IP and the host portion of the IP. Hang in there with me. If it doesn't make a lot of sense right now, do not worry. By the time you're done with this video, you will be a master of looking at IPs and being able to make sense of what these numbers actually mean. So just to kind of reiterate, we got this IP address and we got the subnet mask down below. As you can see, the first 3 octets here in this case, octet number 1, octet number 2, and octet number 3. Same thing. Octet 1, octet 2, octet 3. Up here we have an IP address. Down below we have a subnet mask. Okay, just to be clear. And when we look at these 3 octets, the first, second, and the third, that makes up the network portion for at least the address you're looking at. It's different for different types of IPs and different types of subnet masks. But in this case, what we have is a network portion that is the first 3 octets, and the host portion that is the last octet. IP address can be class full or classless. And I'm going to go deep into this topic so you understand what that means momentarily. Class full means when the original IPv4 RFC came out, RFC 791 that I was talking about on the last slide, it had 5 different classes specified within it. Class A, Class B, Class C, D, and E. And we'll talk about all these classes in a moment, but that's what the original RFC 791 defined in its specification. However, before I start talking about the different classes of IP addressing, what we need to talk about first, I believe, which would make it a lot simpler for you to understand things going forward, would be a quick look into the binary to decimal conversion for IPv4. This is a key concept, guys. This is the most fundamental and key concept when it comes to layer 3. If you guys do not get this concept, you guys will struggle with layer 3. And layer 3 is the heart of routing. Routing happens at layer 3. So you need to understand it. If you want to become a world-class engineer, you must understand how routing works, how IP addressing works. Let's take a look. So we have this conversion chart that I'm going to show you here in a moment. It helps us convert from decimal to binary and binary to decimal. We can kind of go back and forth. And each bit position in an octet has a decimal value associated with it. So for example, what we do is we actually draw this out. So remember we talked about 8 bits, which equals 1 byte. So an IP address, when we look at, let's say for example, 192.168.1.0. When we look at this, each octet, this is the first octet, this is the second octet, this is the third octet, and this is the fourth octet. Each octet is 8 bits. 8 bits per octet. If you were to kind of chop up an IP address into different octets like this. And if you were to zoom into one of these octets, let's say we zoom into this first octet, that's 8 bits. Well, if we can lay them out like this, okay, starting with the value 1, 2, 4, 8, 16, 32, 64, 128. The idea is that these values double, as you can see. They're doubling as we go from right to left. And it will make more sense when I show you that in binary, 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the 3 is 8. 2 to the 4 is 16. 2 to the 5 is 32. So on and so forth. And when we have all the bits on, what we end up getting is what's called a broadcast address. And a broadcast address is an address that's sent to all the devices on the network. Whoever is within that subnet that you belong to, every single device in that network is going to get that message. Hence the name broadcast. It's similar to, if you guys recall, in layer 2 when we were discussing, when an ARP gets sent out and you have all Fs at layer 2, if you guys recall, it's the same thing, but at layer 3 instead. F, all these different Fs happen to be at layer 2. That's the layer 2 broadcast, right? And for us at layer 3, 255 is the broadcast. It's the equivalent. It's the same thing. And what we have next is all zeros. That is considered a network address. So in other words, this defines the beginning of an IP address range, and this defines the end of the IP addressing range. Now let's quickly jump into the IP address classes. So if you guys recall, there are 5 different classes, A, B, C, D, and E. Let's first quickly take a look at Class A. What we get with Class A, according to the RFC standard, is that the first bit must always be 0. What that means is if we were to look at our binary conversion chart, the first bit will always be 0 no matter what. So we can almost draw a line here, and the rest of the bits, once again, we have our starting bit, which is also known as the network address, and we also have the ending address known as the broadcast address, where we have all ones. What that means mathematically, though, is that the Class A starts at 0 and goes all the way up to 127. And let me explain what that means. You see, all the bits when they're 0, right? That means that Class A starts at 0. And because the first bit must always be 0, even for all the ones, the first bit is set to 0. But we have to add up all these numbers here, right? So let's quickly add up. What's 64 plus 32? That's 96. What's 96 plus 16? That is 112. And what is 112 plus 8? That is 120. If we were to add 4, that's 124. We add 2 plus 1. Add 3 to it, that's 127. What we get when all the bits are set to 1 is 127, as shown by the math here. However, as you can see here by these 2 asterisks, if we were to look at these 2 asterisks down below, all zeros and all ones are invalid host addresses. So that is something very, very important to keep in mind. And I'll continue explaining as we move forward, in case if it doesn't make sense at the moment. Now, another thing you want to look at is in Class A, the first octet is dedicated to networks, and the last 3 octets are dedicated to hosts. And the default subnet mask is 255.0.0.0. And here, the total possible number of networks is 2 to the power of 7. That's 128 networks. And within each network, we can have a total of 2 to the power of 24, which is 16.7 million plus hosts per subnet. That number is insane. What we have next is Class B. Class B starts off where Class A ends. So you see it starts off at 128. But before I go there, let's focus on the binary. So the RFC 791 standard defines that the first 2 bits must be set to 1 and 0. So let's go back to our binary conversion chart again. And we're going to be doing that a lot in today's session. So you get a pretty good feel for how this works. Because the standard says for Class B, 1 and 0 are always set this way and are unchangeable, we're going to put them down like that. And another thing we want to keep in mind is, once again, our range always starts with all zeros and it ends with all ones. And then we have different combination of zeros and ones in between, right? This could be 1, this could be 0, so on and so forth. And what that means is, as you can see, the first value here is 128, right? And that's why our range starts at 128, as shown here. And down here at the bottom below, if you were to add 128 to all these different numbers here, let's do that. So 128 plus 32 is 160. 160 plus 16 is 176. Plus 8 is 184 plus 4 plus 2 plus 1. We'll just say plus 7. That right there makes it 191. So this is where the range ends, 191, and voila, it matches this value right here. So hopefully now you guys are starting to see a pattern here. Now, once again, in this one, in Class B though, 2 octets are dedicated to networks and 2 octets are dedicated to hosts. The default subnet mask for Class B is 255.255.0.0. Here we have a total subnets of 2 to the power of 14, that's 16,384, and we have total hosts of 65,534. The reason we have this -2 in the end, as you guys are seeing here, is because, once again, all zeros and all ones are invalid host addresses, meaning none of the network devices, routers, switches, IP phones, desktops, laptops, you name it, any network device in your network cannot be programmed with all zeros and all ones as the host address, because these values are reserved by the RFC to be able to identify the network address and the broadcast address. Next, we look at Class C. Here in Class C, the RFC 791 standard says all the bits in green, the first 3 bits must be 110. So once again, going back to our binary conversion chart, what that means is the first 3 bits will always be 110, regardless, right? So if we were to draw a line like this, because we cannot change the first 3 bits, let's see how the rest of it pans out. Well, I'm missing a 4 here. So what we'll have is 0, 0, 0, 0, 0, and we'll have 1, 1, 1, 1, 1 as the ending. So once again, top one is the starting position, and the bottom one is the ending position. And if we were to do the math, what we'll get is 128 plus 64 is 192. And this is what this value represents. This is where Class C starts. Where Class B ends is where Class C starts. And if you were to do the math here, with 128 plus 64 being 192, and then if you were to add up all these other numbers, it's going to end up being 2, 2, 3. And once again, that very conveniently matches where the Class C range ends. Class C has the first 3 octets reserved for networks and the last octet reserved for host. And the default subnet mask in Class C is 255.255.255.0. Here we have total networks of 2 to the power of 21, over 2 million networks, but we have hosts of 2 to the power of 8 minus 2, which means 2 to the power of 8 is 256. But once again, we cannot use the first and the last in the range. That gives us a total of 254. And that's what we're seeing here. Next up is Class D. Here, the RFC standard said the first 4 bits will be 1110. So going back to our handy dandy binary conversion chart, what you'll get here is the first 4 bits always locked in like this. And once again, our starting range starts with all zeros and ends with all ones. If we were to add up all these numbers, wherever we see 1, we add up those numbers, right? So 128 plus 64 plus 32 gives us 224, which matches the beginning of the range. And the next up, the final, is the 111 and then a bunch of other ones. And the only thing that's missing is 16. If you were to add all that up, that adds to 239, which matches this number right here. Now, one thing I want to mention about Class D is it's a unique class of IP addresses in a sense that it's reserved for multicast routing. And multicast is a whole different way of doing routing in our networks. Typically, when we talk about routing, we're talking about unicast routing. Here, these ranges are dedicated, This whole class D is dedicated to multicast routing. And in this course, we'll touch base on multicast a little bit. We'll talk a lot more about it in the CCNP class. So it's kind of beyond the scope of the CCNA exam, but you need to know a little bit about the multicast, which we'll cover later in the course. And finally, we have Class E. Here, what we get is, according to the RFC standard, first 4 bits are always set to 1, and then, once again, our starting position is all zeros, and then the ending position is all ones. If you were to add up all these numbers, all these ones to the left, you'll get the value of 240. And if you were to add up all the ones, of course, you're going to get 255 as the end of the range. This is, once again, a unique bird in a sense that it's an experimental range. So in real world, you'll never see anything in this range being handed out in your network. So in reality, you should only see the top 4 classes of the IP addressing in your networks, and you shouldn't really see Class E specified anywhere. Now let's quickly talk about classless. So we just finished talking about class full IPs. So remember those different categories, Class A through E, we just finished talking about. This is the other side of it, where we have what's called a CIDR, or classless internet domain routing, or VLSM, or variable length subnet masking, where we have the ability to be able to control IPs. And this technique was introduced to slow down the rapid exhaustion of IPv4 addresses, because as I mentioned, we only have roughly under 4.3 billion IPv4 addresses, and we have to be smart about how we allocate and use them. And like I said, gives you full control as an administrator to use this space and then define and carve out the network portion and the host portion as you see fit. An address in a CIDR notation is written as follows. So you may see an address like this. Even though it belongs to Class A, you might say, well, if it's Class A, it shouldn't end with a /16, right? It should actually, Class A ends in a /8. And the reason Class A ends in a /8 is because, if you guys remember, the subnet mask is 255.0.0.0, which means only the first octet has all the bits on, and then the rest of the octets are all zeros. That's the default class. But that's not what we're seeing here. So what's up with that? Well, this is what's called classless, where we're taking an IP and we're carving it out according to however we want to carve it out to program our devices in our network. And what we have here is the portion to the left, which is the IP address or the network address here, 10.1.0.0 is the network address. That's what's called the prefix or the network address, and the /16 represents the suffix or the subnet mask. And this subnet mask in decimal would be written as 255.255.0.0. That's how /16 is represented. Now let's quickly talk about IPv4 private versus public IP addresses. So what had happened was, because as I mentioned, IPv4, there was this real scare many years ago in the IT community about running out of IP addressing space. And it's real, right? Because we have a lot of devices, a lot of people online, and we're running out of IPv4. So we had to come up with some clever, smart way of dealing with this situation. So what had happened was an RFC 1918 was published, and it defined what's called a private IPv4 address ranges. And these addresses can only be used on the LAN. They're not routable on the internet. And as a matter of fact, the service providers have filters in place to drop packets on their internet routers if the packets are sourcing from private IP address range, and I'll explain that momentarily. And here are the 3 private IP address ranges that you must memorize for the exam. The first range starts with 10.0.0.0 and ends in 10.255.255.255. It's a /8. It's defined in RFC 1918. The next range is 172.16.0.0 through 172.31.255.255. It's a /12 or 12-bit. And the third one is 192.168.0.0 through 192.168.255.255. That's a /16. If you see these IPs configured on your devices, then that means that your devices are configured to take advantage of private IP addressing space. As a matter of fact, I would be willing to bet that most of the environments that you are aware of today, including your home network, a coffee shop, your office, whatever have you, you're going to see IP addresses in one of these ranges. Should never be outside of these ranges. Unless you're talking about a data center where you have servers and things of that nature. Even servers shouldn't actually have public IPs configured on them. You would actually configure private IPs on the servers and then use another clever technique that we'll talk about in a moment to magically mask the private to the public IP. But the bottom line is that these are the private IP address ranges that you must memorize, not only for the exam, but it's a very real-world topic because that's how you configure your LAN or local area network. And as I mentioned, what ends up happening is if you're using these private networks in any of these ranges, 192.168, 10.0, or the 172.16 range that we talked about, as those packets go out and they hit your ISP router, right? So this could be, for example, your Comcast device at your home. This could be your cable modem. And then behind your cable modem, of course, you'll have your router. If that router that you have at home sends this IP, 192.168, 1.0, out to the ISP router, the ISP router will actually discard this packet. It's not going to send it forward. Reason being, these are private IP address ranges. They have no business of being available on the internet because, like I said, the RFC standard specifically called out that these IPs are not allowed to be routed on the internet. So they do not route on the internet. They cannot become part of the internet routing table. So you have to get creative to do something about it. And let me show you how we can get past this challenge. This is where NAT comes in. And NAT stands for Network Address Translation. And what that does for us is allows network devices on the LAN to be able to communicate over the internet. And the whole trick is that NAT function is ran on a router, could be a firewall, mostly a router. And what it does is it changes the source address in the IPv4 header. So if you guys recall the IPv4 header, right? It's 32-bit in length. We just talked about, the 32 bits and how they're carved out, and all the IP addressing we've been discussing so far is part of this right here, the source and destination addressing element. But what I want to point out is we need to swap out this private IP on our LAN that you're seeing to a public IP that we're going to get from our ISP, which means when the packets leave this router is going to run a NAT function, and it's going to translate and swap out this private IP with the public IP. So when the packet gets to the other side, they never see the private IP. All they see is the public IP. And this fools the ISP router. Now, if we were to talk about the ISP router, which is right here, when it gets this packet, when the source address is public, well, this router has no problem because it's designed to forward public routes. So it's going to forward the packet. But if you guys recall on the previous slide, the reason the ISP was actually discarding the packet before using NAT is because it's programmed not to allow the private IP addressing space to be routed across the internet, because that's what the standard says. Now, quick disclaimer, I'm not going to go deeper into NAT here because this section is about IP addressing, but we'll have another section later in the course under IP services where we'll go deep into this topic, and we'll talk about the static and dynamic and different types of NAT strategies that we can use to be able to configure our network. But at this point, I think this is sufficient enough information for you to understand the concept of NAT. Now, let's go through a bunch of different exercises so you get to learn how subnetting actually works. The VLSM, the variable length subnet masking. How does it work? How do we take an IP address and kind of chop it up into different networks? Well, here's the first example where we've been given this IP address up at the top, 200, or network address, I should say, 200.10.5.0/24, and we've been asked to create 4 subnets out of it. Well, how are we going to do that? Here's a 3-step process that I love to use, and there are a number of different ways of doing it. And I don't blame you if you end up using another method if it works better for you. But the method that works best for me and for my students is this one. They absolutely love it, and I personally also loved it when I was a student myself. So the first thing we do is we convert the number of subnets required from decimal to binary. So what are the total number of networks required? You need 4. So what that means is we talked about, if you guys remember, handy dandy binary conversion chart, right? 1, 2, 4, 8, 16, 32, 64, 128. Now, if you need 4 out of these, we have to see how we can come up with number 4. Well, if this bit is on, and if all of the rest of the bits are off, that gives us a decimal value of 4. And that's exactly what we are after. Now, what we do next is we defined the network bits to create a modified subnet mask. So the default subnet mask we have in /24, by now you guys know, is 255.255.255.0, which equals a bunch of 1s in the first octet, a bunch of 1s in the second octet, a bunch of 1s in the third octet, and all 0s in the fourth and the last octet. Well, we learned from the previous step that it takes 3 bits to produce 4 networks. What that means is we're going to go ahead and borrow 3 bits from the host address. And just to quickly clarify, in /24, the first 3 octets are all network octets, right? They're dedicated to networks. And what we need to do is we need to find 4 networks, right? So what we did was this right here is the host octet, the final one. We borrowed 3 bits that match the 3 bits that we came up with here, right? To come up with the value of 4. So that's what we're doing here. And what that gives us is a modified subnet mask of 255.255.255.224 or /27. Why do we call it /27? Well, if you were to add up all these bits here, all these network bits, and by the way, network bits must be contiguous. If they're not, that's a violation of the IPv4 addressing rules. So make sure that, in other words, you can't have a network where you have a 0 here, for example, and 1, and then 0 and 1. You will never run into a situation like that ever, because that's a violation of IPv4 addressing rules. When you have all 1s like this, you should always see contiguous 1s, okay, in all of these octets. So something for you guys to keep in mind. And the 224 value is, once again, looking at the binary conversion chart where we have 1, 2, 4, 8, and all that, right? This is 128 position right here. This is 64 position. This is 32 position. If you add all that up, that equals 224. Third and the final step is we define the network range for each subnet. How do we do it? Well, we focus on the last network bit. So if you guys remember, this was our last network bit. This last network bit position, what's this position here? Let's blow it up a little bit. So we have 1, 2, 4, 8, 16, 32, 64, 128, right? So if I were to do 1, 1, 1, 0, 0, 0, 0, 0. Well, this right here is the last network bit position. That's what I'm talking about, right? Which is 32. The value 32 comes from here. It's the least significant bit. By the way, that's another terminology you guys need to be aware of. The leftmost bit is considered the most significant bit, and the last network bit is considered the least significant bit. So we'll look at the least significant bit value position, and we'll take that from the modified subnet mask, which we're looking at right here, to define our network range. So the first range ends up becoming 200.10.5.0 through 200.10.5.31. Well, how did we figure this out, and what are we doing again? Well, let's take a step back quickly. What that means is after modifying what we needed to modify in order to get 4 networks, right? Create 4 different chunks or 4 different pieces of this network, 1/24 divided into 4 different subnets. We did all this to come up with certain values, right? And if you were to pay attention to this right here, the modified subnet mask, that tells us everything we need to know. And here's what I mean. All the network bits that we have, if you look at all the zeros, these are for hosts. How many zeros we have? 1, 2, 3, 4, 5. We have 5 zeros, right? So 2 to the power of 5 gives us what? 32. That's what it gives us, right? And that's the value that we're looking at here. So what that means is we'll have 32 hosts in each subnet. And if you guys remember, we have to do 32 minus 2 to get to the value of 30. That's the usable space. That's what we call usable IP address space. Because we cannot use the first IP because that's the network address, and we cannot use the last IP because that's the broadcast address, and these are reserved according to the RFC standards. So what does that mean? What should be the next range here? Well, what that means is the next range should start with 200.10.5.32 because this value is 32 here, right? And at this point, I think we can start identifying that the one after that would be 32 plus 32 is 64. And then if we were to add another 32 to that, we'll get 96, and so on and so forth. These are all the different ranges that we'll actually end up getting. So we're gonna get, instead of 4, even though we needed 4, but the way it worked out, we're gonna actually end up with 8 networks. And these 8 networks, each network is gonna be able to support 30 usable IPs. And where does this number 8 come from? Remember the borrowed bits. What's 2 to the power of 3? How many bits we borrowed? 3, right? That's 8. These are the networks that we're going to end up getting. So as you can see, once you guys understand and get a feel for this binary conversion chart and math, it kind of becomes very cool, and you sort of like become a ninja of going back and forth and doing conversions between binary and decimal to make sense of what you're dealing with. So I've got a ton of other examples. Let's keep rolling. Example number 2. We're still subnetting networks. we got the IP address 193.9.10.0/24, and we need 60 subnets. Step 1, convert the number of subnets required from decimal to binary. So we're going to look at the number 60. We're going to do our handy dandy binary conversion chart. And after doing the math, that's what we're going to get to the number 60. Step number 2, if you guys recall, is we define network bits to create a modified subnet mask. So first we write down our default subnet mask of 255.255.255.0, and then we see the binary in front of it. Well, we learned from the first step that it takes 6 bits to produce 60 networks. What that means is we need to borrow 6 bits from the host address space in order to be able to come up with 60 networks. And this is how the modified subnet mask will look like. The modified subnet mask shows us that we've got ourselves a subnet mask of 255.255.255.252 or /30. Finally, we define network range for each subnet. So as you can see here, let me draw that out for you. The least significant bit, which happens to be this one, what's this position aligned to when it comes to the binary conversion chart up here? 1, 2, 4, right? This right here is 4. Well, that's the position we got right here. And we use this to define our network range. So what that means is our network range should start with 193.9.10.0, and the one after that should be 193.9.10.4, and the one after that would be 193.9.10.8. But where does this first range end? These are all different ranges, right? It's going to end at 193.9.10.3. Where does the second one end? It ends at 193.9.10.7. And where does this one end, the third one? 193.9.10.11. Because the next one down below would be .12, right? So I'm sure at this point you guys are starting to see a pattern here. But remember, we cannot use the first and the last IP in each range, which means we only have 2 usable IPs per subnet that we have. And how many subnets are we going to get in total? Well, 2 to the power of 6 equal 64. That's how many subnets you're going to get. So 64 subnets, even though we only wanted 60, but we ended up getting a few extra because that's how the math worked out. And within each subnet, we're only going to have 2 usable IPs. And here are all the different ranges, and it's going to continue, but you guys get the idea. Now I'm going to pick up my pace a little bit because at this point I'm sure you guys are getting comfortable with how this works. So this is example number 3, and we're still subnetting networks. So what we have here is 155.1.0.0/16, and we need 120 subnets. Now, this is a different one. Before we had 2/24s, the previous examples, right? This example is a /16, a little bit different, but the rules are still the same. So first thing that we do is we convert the number of subnets required from decimal to binary. So what's the decimal number we're after? 120. Let's do the binary math real quick. This is how the binary math works out. Step number 2, define network bits to create a modified subnet mask, right? We first of all jot down the default subnet mask, which is /16, 255.255.0.0. it takes 7 bits, we learned from step 1, to create 120 networks. So let's go ahead and borrow network bits from the host octet. And that's exactly what we did. We borrowed 7 bits. Well, that gives us a modified subnet mask of 255.255.254.0 or /23. Let's define our network range for each subnet. What's the last position? So let's quickly talk about the last position. So as you can see here, the last position, once again, if we were to compare it to our handy-dandy binary conversion chart, is in the bit position 2. And that's what we got here. And we can use this to define our network ranges. So it starts off at 155.1.0.0 all the way up to 155.1.1.255. The next range starts at 155.1.2.0 through 155.1.3.255, so on and so forth. But what I want you to pay attention to is based on the steps that I outlined above, you will see that as long as we stick to our formula here, you see we start off at 0 because that's a default, right? And then we go to 2 and 4 and 6 and 8 because here we're messing with the third octet, right? Because this is class B. So this is where we need to write things down. It's a little different than how we manage class C so far, but just hang in there with me. And I think you guys are understanding what I'm doing here. And let's talk about how many total networks we're going to get. Well, total networks would be 2 to the power of 7, and that is 128. So that's the total of subnets I'm going to get from the math I just did. Even though we only needed 120, but we're going to have a few extra. And within each subnet, we're going to have how many hosts? How many host bits do you see here? Well, we see 8 bits right here in the last octet, and then 1 additional host bit in the third octet. So altogether, we have 2 to the power of 9. And what does that give us? Well, that gives us a total of 512 hosts. But the usable would be 510 because once again, we cannot use the first and the last. So that's the total number of hosts. And that's why the range looks bigger. It starts with 0.0, but then as you noticed, the third octet changes to 0.1 and ends at 255. But the reason it goes from 0 to 1 is because the first range looks like this, 155.1.0.0 through 155.1.0 through 255, but then we don't stop, we continue. 155.1.1.0 through 155.1.1.255. So you guys see the way it works out? And the same thing with other ranges too. But I'm going to spare you the grief. And here's the last example. Once again, we're still subnetting networks. The network we have been given is class A, 89.0.0.0/8, and we need 300 subnets. Same steps. Convert the number of subnets required from decimal to binary. Well, decimal is 300. What's the binary? That's how the way math works out. Now, one little difference here you guys probably noticed. I'm going beyond our typical 128 boundary is because I needed 300 networks. And I could not create 300 networks just from the fourth octet alone. The maximum number of networks that I can get from the fourth octet is 256. Why? Because there are 8 bits in each octet. 2 to the power 8 is 256. So that's the maximum number I can get from one octet, right? but I needed 300. So I need to go above that. Well, that's where we kind of crossed over to the other boundary and went from the 4th octet into the 3rd octet in order to be able to borrow the appropriate bits and get the job done. Step 2. We define network bits to create a modified subnet mask. 255.0.0.0. And then we lay that out in binary. It takes 9 bits to produce 300 networks. That's what we saw in step 1, right? Well, let's go ahead and specify how that will play out. So because, remember, it's a /8, we only have the 1st octet with all 1s. 2nd octet through the 4th octet were all 0s before, but because we needed 9 bits to come up with 300 subnets, we now have to turn on those bits, as you're seeing in red. So the modified subnet mask equals 255.255.128.0 or /17. And the reason it's /17 is because we have 17 network bits on. And the final step, we define network range for each subnet. So let's see how that looks like. So we start off at 89.0.0.0 through 89.0.127.255. The next one is 89.0.128.0 and it ends at 89.0.255.255. Next range is 89.1.0.0, so on and so forth. But once again, the key here is that once we have identified our bit position, we can use that to our advantage and figure out how to define the ranges. Now, one thing I want you guys to keep in mind is here, because this is class A address and we're messing with the 2nd and 3rd octets, you'll actually see the values increment both in the 2nd and 3rd octets, as you can see here, which is very, very different than the /24 and /16s that we have looked at so far. So I don't want you to freak out. I want you to understand that because you're modifying the 2nd and the 3rd octet, the values are going to increment as you define your network ranges. Finally, how many subnets do we actually get? 2 to the power of 9 equals 512. And how do we know that? Well, 2 to the power of 8 is 256, right? So if you double 256, that's 512. Okay, so that's simple. And that's a total number of subnets. Once again, we only needed 300, but we're going to end up with 512, and that's fine. We needed a minimum of 300. So it doesn't matter if we end up with more. That's fine. They can come in handy later in the future. And as far as IP addressing, look at how many host bits we got. All the zeros that are left over in this modified subnet mask are actually host bits. So that's 2 to the power of 8, 9, 10, 11, 12, 13, 14, 15. 2 to the power of 15. That's a gigantic number. I'm going to have to fire up a calculator to figure this one out. It's 32,768. But remember, we'll have to do -2, so we're going to end up with 32,766 of usable IPs. Once again, these are the number of hosts per subnet. That's a lot of hosts per subnet. You should never see that many hosts on a single subnet because your network devices will melt if you had that many devices. And if you were to send broadcasts and things of that nature, not going to work. But keep in mind, we're just doing a theoretical exercise right now for your brain muscles, so you can learn how IP addressing works, because in the exam, they're going to get you on this topic, and they're going to throw some weird numbers at you. So that's why I'm going through these random examples from different classes, so you get a feel for how to subnet your networks. And this is the final section. We're going to now look at, previously we talked about how to subnet networks or create chunks from networks. Now we're going to look at how to subnet hosts. So this is example number 1. What we have is 200.10.5.0/24, and we need 25 hosts. Now it's switched. Instead of networks, now we're looking for hosts. The overall logic is going to stay the same, but I'm going to point out a few differences. First, convert the number of hosts required from decimal to binary. So if you look at the decimal number 25, we map that against the binary conversion chart, and that's what we get. Step 2, we define host bits to create a modified subnet mask. You get 255, 255, 255.0, and right in front of it is the binary numbers. It takes 5 bits to produce 25 hosts, as mentioned in the previous step, right? That's what we learned. Well, we're going to have to divvy up the host bits. So instead of focused on the network bits that we were in the previous section, in this section, we're focused on just the host bits. And this is how the modified subnet mask is going to look like once we did that. 255, 255, 255, 224, or /27. Step number 3, we define network range for each subnet. Let's look at the position of the least significant bit. Here's where the gotcha is. You may end up looking here at this last 0. No, you don't want to do that. That's wrong. What you want to do instead is you want to look, it says last network bit position, not host, network bit. Well, this is the network bit right here. Well, what does this match to when it comes to the binary conversion chart? Well, it maps to the value 32. Hence, the value 32 here. Now let's use this to our advantage to figure out the network ranges. So 200.10.5.0 is where we begin, and the next range would be 200.10.5. Well, it says 32. I'm pretty confident we can put this down. 200.10.5.64. And where does each range end? The first one is going to end at 200.10.5.31. The second one is going to end at 200.10.5.63. The third one, .10.5.95, and so on and so forth. We are not done yet, but you guys get the idea. Now, one final step that we always do, how many hosts and subnets are we going to get out of this? Well, originally we had a subnet mask of 24, and we ended up borrowing a couple of network bits in the 4th octet, and what we have is 2 to the power of 3, because we borrowed 3 bits. We're going to get 8 subnets, and we're going to get 2 to the power of 5. That equals 32 hosts minus 2, because we can't use the first and last. We're going to get 30 hosts per subnet. So we're going to get 8 subnets in total, and we're going to get 30 hosts, usable hosts, or usable IPs in total. Now let's look at the next example. 199.5.10.0/24, and we need 60 hosts. Let's go. First, convert the number of hosts required from decimal to binary. Should be pretty fast now. right? 60, we look at the binary conversion chart. That's what we come up with. Second step, we define host bits to create a modified subnet mask. Here, we got a /24, which is 255.255.255.0. Then we have the binary representation in front of it. We learned from the last step that it takes 6 bits to create or produce 60 hosts. What we're going to do is go ahead and set aside a bunch of zeros that match the number of bits that we defined in step 1. And this gives us a subnet mask of 255.255.255.192 or /26. Step 3, define network range for each subnet. Well, let's quickly take a look at the network bit position. Once again, be careful. It's not this guy. It's the network. It's the least significant network bit. So if you look at this, this is what position when it comes to the binary conversion chart. That is a position 64. That's what you got here. Now let's look at the different ranges. 199.5.10.0 through 199.5.10.63. Next up, 199.5.10.64 all the way up to 127. Third range, 199.5.10.128 all the way up to 191. Fourth range, 199.5.10.192 all the way up to 255. So how many hosts do we actually get in this scenario? But first, let's look at subnets. Well, initially we had /24, so what we did was we only modified 2 bits, right? These are the bits we borrowed from the host octet, or the 4th octet, right? So 2 to the power of 2 equals 4. So that's it. We only get 4 networks. And what do we get within each network or each subnet as far as hosts? Well, we got ourselves 2 to the power of 6, and that gives us 64 hosts minus 2, 62 usable IPs per subnet. Next example, 130.5.0.0/16. We need 450 hosts. Step 1, convert the number of hosts required from decimal to binary. Let's do that very quickly. That's how it maps out. Also notice we're kind of going beyond our regular 8-bit boundary. We're kind of in the 9th bit territory, if you will. Step 2, we define host bits to create a modified subnet mask. Here, the default is /16, so 255.255.0.0. Then we have the binary representation in front of it. It takes 9 bits to produce 450 hosts, as mentioned in step 1. So what we're going to do now is we're going to go ahead and reserve 9 bits for hosts in our subnet mask, and the rest will make that part of the network portion. And what we end up getting is a modified subnet mask of 255.255.254.0 or /23. Final step is we define network range for each subnet, and we look at the least significant bit, least significant network bit. So that would be this guy right here. So according to the binary conversion chart, if this is 1, this is 2. That's it. And this is how it looks like, 130.5.0.0 through 130.5.1.255, and so on and so forth. Let's quickly, as always, look at how many subnets in total first. Well, how many bits did we mess around with, or we actually enabled compared to, so we messed with the 3rd octet, right? The default was all zeros in the 3rd octet, right? As you can see here, but we actually messed with it. So what are the bits that we actually messed around with? We actually borrowed 2 to the power of 7. That gives us 128 subnets. How about hosts? Well, let's check that out. So 2 to the power of 9. Because we have to count up all the zeros, right? And what we get is, if 2 to the power of 8 is 256, 2 to the power of 9 must be 512, because we just keep doubling the number in decimal, right? And that's the total number of hosts. We do minus 2. We end up getting 510 usable IPs per subnet in our network. And yay, the final subnetting exercise. In this example, you're going to look at class A, 14.0.0.0/8. We need 110 hosts. Step 1, convert the number of hosts required from decimal to binary. Let's do that real quick. Step 2, define host to create a modified subnet mask. So default one is /8. That's what we got, 255.0.0.0. And then we got the binary representation in front of it. Because it takes 7 bits, according to step 1, to create 110 hosts, what we're going to do is we're going to go ahead and specify the hosts in the 4th octet in red, and then we're going to enable the rest of the bits to the left of it to all ones. Because remember, this is how it works in IPv4 addressing. Network has to be contiguous, and you cannot have a mix of zeros and ones when it comes to the network address. All the subnet bits must be ones, the ones that are considered significant bits. They must all be ones contiguously and consecutively. And what that gives us is a modified subnet mask of 255.255.255.128 or /25. Final step, define network range for each subnet. Well, let's find the last network bit position very, very quickly. We look at this guy. Well, this position is 128. That's what we got. Let's start looking at the different ranges. 14.0.0.0 through 14.0.0.127, 14.0.0.128, so on and so forth. Let's finally talk about how many networks we get first. So how many network bits did we mess with? The default subnet mask here, and look at what we did down below. We modified a lot of bits. We need to count them up. So 8 plus 8 plus 1. So 8 plus 8 is 16, plus 1 is 17. That's 2 to the power of 17. Once again, I'm going to have to fire up a calculator because I don't think I can do that in my head. That's 131,072. That's the total number of subnets we're going to get. That's a lot. How about the number of hosts? Because that's what we really cared for. Right? 2 to the power of 7. That is 128. We know that already because 2 to the power of 8 is 256. So half of that is 128. So that's the total number of hosts. But remember, we do minus 2. We're going to actually end up getting 126 usable IPs on each subnet. And one bonus topic that I want to touch base on, kind of fun, is IPv4 subnetting hack. And what I'm talking about here is, so this is my machine's IP address at home. What I have here is, this is the IP address I've got. Here's the subnet mask I got. And this is the gateway IP, also known as router IP. But don't worry about the router IP. This is irrelevant for our purpose right now. You guys will learn that in the next section when we talk about IP routing. But today, all you should be concerned with is the IP address and the subnet mask. So if you walked into a real world environment and you plugged in your machine or through wireless, you picked up an IP address, if you ever wondered how the administrator in that network came up with this strategy, and how many available hosts there are and networks and things of that nature, you can actually use this technique that I'm going to show you to kind of reverse engineer the administrator's brain and see what they were thinking when they designed the network. Let's take a look. So as you guys saw on the previous screen, my IP address is 172.27.7.35 on my machine at home. And my subnet mask is 255.255.255.192. Let's figure out how this network was designed. So here's the technique. It's a two-step process, much simpler than some of the other steps that we looked at previously. But this knowledge builds upon what we have learned so far, so it's complementary. Step 1, we figure out the last network bit position in the subnet mask. So what does that mean? So let's lay out the subnet mask. It's 255.255.255.192, right? And then we kind of write down the binary representation of it. The least significant network bit is this guy right here. And if you were to compare this against the binary conversion chart, this is position number 64. That's what we have here. Step number 2, and the final step, we define network range for each subnet. We use the last network bit position, 64, of the modified subnet mask to define network range. So what we have is 172.27.0.0. Because this is VLSM, we're not going to worry about the other ranges. So the range that we're concerned with right here is, so at my home, the IP addresses start from 172.27.7.0. Once again, O cannot be assigned to anything because that's the network address, right? And the range ends with 172.27.7.63. Once again, 63 is also unusable because it's reserved and it's a broadcast address. What I'm going to get is 64 minus 2 equals 62 hosts on this network. So this is good information to have because a lot of hackers can use this information to do what's called a reconnaissance attack, where they start gathering information about different hosts in the network. So this is a starting point. This will give them an idea of how large the network is and what information and value they can extract out of the network. As a disclaimer, I'm not encouraging you to become a hacker, but rather the opposite. I'm getting you excited to become a security expert because in order to become a security expert, you have to reverse engineer a hacker's brain. Welcome to CCNA 200-301 course. Today, I'll cover Section 3, Part 2, IP addressing and routing. We'll do a deep dive into IPv4 routing. Here are the topics I plan on covering today. First, IPv4 routing overview. Second, fundamentals of IP routing. And finally, I'll wrap it up by providing a quick overview of different types of static routes. First, let's look at IPv4 routing overview. What is routing? At a very high level, routing is about forwarding packets from the source to the destination. If you guys remember the OSI model, IP addressing lives at layer 3 of the OSI model, at the network layer. And routing is all about sending packets from one device to another device. So if we were to look at this topology here, in this instance, Bob at the top wants to send an email to Sal at the bottom. What Bob will do is it's going to be the source because that's where the email is originating. And Sal will be the destination. So from a routing perspective, in order for Bob to be able to successfully send an email to Sal, he's going to need to do IP routing in order for him to be able to successfully deliver the email message. Now, I'm going to come back to this slide momentarily because there's a bunch of concepts that I would like to clarify as we continue moving forward. Now, the type of routing we're going to be talking about here today is called unicast routing. There's also something called multicast routing. That's a topic for another day. Today, our goal is to focus on unicast routing, and routing is based on destination. It's all about getting to the destination. So if you think about, the best analogy I can give you is a GPS. If you have ever fired up and used a GPS on your smartphone, then you know that when you do that, you become the center of the universe as an individual. So you become the source. And where you want to go, the destination you want to get to is the destination, right? So similarly, each layer 3 device in our network that needs to send information to another device ends up becoming the source, and the other device on the other end is the destination. And that's what routing is all about. Now, layer 3 devices include end hosts. So that's your PCs, IP phones, printers, IP cameras, any type of device that is able to communicate IP, that also includes switches and routers and firewalls, etc., must know where the destinations are, right? So every single hop, so for example, if I'm in San Jose and if I want to send an email to somebody who's in New York, well, physically, there's going to be a bunch of routers in between us. And every single device, every single layer 3 hop between San Jose, California to New York needs to have information about the destination so it can actually route my traffic to the eventual destination, which in this case is SAL. And once again, I'm going to come back to this slide because there's a couple of concepts that I would like to crystallize. So what ends up happening is, how did Bob know how to send information to SAL to begin with? Well, there's something called a binary AND operation that is ran on the devices. And all layer 3 devices run this binary AND operation. The first thing that happens when that operation is ran is the layer 3 device looks at its own IP address and its own subnet mask and run the binary AND against it. Then what it does is it takes the destination IP address and its own subnet mask and then runs a binary AND against it. And if the resulting value is identical, then that means we're on the same subnet. And if that's the case, then the traffic is sent directly to the destination. If the resulting value is not identical, then that means we are on different subnets. And in that case, the packets are sent to the local default gateway. Now, to continue building on this, there's something called a binary AND operation logic truth table. That tells us how the overall binary AND logic actually works. So let's quickly take a look at it. Let's assume value A is the IP address, and value B is the subnet mask. What ends up happening in this case is that we look at the binary number, whether it's 0 or 1, right? Binary is either a 0 or a 1. So if the IP address is 0, and if the bit on the subnet mask side of the house is 0, then the end result is 0. If the binary bit is 0 for IP and it's 1 for subnet mask, the result is still 0. And remember that there is an implied AND because we're looking at the AND operation inserted in between A and B. So it's the binary AND operation. If the IP address is 1 and subnet mask is 0, then the result is 0. If IP address is 1, if the subnet mask is also 1, then the result is 1. So if you look at the two bullets at the bottom here, if both inputs match 1, the result is true and the value is 1. In all other variations, the result is false. So that's how the binary bit logic works. Now, under this context, let me take you back to the first topology that I was showing you earlier to help crystallize how this works. So if you were to look at these two IPs here, Bob wants to send an email to Sal, right? So Bob's IP is 172.16.0.1, and it wants to communicate with 172.16.0.2. Well, what did we learn? What we need to do first is we need to look at the source IP, and we need to run a binary AND against it. So what that means is, let me do quick whiteboarding. 172.16.0.1, this is Bob's IP, right? And the subnet mask is 255.255.255.0. Well, we need to look at these from a binary perspective. So what's 172 in binary? So let's quickly do the binary math here. So 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. If you guys remember the binary decimal conversion chart, that's what I'm going to explain here. But I've done that already in my last video. I'll provide a link up at the top. You can either tap or click on it, and you can go and look at that video that I did. So you can learn at a much deeper level how this works. But here I'm just giving you a quick overview. So 2 to the power of 0 is 1. 2 to the power of 1 is 2, 4, 8, 16, 32, 64, 128. And if you were to draw a line here, what we want to do now is look at 172.16.0.1. So we're going to have to look at each octet here in this IP address and map it to this binary conversion chart. So what's 172 in binary? Well, let's figure that out. So if the first bit, if the 128 bit is set to 1, if the 64 is also set to 1, it's going to go over 172. So we're going to have to set that to 0. 128 plus 32 is 160. So this is also going to be 1. If we also enable 16, that would be too much. It's going to go beyond 172, so we're going to have to set that bit to 0. The one right next to it is 8, so a total of 168. We need to get to 172. Well, this bit, if you also enable this bit and set the rest of the bits to 0, we'll get a decimal figure of 172. How about 16? Well, let's do that as well. So 16 means these bits are going to be off, 16th position is going to be on, the rest are going to be all zeros. What about 0? Well, that's a very simple one. It's going to be all zeros. Love the simplicity. And then what about 1? Well, it's going to be all zeros followed by a 1. So now, let's take this binary math and line it all up. So let's do that. 1, 0, 1, 0, 1, 1, 0, 0. That's 172. What about 16? 0, 0, 0, 1, 0, 0, 0, 0. What about 0? It's going to be 8 zeros. And then what about 1? It's going to be 7 zeros, 6, 7, followed by 1. And then what about 255? Well, 255 means all the bits are on. So we're going to do that. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then 0 means it's going to be all zeros. Well, what we need to do now is we need to very quickly here look at the end result. So if you guys remember the binary logic, the truth table, 1 and 1 is 1. But 1 and 0 will always be a 0. 1 and 1 is 1. 1 and 0 is 0. 1 and 1 is 1, and 1 and 1 is 1, 0, 0. Then we get 0, 0, 0, 1, 0, 0, 0, 0. Then a bunch of zeros in the third octet. 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So what this gives us, if we were to convert this into decimal, is 172.16.0.0. So that means that this is our network address. And that was the whole point of Bob's PC running this binary AND operation in the background. All it was trying to do was trying to determine its own network address. So it knows that its network address is 172.16.0.0. So now let me go back to the slide we were looking at. So it knows that the network address is 172.16.0.0. So that's first step, right? So Bob's first step is to determine its own network address. Second step is to take the destination IP and run it against its own subnet mask. So that's step number 2. Well, let me save you some math and let you know that the end result is going to be the same, which means they're both on the same subnet. And because both PCs are on the same subnet, Bob now knows that it has the ability to communicate directly with Sal without having to go through an intermediary gateway device. So it doesn't need a default gateway. Bob can communicate directly with Sal because in between we got a layer 2 transport network, which is seamless to Bob. It might as well be a one long wire running from Bob's PC all the way to Sal's PC. So that's a level of transparency that we're getting from these switches here. And that's how the binary AND operation works. Now there's one more concept that I want to clarify, and that is, if you guys recall, and I want you to picture the OSI model in your head, at layer 3, at the network layer, that's where IP addressing lives, right? And IP addressing is basically logical addressing. And at OSI layer 2, that's where MAC addressing lives. Well, we have to map the two together in order for the communication to occur. And the way it happens is through a protocol called ARP, or Address Resolution Protocol. And all layer 3 devices on our network maintain an ARP table, which is a mapping of an IP address to a MAC address. And ARP allows us to create a new layer 2 frame. It's also called layer 2 packet rewrite. But before I go too deep into this, I'm going to actually give you an example of how this works. Until then, let's park it. Always remember that ARP request is a broadcast, whereas ARP reply is a unicast. And we just talked about the binary AND operation, right? The whole idea of running the binary AND operation by the layer 3 devices in our network is to determine who to ARP for. Because ultimately we need to decide, are we ARPing for another device on our local subnet? And how's that determined? Well, if the destination IP matches my subnet when I run the IP AND operation, then that means the final destination is local to me. So I'm going to ARP for my final destination locally. But if the destination IP doesn't match my subnet, then that means I need to go and talk to my default gateway or a router in the middle, also known as intermediary router, and let that router figure out to get me to the final destination. And one final thought, guys, before I go back and explain to you using the topologies you were looking at earlier, this ARP process is repeated at each layer 3 hop throughout our network. So if there are 10 routers in the middle, every single router in the middle of our source and destination is going to run the ARP process, assuming it's an Ethernet network. Now let me quickly go back to the topologies and explain how this works. So now I'm going to be very quick. Step number 1, I'm sure you guys remember at this point, Bob's PC has to run a binary AND against its own IP and subnet mask. It finds out that it's on subnet 172.16.0.0. Second step, it takes Sal's IP and its own subnet mask and runs the same AND operation, and it finds out that Sal also happens to be on 172.16.0.0. Well, what it finds out by running these two operations is that they're both on the same subnet, and because they're on the same subnet, Bob ARPs for the destination directly, which happens to be Sal in this case. And let me quickly explain a quick review of how ARP works. In order to understand how ARP works, let's quickly zoom into an IP header or an Ethernet header. So what an Ethernet header would contain is the layer 7 information, which happens to be email in this case. Then we'll have the layer 4 header information like TCP. In this case, we'll have the layer 3, and then we'll have the layer 2. Now, if we were to zoom in to layer 3, we're going to have the source IP of Bob. We'll have the destination IP of Sal. However, when we look into layer 2, we'll have a source MAC of Bob, because Bob is the originator, and then the destination MAC of, if you were thinking Sal, you would be incorrect. It would actually be, if they're talking to each other for the first time, they've never communicated before, then what's going to end up happening is the destination is going to be set to all Fs by Bob. And all Fs is basically a layer 2 broadcast. So every single device on that VLAN at layer 2 or that subnet at layer 3 is going to get that broadcast. Well, in this case, the only other device on this network is Sal. So Sal is going to get that. It's going to look into layer 2 and layer 3, and by looking at layer 3, it's going to see that the destination IP is itself. It's going to realize that this message is meant for him. He's going to go ahead and respond back to Bob by providing its own MAC address, which ends in B. And Bob will get that, and Bob will build its ARP table. Sal will also update its ARP table. What that also does for us in the middle is that switch 1 and switch 2 will also build their MAC address tables when this happens. And let me quickly show you the CLI of how this looks. So here I am on Bob's PC. I'm going to do ipconfig/all. By doing that, I'm looking at a couple of different things here. First of all, I'm going to focus in on Fast Ethernet 0. That's the main interface I care for. My IP address, my subnet mask, and my physical address, which ends in .a. So that's Bob. Now let's also quickly take a look at Bob's ARP table. And Bob does not have any entries in its ARP table at the moment. Let's go ahead and quickly check out Sal. So here I am on Sal. I'm going to do ipconfig/all. And when I look at the Fast Ethernet 0, I see that my MAC address ends in B, which matches the diagram. The IP address matches, and the subnet mask matches. Now, let me also quickly take a look at the ARP table on this PC. And there are no ARP entries. Now let me go ahead and ping on Bob's PC. I'm going to go ahead and ping Sal. So 172.16.0.2. and it's successful. Beautiful. Let's quickly look at our ARP table again and see this time around our ARP table is populated. And as a matter of fact, not only we can see the IP address of Sal, but we see the physical address that ends in B also being populated here. And now that we have the ARP table built, Bob will have the ability now to construct a layer 2 frame and start sending information directly without using any other intermediary layer 3 device. And this is actually called transparent bridging, this whole process, because we're not using any other layer 3 device in the middle, and the switches are not manipulating any data. They're not changing the layer 2 header information. The layer 2 header information stays intact between Bob and Sal. And this is what's known as transparent bridging. Now let's quickly take a look at the other topology where we have a router in the middle to kind of go a little bit deeper into this stuff. Now in this example here, we've got two separate subnets. We've got a subnet on the left and we got a subnet on the right. And I have this imaginary kind of dotted line in the middle to differentiate between the two subnets. Now, if you look at Bob's IP and if you look at Sal's IP, on the surface, you might think, well, 172.16.0.1 and 172.16.0.17, they got to be on the same subnet, right? That's what it seems like. Well, but pay very close attention. You see the /28. It's not /24, it's /28, which makes the overall subnet very small. What's /28? 255.255.255.240. So it only gives us 16 possible IP addresses in the network range, and out of 16, if we were to subtract 2, because we can't use the network address and the broadcast address, the very first address in any IP range is a network address, and the last one is a broadcast address, and we cannot use them based on the IP rules, we end up getting only 14 usable IPs in each of these subnet ranges. And that's what we're seeing here. I wanted to trick you a little bit. I wanted to see if you were actually paying attention. And guys, just taking a step back here, remember, network engineering is all about paying attention to detail. At the end of the day, unless you pay attention to detail, you're never going to become a good network engineer. That's the number one trait that you need to develop as a network engineer, paying very close attention to every single thing that's happening on the screen, to the topology, to the configuration of the devices, everything, to make sure everything properly matches. So that being said, now let me explain how this scenario is going to play out compared to the previous scenario where we didn't have the router. So in this scenario, Bob wants to send an email to Sal. So what's going to end up happening is Bob's PC is going to run a binary AND operation against its IP and subnet mask. And it's going to realize that it's on a network 172.16.0.0/28. Next, it's going to take Sal's IP address, which ends in .17, and run a binary AND against its own subnet mask of /28. And what it would realize, and let me save you a lot of math and time here, is that it's on 172.16.0.16/28. Because these two subnets do not match, there's actually a mismatch. What ends up happening in step 3 is that we send packets to the default gateway, which in this case happens to be the router here. But before we do that, we need to ARP for the default gateway. And when we inspect the ARP packet, that's what we see. We see the payload, which is data. We see layer 4 information, which in this case would be TCP, SMTP in particular, because this is email. And then we'll have layer 3 and layer 2 header information. If you were to zoom into layer 3 header information, we'll have the source IP of Bob's PC. We'll have the destination IP of Sal's PC. We'll have the source MAC of Bob's PC. And the destination MAC is going to be set to what? All Fs, right? Because we just finished talking about ARP. So initially it's all Fs, which is a layer 2 broadcast. And it's sent out to all the hosts on the same VLAN or all the hosts on the same subnet at layer 3. Everybody gets it. Only the device that is supposed to respond back is going to respond back. And at that point, these all Fs in the subsequent packets will be replaced with router's interface number 1. The interface pointing to the Bob's PC here. This interface right here. The next thing the router is going to do is it's going to realize that the destination IP is pointing to Sal's IP. And lucky for the router, Sal's IP happens to be directly connected on router's interface number 2. So what it's going to do is it's going to go ahead and decapsulate the packet and re-encapsulate it. And I'm going to explain the process in a moment here. But when it goes ahead and does that, it's going to retain the data, the layer 4 information, and the layer 3 information. The only thing that it's going to change is it's going to go ahead and rewrite layer 2 header. Because remember, we're swapping interfaces here. So because the interfaces are being swapped, it has to do what's called a layer 2 packet rewrite in order for the packet to be transported across 2 different networks and 2 different interfaces. Now, if we were to zoom in to this packet right here, here's what we're going to see. The source IP of Bob's IP, source IP didn't change. Destination IP didn't change either. This is Sal's IP. But what did change is the source MAC. In this instance, the source MAC is going to be router's interface number 2. And the destination MAC in this instance is going to be initially all Fs because it has to determine Sal's MAC address and all that. So it's going to go through the whole jazz that I've discussed so far. And eventually it's going to get Sal's MAC address back. It's going to populate its ARP table, and all the consequent packets are going to have the destination MAC set to Sal's MAC address. And now at this point, there's sufficient information for the router to be able to go ahead and send traffic. Now, another thing that the router had to do behind the scenes is it would actually have to look into the layer 3 routing table because it's 2 different subnets. So it's going to look at the source subnet and the destination subnet and its routing table, and then formulate the packet accordingly, which is the layer 2 packet read-write process, so the information can flow from one end to the other. Now, another thing to keep in mind is Sal's PC also has to do the same thing in reverse in order to be able to find its way back to Bob's PC. Because remember, it's a per hop idea, and it's also a directional idea. So each direction, so from Bob's perspective, we have directionality that is pointing us into Sal's direction. But then the opposite is also true. Sal has to go through the network in order for it to be able to find its way back to Bob. So naturally, it has to go through the exact same process of running the AND operation on its IP, then running the AND against Bob's IP, using its own subnet mask, and then it's going to have to ARP for the default gateway, and the same thing is going to have to be repeated all over again. And eventually, the ARP tables are going to be built end to end, router in the middle is going to have its ARP table populated for both sides of the subnet, and we're going to have end-to-end connectivity. So now that we understand the mechanics of IP routing, we're going to quickly take a step back and do a 10,000-foot overview of the fundamentals of IP routing. There are two components of IP routing. First is determining the optimal path, which is called the routing protocol, and the other is transporting packets through a network. That's called routed protocol. Now let's quickly zoom into each. Routing protocols are used to establish a communication channel that helps the layer 3 device or router determine the best path. Examples are routing information protocol, enhanced interior gateway routing protocol, open shortest path first, intermediate system to intermediate system, and border gateway protocol. Routed protocol, on the other hand, carry the actual data. They are the ones that are carried across the network. Examples include IPv4 and IPv6. Now, a very quick analogy that I can give you that helps me understand these protocols very easily is you can think of a routing protocol as a road, like a highway. And what you have on a highway is a bunch of cars. You may have the big cars, a big truck, different type of vehicles, right? Those vehicles you can consider as the routed protocols, whereas the road itself could be considered a routing protocol, because road is what's providing the communication path, the transportation path. If you want to go from San Jose, California to Chicago, Illinois, the path you take is the routing protocol. But the vehicle that you're using to get there is the routed protocol. So hopefully this kind of crystallizes the concept in your head a little bit. What's the job of a routing protocol? Let's quickly talk through that. First, IP protocol learns IP routes from neighboring routers. Second, it advertises IP routes to the neighboring routers. Third, if more than one path exists to one destination subnet, the routing protocol picks the best route based on a metric. If something changes in our network topology, meaning a circuit goes down or a link failure, interface dies, we remove the path from our local routing table. That's what the routing protocol does. Then it advertises the change so everybody else in the network knows that, hey, this link went away. Don't use this path because it's dead. And instead, we look for an alternative path. Now, these three last steps that I just talked about, this process is known as convergence, where interface went down, we advertise the change to others so everybody knows that the network is down. And then we do a quick calculation to figure out how to route to the same destination using a different path. That's called convergence. There are two major categories of routing protocols. First is called Interior Gateway Protocols, or IGP. That's the type of routing protocol that's used inside a single autonomous system. An autonomous system is a single administrative domain. So you can think of it as the company you work for. It's a single organization. So that would be considered a single autonomous system. And the examples of IGPs include RIP, EIGRP, OSPF, and ISIS. EGP, on the other hand, or Exterior Gateway Protocols, is where you have different autonomous systems in the mix. And the administrative domain here is multiple organizations instead of a single organization. And there's only one EGP on planet Earth. It's called BGP, or Border Gateway Protocol. So here's a quick real-world view of how IGPs relate to EGPs. So let's assume I have this company called Notch Corp, and my very first location opened up in San Jose, ended up becoming a data center. This is the public IP that I have. and I'm running OSPF internally between the routers. So this becomes one autonomous system. And then I have another location. That's another company that I just bought in Chicago. And this is the public IP that I have for this location. And I'm internally running EIGRP between the routers to route. As you can see, San Jose is running OSPF, but Chicago is running EIGRP. It doesn't really matter because each of them are their own domains, right? Administrative domains. So that would be considered an IGP operation here within this cloud, IGP operation here within this cloud. And what each cloud has is a leg, an internet circuit into a service provider. So Chicago has an internet circuit into an ISP, and so does San Jose. And there's a BGP peering that we have with the service provider routers. And Chicago connects to ISP1. ISP1 internally runs OSPF. ISP2, on the other hand, that's connected to San Jose, runs ISIS. And then the ISPs interconnect with each other over BGP. And then there are different autonomous system numbers. As you can see, Chicago has the autonomous system number of 111. ISP1 has BGP ASN of 222. ISP2 has BGP ASN 333, whereas San Jose has BGP ASN of 444. Now, a couple of things I want to bring to your attention. So each one is running an IGP, each cloud, within their own administrative domain. But the common thread that interconnects everything, as you can clearly see, is the BGP. BGP is the thread that interconnects all of these sites together. And BGP is how the internet exists today. Internet wouldn't exist if it wasn't for BGP. So BGP is an amazing and very powerful routing protocol that allows the whole world to connect with each other. And that's the difference between IGPs and EGPs. Now, a quick tidbit for your information, we can get public IPs from an organization called ARN, American Registry for Internet Numbers. And we can get public IPs from ARN. We can also get, these would be IPv4 IPs, of course. You can also get IPv6, but IPv6, that's a topic for another day. And we also get BGP ASNs from ARN as well. And these are public BGP ASN. You can also have a private BGP ASN, but that's beyond the scope of this exam. But here, both BGP ASN and public IPs can be obtained from ARN in North America, but then other regions like APNIC for Asia, and there are others for Europe and all that. You basically go to those local authorities to obtain the IP addresses and BGP autonomous system numbers. Now, that's just a little tidbit. It's not necessarily related to IGP and EGP, but I just wanted to throw it out there for some real-world knowledge. Now let's quickly take a look at routing classification and types. There are two routing classifications: classful routing, type of routing that does not have support for VLSM. This is the old school, like class A, B, C. Watch my previous video to learn more about these classes. Classless routing, on the other hand, supports VLSM, which stands for Variable Length Subnet Masking. And the examples are RIP, EIGRP, OSPF, BGP, and ISIS. Routing types. There are two different types of routing. Static routing. This is how we manually type in the routes. And it's designed to define fixed paths. It works well in small environments where traffic is predictable. The other one is called dynamic routing. That's the preferred mechanism. That's the type of routing in which routes are learned auto-magically. Dynamically adapts to the changes in the environment. And the internet wouldn't exist today if it wasn't for dynamic routing. And examples are BGP, OSPF, all these routing protocols are dynamic routing protocols. Whereas if you were to manually type in a static route command, that would be considered static routing. There are different types of routing algorithms. First, distance vector. Distance vector protocols are also called Bellman-Ford algorithm, named after their inventors. They send routing updates to their neighbors. Distance vector protocols send large updates to the neighboring routers. Each node running distance vector protocol only knows about its neighbor. Distance vector protocols conduct routing by a process called routing by rumor. So what that means is, if the neighbor is advertising false information, we'll accept it, because that's what routing by rumor means. If it's a rumor, it's a rumor. We don't know any better. Because our neighbor is saying it's truth, we'll assume it's true, and we'll advertise that information to the rest of the environment. Examples include RIP, IGRP, EGP, and BGP. Link state. Protocols, also known as shortest path first or SPF algorithms, they flood routing updates to all the routers in the entire network. So the idea here with link state is that all the nodes, all the routers in the entire environment know about everybody else. And small updates are sent to the routers in link state because everybody knows about everybody already. And each node has an entire picture of the entire network. And the examples include ISIS and OSPF. Link state routing protocols are taxing on the routers and layer 3 devices that these protocols are running on, because each device, each node needs to have an entire picture of the entire network. So something to keep in mind. The final type is called balanced hybrid or advanced distance vector. They have characteristics of both distance vector and link state. Hybrid routing protocols send only incremental updates similar to link state, but only to its neighbors like distance vector. Example includes EIGRP. Now, how does routing table work? Let's quickly talk through the decision-making process in the order of operation. So the order of operation that I'm going to show you here is important. First order of operation is prefix length. The longest prefix match is the best and most specific route and is always preferred in the routing table. This criteria has the highest preference and it trumps all other route attributes. The next thing that the router looks at, if the prefix length is the same for different routes in our routing table, is administrative distance. If there are multiple routes to a destination with the same prefix length, the route learned by the protocol with the lowest administrative distance is preferred. Administrative distance is locally significant and does not get advertised, and lower number is considered better. So lower AD equals high priority. Administrative distance can be manually manipulated as shown below. So for example, here's a sample config, right? So if you're in a router, we can type in router OSPF 1, and then under the router OSPF configuration, we can change the distance to 70, for example, and that would change the administrative distance of the OSPF routing protocol on that router. And the final criteria is metric. And if the administrative distance, subnet mask, and prefix length are all the same for multiple routes, then the lowest metric is used to choose the best route. RIP uses the metric of hop count. OSPF uses the metric of cost. And EIGRP uses what's called a composite metric or K values. And the default is bandwidth and delay for EIGRP. If administrative distance, subnet mask, and metric are all the same, then the router starts load sharing on that link. Now let's quickly take a look at the administrative distance table. And here are the default values. Connected interface has an administrator distance of 0. Static route has an AD of 1. eBGP has an administrator distance of 90. EIGRP has an AD of 90. OSPF 110, ISIS 115, RIP 120, and unknown is set to 255. Now, administrative distance is the believability. So the connected interface is always the most predictable and the most believable because that is literally connected to the router, right? It's physically there or logically there. Static route is a route that an administrator manually types into the router. That's also pretty believable. But as you can see, with dynamic routing protocols, the believability decreases with different types of routing protocols. So that what that means is if we have static routes configured on our router, most likely our static routes will be considered preferred over the dynamic routing protocols. Now, let's quickly look at IGP comparison chart. So there are 6 different features that I want you to look at. First of all, these 3 routing protocols, they're all classless. RIP version 2, EIGRP, and OSPF. From an algorithm perspective, RIP version 2 uses distance vector, EIGRP uses advanced distance vector, and OSPF uses link state. They all support manual summarization. RIP version 2 is vendor agnostic, meaning it's multi-vendor supported. So is OSPF. EIGRP, on the other hand, used to be Cisco proprietary. The reason I have an asterisk here is because in 2013, EIGRP was made public, meaning other vendors can now also implement EIGRP in their code and in their network operating system and run it. But I think Cisco took so long to actually make that happen that I don't think there's any adoption in the industry. In other words, nobody really cares to implement EIGRP in their routers. Cisco should have done it a long time ago when EIGRP had just come out. But, it is what it is. Routing updates are sent to a multicast IP address on all 3. And from a convergence perspective, RIP version 2 is slow. EIGRP is very fast because it has a concept of successor and feasible successor, which means it has the primary path and the secondary path in the routing table available all at the same time, and it doesn't have to recalculate. It's very, very fast. So switch over, and OSPF is considered fast. Now let me give you a quick overview of static routes. So a static network route or static route is composed of 2 different pieces. Piece number 1, it's a manually configured route that defines a subnet or an entire class A, B, or C network. Next, you can either specify an outgoing interface or a next hop IP. So here's how the syntax looks. On the router, and we'll do this in CLI in a moment, here's what we type in. On the router, we type in IP, route. We specify the network that we need to specify. We specify the subnet mask of that network. And then finally, we specify the next hop IP address. So the next hop IP, this is the subnet mask, this is the network address, and then these are the keywords, IP route. And that's how we create a static route on a router. Here's another example where instead of the next hop IP, we have the local interface specified. Specifying the next hop IP in the static route is considered a best practice design. Specifying an Ethernet interface, for example, is not considered good because if it's a point-to-point interface, you're fine. But if it's not a point-to-point interface and if it's like an Ethernet segment with multiple devices on it, every single time you're expected to route traffic to that interface, it's going to generate a broadcast, and that broadcast will be sent out to all the devices. So it's not considered good practice to specify an interface. Instead, you should always have a next hop IP configured. Reviewing the show IP route command shows a different output in the routing table for each of the static routes configured above. So what I'm saying is that for each of the IP route statements that we have specified here, whether we have the next hop IP or the interface specified, the output is going to look different. And I'll show you that in a moment. When the router interface associated with static route fails, the router automatically removes the static route from its routing table. So now let's quickly go to the CLI and look at this stuff. Now let's quickly take a look at this routing scenario here right in front of us. So about router 1 right now, and I'm going to go ahead and take a look at show IP interface brief to see what's going on. And it seems like I have an IP address of 10.0.0.1 configured. See if I can ping the other side, which happens to be 10.0.0.2. And it seems like I'm able to successfully do that. So router 1 is able to ping router 2. Now router 2 happens to have a couple of different routes. 192.168.0.0/24 and 192.168.1.0/24. Two separate subnets behind its LAN. Now router 1 by default is not going to have the ability to see those routes. To verify that, we'll look at show IP route. This is the routing table. And as you can see here, routing table has this codes section. So what we can see right below that is the different networks that are in our routing table. And C corresponds to the flag or the code up here in the table, which stands for connected. So this right here is a connected route, and it's on our interface gigabit 000. And this happens to be the /30. Our local route, which is the L flag here, is 10.0.0.1/32. Now this is called a host route because it's a very specific route. It's a /32. And it's also directly connected over gigabit Ethernet 000. So if you guys remember the administrative distance chart we were looking at, this has an administrative distance of 0 because it's directly connected. It's considered to be the most believable. Now, we got a bit of a problem here. We cannot see the routes that router 2 has, these 192.168 routes. Now, before we do anything, let's quickly jump to router 2 and look at show IP interface brief, make sure everything is up and running. And indeed it is. And what I've done is I'm representing these routes as loopback interfaces because it doesn't really matter. I mean, I could have other layer 3 devices hanging off of this router if I wanted to, but I'm just trying to simplify the configuration here, and it doesn't make any difference whatsoever. Let's quickly take a look at show IP route. So if I do that, I will see that I have a bunch of routes that I've specified. Once again, for every route or for every interface, I'm going to see two different entries. One is the host specific entry, and that has a flag of L right next to it. And then I'll see another entry, which is the C entry, the connected route. And that is the network that I specified when I was configuring my interface. So let me quickly show you what I mean. So if I were to do show run, let me show you how I've specified these interfaces. Loopbacks are /24s, as you can see here. The gigabit 000 is actually a /30 because it ends in .252. Now, if I were to look at the show IP route, the reason we're seeing the loopbacks with /24 and /32 is /24 represents the subnet that I typed in here, right, which was .0. But because I have specific IPs on the interface, it automatically inserts a host route. So this is not something I inserted. This is the operating system automatically inserting the host route just so it has a specific entry in its table. So I just wanted to quickly point out that distinction. Now let me jump back to router 1. We still have a problem. I can't ping, for example, one of these subnets that router 2 has on its LAN side. And I'll prove to you that I can't ping either one of them. Both networks are currently unavailable on router 1. And the reason is router 1 doesn't know where those routes are and hence is unable to get to those destinations. So let's go ahead and enter those routes manually. That's what's called static routing. We'll go ahead and set that up. So IP route 192.168.0.0. Then I'll type in the subnet mask, and finally I'll type in the next hop IP here, which for us is 10.0.0.2, which happens to be the router 2's interface pointing toward us. Now let's go ahead and do ping 192.168.0.1, and voila, we have much better luck this time around. Now, if you were to look at show IP route, you'll clearly see that we have an S flag, which stands for static, meaning I manually typed it in. And as you can see, it clearly spells out the network address, the subnet mask, and the fact that it has an admin distance of 1 and metric of 0. So it's very, very believable. Of course, directly connected will always be preferred, but then right after that would be the manually typed in static route. And it specifies the next hop IP that we typed in of router 2. Let's go ahead and now add the other route, IP route 192.168.1.0, 255, 255, 255.0. And this time around, instead of specifying the next hop IP, I'm going to go ahead and specify my local outgoing interface toward router 2. And as you can see here, the operating system on this router is giving me a grief. It's barking at me. It's saying default route without gateway, if not a point-to-point interface, may impact performance. And that's what I was alluding to earlier, that we're going to have a lot of ARPing going on. And if it's not a point-to-point link, we might have performance issues because our ARP table is going to get pretty big and we're going to have broadcasts going to different devices. Now let's go ahead and look at our show IP route again. And this time around, as you can see, it appears in our routing table a little differently. The first part is the same. So the network and the subnet mask is the same, but this time around it says it's directly connected. And once again, directly connected is preferred over the static route, but remember, this is not a good practice. This is actually a bad design to specify a next hop interface instead of the next hop IP, but I just wanted to show you two different ways of doing this. And one final thing is to do a quick verification check and make sure we're able to reach the new subnet that we just added. And indeed, we are able to do that. Now let's quickly take a look at show ARP. And sure enough, we have those IPs specified in our ARP table. And one final thing I want to talk about today is static host route, also known as a host route, a default route, and a floating static route. Let's start off with static host route. That's a route that points to a single host address, as I showed you earlier. So in this instance, instead of specifying a network address, this is a spin on it. So instead of a network address, you see we're actually specifying an exact IP address. That's what makes it a host-specific route. And look at the subnet mask. It's a /32. Once again, another thing that makes it a host-specific route. And then we're specifying our next hop IP. Host routes are preferred if you know that that is the only device that you'll be communicating with on the other side of the network, and you're never going to expect any other device on that network to be able to communicate with you. Then host routes is the most beautiful way because it's least taxing on your router from resources perspective, CPU, memory, and all that. Next up is default route, also known as static default route. But commonly in the real world, you would call it a default route. Default route is a router's gateway of last resort. It provides a path for traffic that does not match anything in the routing table. The way we specify it is we type in the command IP route 0000 followed by a bunch of zeros, and then we specify either the next hop or our outgoing interface, and there you go. Anything that does not match our routing table will automatically send that traffic to the next device that's connected to us and let that device take care of the traffic for us. Here's another syntax, alternative syntax. Instead of specifying outgoing interface, you're specifying the next hop IP. And finally, the floating static route. Now, this is a hidden route that can be used as a backup route. For example, you might have a static default route pointing to your primary MPLS link. But when that MPLS goes down, you may have a backup internet route. So as you can see, we're specifying a route in our routing table by typing in IP route 192.168.1.0/24 with the next hop. And here's what's different. We're specifying a value of 200. That's administrative distance. So what we're saying is when the primary static route that we had manually typed in as primary, when that one disappears, we want this route to show up. So meaning when the MPLS link goes down, and let's assume this is an internet circuit or DIA, dedicated internet access circuit, we want this route to show up instead so we can start routing traffic across this link. And that's what floating static route does for us. Now let's go ahead and quickly take a look at these different types of static routes we just finished talking about. The first one we're going to look at is the static host route. So first of all, let's look at the interfaces on this router. We'll do show IP route. And what we're seeing in our show IP route are the different routes. We have a connected route, we have a local route. These are both connected and local are automatically added by the router. We don't have to type them in, whereas the routes with S in front of them are the ones that we have manually added. These are the routes that we had added a little bit ago. So what I'm going to do is I'm going to go ahead and remove one of these routes and instead specify a host route. So to do that, I'm going to go ahead and look at show running configuration and see what I had done in this config. So these are the two routes that I had specified. So I'm going to go ahead and remove the bottom one with the interface specified as the outgoing interface, because remember, that's bad design. So we're going to go ahead and remove that route very quickly here. We're going to go to global configuration mode, type in no, and go ahead and copy and paste this command. And here we are. It's gone. Now let's go ahead and type in a static host route. So if you guys recall, a host route is a route that is very, very specific. So it's a /32 route. So we're going to go ahead and specify that, and we're going to provide our path to get to that route, which is the next hop IP, and we're going to go ahead and hit enter. Now, if we were to look at show IP route, we see that we actually now have a host route pointing to the LAN on router 2, which happens to be the bottom one, the bottom LAN, 192.168.1.0/24. So let's go ahead and ping 192.168.1.1, only if I can type today. And sure enough, we're able to ping that IP. What you want to do next is look at static default route. So instead of specifying specific routes, we can have what's called a default route. So that's a catch-all route. So what that means is whenever nothing matches specifically in my routing table, I'm going to go ahead and send my traffic to that next hop that is specified via the default route. And it's essentially the gateway of last resort. It's basically specifying a default gateway for us on the router. So let's quickly go ahead and take a look at our show running config. And let's go ahead and remove both of these routes from our routing table. Because instead, what you want to do is you want to specify a default route. So I'm going to go ahead and do that. I just removed both of the static routes that I had manually configured. Let me do show run, and I shouldn't see those routes in my configuration anymore. So I'm going to go ahead and type in IP route 00000. It's all zeros, and then we specify the next hop IP. So the next hop IP for us is 10.0.0.2, and I'm going to go ahead and hit enter. At this point, if I were to do show IP route, what you're going to see is we have a static route and there is a star right next to it, which makes it a candidate default route, which means whenever we get packets that do not match anything specific on our router or in our routing table in particular, we're going to go ahead and forward that traffic to 10.0.0.2, which is router 2. Now let me go ahead and ping 192.168.0.1, which happens to be a LAN subnet on router 2. And if I can reach those subnets that are behind router 2, then it means I can go through router 2 and I'm good to go. So as you can see, this kind of simplifies the configuration. We didn't need to specify multiple routes. All we did was specify a single route, default route, which is a catch-all route, and all the traffic that doesn't match just automatically gets forwarded over to that gateway of last resort. And finally, I'm going to show you a configuration for specifying a floating static route. So we have this default route that is pointing to the primary gateway. I'm going to go ahead and remove the default route from my routing table and specify a static route to demonstrate how floating static route works. So what we'll do is we'll do IP route 192.168.0.0, 255.255.255.0 with the next hop of 10.0.0.2. What we'll do next is for the next route, which is 192.168.1.0/24, I'm going to specify the DIA backup. You see the blue path? That's the backup path. I'm going to go ahead and specify that. And I'm going to go ahead and write my configuration. WR means write mem, which is the same as copy running config to startup config. So it's the same thing. Now I'm going to go ahead and look at my routing table again. I'm seeing a static route pointing to router 2, but guys, we have a bit of a problem. What happened to the second route? I see the .00 route, but I don't see the 1.0 route, the backup one. It should be here. Well, let's figure out what's going on. So let's do show IP interface brief. And if you can see here, it seems like our protocol status is up, but the protocol is down. And this is a very key concept here, guys. I want you to pay very close attention to this. So both the status and the protocol have to be up for the route to show up in the routing table. If the status is up, which means physically it's connected, but the protocol is down, which means it's down at layer 2, the route will never show up in the routing table. So let's go ahead and quickly troubleshoot and fix this issue. So I'm going to go to router 2 and look at what's going on here. So show IP interface brief. Aha! It seems like gigabit Ethernet 001 is administratively down, which means it's manually shut down. Let's go ahead and enable that. Interface gigabit 001. And we're going to do no shut on it. And boom. As you can see, line protocol came up on this side. Line protocol also came up on the left. So you should be good to go here. Do show IP interface brief. And it's up. Let's do show IP interface brief again. It's up now. So that's perfect. Now let's see how our routing table looks. Do show IP route. And sure enough, the secondary route has also now shown up. So what I'm going to do now is show you guys floating static route. So I'm going to go ahead and look at show run and see how my routes look like. What I want to do is I want to go ahead and specify a floating static route pointing to 192.168.0.0 network behind router 2 and tell my router that let's use the DIA path for it, which is 10.0.1.2. That's the next hop. And let's change the administrative distance to 200. So now when I do show IP route, as you can see, my router is still pointing to 0.2, right? Which is the MPLS primary path. But I have now configured a floating static route with an administrative distance of 200. And it's floating, meaning it's kind of there, but it's not inserted or installed in the routing table because the primary path is up right now. But let's go ahead and simulate an outage on the primary path. So I'm going to go to router 2, and I'm going to go to gigabit interface gigabit 000 and simulate an outage. I'm going to shut it down. And let's go ahead and take a look at show IP interface brief. Sure enough, the primary path is down. Let's see if that floating static route actually shows up. Show IP route. And sure enough, you see what happened there? The floating static route showed up with an administrative distance of 200 and a metric of 0. Right? It showed up because the primary path is down, but we still want to reach this subnet behind router 2 across the backup link, which is the internet link, right? Or the DIA, dedicated internet access link. We want to make sure we can get there using the secondary path that we have. That's how floating static route works. Welcome to CCNA 200-301 course. Today I'll cover Section 3, Part 3, IP addressing and routing. We'll do a deep dive into OSPF. Here are the topics I plan on covering today. I'll first do a quick review of static versus dynamic routing. I will then get into OSPF basic concepts. Finally, I'll wrap it all up with OSPF command line interface configuration. So what's the difference between static and dynamic routing? First, in static routing, we have to manually specify the routes. Whereas in dynamic routing, routes are dynamically learned. Second, in static routing, we have to specify a lot of manual entries for redundant paths. And because we have to specify, it's at least double the number of entries, but if you have more than 2 redundant paths, then most likely you're going to have to enter even more entries into your routing table by hand. That makes the process very error prone because human beings, we make mistakes. And In static routing, you best believe that if you have nothing but static routing configured everywhere, you're going to end up making a ton of mistakes. Whereas on the dynamic routing side of the house, we have what's called built-in intelligence that calculates the best path to the destination. Because dynamic routing uses different mathematical algorithms, that's the built-in intelligence I'm talking about. Third, in static routing, if we have bad entries, that can cause routing loops. In dynamic routing, on the other hand, we have inherent routing loop prevention mechanism. 4, in static routing, we have a predictable path, meaning the route that we have specified manually, we will always expect the same route to the destination. It's never going to change. So we have predictability in path. Whereas on the dynamic routing side of the house, we have a predictable outcome, meaning ultimately what we care for is whether or not a particular source can get to a certain destination, because routing is all about source to destination, right? What's in between, like as far as different paths, we do care, but we could care less as long as we can get to our destination predictably. So dynamic routing gives us that ability. Number 5, static routing is for small networks, whereas dynamic routing is great for medium to large size networks. And finally, static routing is great if you're getting paid per routing entry, wink wink, whereas in dynamic routing, not so great if you're getting paid per routing entry, sad face, because you're going to have to type in less entries in dynamic routing, which means you're going to get paid less. Well, there's a pun intended here. Of course, nobody will ever hire you per routing entry. Most likely, you're either going to be a contractor where there's going to be a certain project you have to complete, or if you're a full-time employee, you have to learn how to do things efficiently, and that's where dynamic routing comes into play. Now let's look at OSPF basic concepts. First, OSPF overview. Shortest path first algorithm. So in particular, we're going to talk about OSPF version 2. It's defined in RFC 2328. It uses SPF algorithm, or shortest path first algorithm, also known as Dijkstra algorithm, to find the shortest path to each destination based on the cumulative cost. And we'll talk about the cumulative cost as we continue moving forward to get to a particular destination. That's what makes OSPF such a powerful routing protocol, because under the covers, it uses SPF. And by the way, not sure if you guys know, but SPF is the same algorithm that our GPS uses. So it's really, really cool. GPS uses the same mathematical logic to figure out how to get you to your destination in the most efficient way possible. OSPF is vendor neutral, meaning it's an open standard. So if you're on a Cisco router on one end and there's a Juniper router on the other end, they will work perfectly fine as long as they're running the same version of OSPF, which in this case is OSPF version 2. OSPF has a built-in intelligence for building a loop-free topology. OSPF pretty much guarantees a loop-free topology. What OSPF does is it only keeps the best routes in the routing table. If there are more than one paths in the routing table to get to the destination, OSPF supports ECMP, or equal cost multipath, and that allows OSPF to actually have redundant paths being installed in the routing table. OSPF supports VLSM and security. So if you guys recall from my previous videos, VLSM stands for Variable Length Subnet Masking, which means OSPF is classless, and With every single route advertisement, it advertises a subnet mask for that destination. And from a security standpoint, it can either use clear text or MD5 based authentication. Now, this is an optional feature. You don't have to use it, but it's recommended to use it to protect potential bad actors or hackers wreaking havoc on your environment by bringing in a rogue device that pretends to be an OSPF router and it's actually not. In real world, you would want to do it for security reasons. OSPF deals with efficient updates. OSPF advertises link states or connected links instead of routes. So the biggest difference between OSPF and other routing protocols is other routing protocols advertise routes or networks, whereas OSPF advertises the link states or the local links. OSPF sends incremental or triggered updates only when changes happen in the network rather than sending the entire routing table, and that allows OSPF to achieve really fast convergence, meaning when things change in the network, our network can very quickly adapt to that change. OSPF also sends periodic updates known as LS refresh or link state refresh every 30 minutes. And LS refresh contains a full routing table. Now let's quickly review the different type of tables that OSPF maintains. In particular, it maintains 3 different type of tables. First, neighbor table, same as EIGRP. OSPF routers use hello packets to discover neighbors. OSPF goes through a series of steps to form a neighbor relationship, and I'm going to go ahead and walk you through those steps momentarily. The next table that OSPF uses is called topology table, and topology table is a map or a roadmap of every single network that is available within the same area and all the possible paths to get there. And I'll talk about areas in a moment. Until then, hold that thought, but let me explain what topology table is. So, I'm right here in California. If I want to get to Texas, which is right here, there are different paths I can take. I can take Nevada, Utah, Colorado, Oklahoma, down to Texas. That could be path 1. Or I can take a different path. I can go California through Arizona, New Mexico, down to Texas. So I can either take the red path, the northern path up here, or I can take the southern path down here in blue. Well, the reality of the matter is, when I fire up my GPS, it's going to show me these 2 paths. Now, you may jump to the conclusion by looking at these 2 paths immediately to go, well, the blue path should always be preferred because you're only going through 2 different states compared to the northern path in red where you're going through 4 different states to get to Texas. But let's not jump to the conclusion here, guys, because there's a couple of very critical pieces that are missing here. Piece number 1, the source. What's the exact source of this traffic? Meaning, am I located in Southern California or am I located in Northern California? I'm located in Northern California, right? I'm in San Jose. So if I want to get to Texas, perhaps the northern path is faster to get there. Maybe. But if I live in Southern California, most likely the southern path is much faster and efficient. But there's one other critical piece that's missing. What does the traffic look like? That's another thing my GPS looks for, right? If the traffic is bad on the southern path, then most likely northern path is the only efficient path to get to my destination. Now, how's that relevant to OSPF? OSPF, using the SPF algorithm or the shortest path first algorithm, uses the same logic. It looks at the source, it looks at the destination, and then it also looks at, instead of traffic, it actually looks at bandwidth. OSPF doesn't actually look at the congestion, but it looks at the bandwidth, which is considered cost to get to the network. Now, I'll talk about cost in a little bit, but the bottom line is that this is the information that OSPF uses to figure out how to allow packets to go from the source to destination in the most efficient way possible. Now, with this context in mind, let's continue. And there's a third table that OSPF maintains called a routing table. And where routing table comes into play is OSPF router initially builds a topology table right after the neighbor table is built. And once it understands the topology and the database is built, then it runs its SPF algorithm and it finds the best path, and then that best route goes in the routing table. Now here, let's quickly take a look at which path OSPF will choose to install in the routing table. We have the source on the left, router 1. We have destination to the right, router 8. Path A, there's only one hop in the middle, only one additional router in the middle. We have path B in green, and we have 2 routers in the middle, or 2 additional hops. And we have path C that has 3 additional hops to get to the destination. Which path do you think OSPF will take? Well, you might jump to the conclusion and say, obviously, path A, duh, that's the path with the least number of hops. But you would actually be wrong. And let me explain why. Path A, what if this is 10 meg? And this is also 10 meg. Whereas path B, what if this is 100 meg on all the circuits? And path C is 1 gig on all the circuits and all the links all the way across. Now, which one do you think OSPF should choose? Well, OSPF uses bandwidth intelligence to figure out, right? It's called cost. That's a metric that it uses. Obviously, it will take path C and install this path in its routing table to get to this destination of router 8 because of the efficiency in bandwidth. So hopefully, this gives you an idea that in network architecture, we can never jump to conclusions. We should take our time, look at the design, and see exactly what the network is telling us before we can jump to any conclusion. Now let's quickly look at OSPF areas and terminology. OSPF has what's called Area 0, and it's considered a backbone area. And the best analogy I can give you when it comes to the backbone area is the human backbone. We have a backbone that connects to all the different limbs in our body and all that. And all the signals are processed through our central nervous system and carried through our backbone to the brain. But our backbone is the key to connecting the entire body together, and that's exactly what OSPF Area 0 does for us. It's the backbone of the entire network. And all other areas must connect to Area 0. So let's quickly take a look at this topology we have here. So we got a couple of different routers here. We have an ASBR, ABR, BB, and ABR. And I'll explain this terminology in a moment. I'll just explain BB for now. BB stands for backbone router. And the reason it's called backbone router is because it's only in Area 0. But then we got other routers that have connectivity into other areas, which we'll discuss in a moment. But the bottom line is all areas must connect to Area 0. Routers in the same area share the same database or topology table. In other words, this router right here, this router right here, this and this, all 4 of these guys will have the same view of the entire network, meaning they'll see the same links being advertised, same networks being advertised. They're going to see the exact same picture of the entire network. The only difference is that each router is going to be at the center of the universe. Once again, it's a GPS idea. No matter where you are in the world, when you fire up your GPS, you immediately become the source. And then the place you want to visit is the destination. It's the same thing here. And ABR would be the source, and then when it runs its shortest path first algorithm to figure out how it should communicate with the rest of the network and the databases are exchanged, all of these routers will have the same view from their own unique perspective. ABR stands for Area Border Router. That's the router that sits at the border of the network, and it connects multiple areas together. So if you look at, for example, this area border router right here, it has one leg into area 1 and another leg into area 0. If you look at this ABR right here, it has one leg into area 2 and another leg into area 0. So that's what makes these routers ABRs, or area border routers. We also have an ASBR, which stands for Autonomous System Boundary Router, which in this case is this guy. So it has one leg into area 0, into OSPF, and it has another leg into another external routing domain. Now this could be BGP, this could be EIGRP, this could be ISIS, could be RIP version 2, but I hope not. But the bottom line is ASBR connects you to the external world. When it comes to OSPF, we have this area concept. We have what's called a single area design, and we have what's called a multi-area OSPF design. Theoretically, you could get away with having a single area and all of the devices can be part of that area. So for example, you can have area 0 and all of the devices in your network, let's say if you have 50 sites, all 50 sites can be part of OSPF and life is good. But what if your network grows? What if you have 100 sites or 200 sites or maybe 1,000 sites or 10,000 sites? Having a single area in that case would be insanity. So what you would do then is define different areas and somehow figure out like a geographical separation to define how the network is designed. And that allows an efficiency in the network. Another very important thing to keep in mind, guys, is route summarization. And it's a really amazing feature. And let me give you a quick example. So let's say behind this ABR, you have 30 routers. Okay. And each of these 30 routers has 3 different subnets on the LAN that are carrying different type of traffic, PCI, internet, and MPLS. Now, 3 times 30 equals 90. That's 90 LAN subnets that this ABR will have to advertise into area 0. But not only that, this doesn't even include all the links. So the 30 routers, each router is going to have at least single link. So assuming we only have a single link design, we don't have redundant circuits, that's 90 plus 30. That equals 120 potential networks that will have to be flooded into this area 0. Now, as you can imagine, if you have a much larger network, you're looking at a much, much larger number of advertisements. So to compress this, and instead of advertising 120 individual networks, wouldn't it be nice if you could take all these 120 and advertise a single network? And this is where network summarization come in. We can actually do that. It's called supernetting. It's the opposite of subnetting, where we take a bunch of subnets and we summarize them. In subnetting, we take one network and we divide it into different networks, right? But in summarization, we take multiple smaller networks and combine them into a single larger network entry. And this way, we don't have to send a ton of routes. We just send a single route and that's it. And one key thing to keep in mind is in OSPF, only the area border router and the autonomous system boundary router are the ones that can do summarization. No other device can do summarization. So in other words, this guy cannot do summarization. And if there was another router behind this ABR, or if there was another router behind this ABR, these devices won't be able to do summarization. And this backbone won't be able to do summarization either, because it doesn't have a link in different areas. Only the device that sits at the edge of different networks has the ability to be able to do summarization, which makes sense. Now let's quickly take a look at OSPF LSA types. There are 3 different types of LSAs in OSPF, and these are link state advertisements. So when the routers connect with each other, they start exchanging packets with each other. That's where these LSAs come in. So we have what's called an LSA type 1. It's called router LSA. And it describes a router. Each router sends a type 1 LSA in an area, and it includes a list of directly attached links and a router ID. LSA type 2 is the network LSA, and it describes a network that has a designated router, and we'll talk about a DR in a moment. This LSA is only generated by the DR on broadcast network, and it includes the DR and BDR IP, subnet ID, and subnet mask. And finally, LSA type 3, called summary LSA, it describes a subnet in another area. This LSA is summarized route generated by the area border router. It includes subnet ID, mask, and router ID of advertising ABR. Keep in mind, there are 11 types of LSA in OSPF. In CCNA exam, though, because of the exam blueprint, we're only covering 3. When we get to CCNP, we're going to learn about 4 additional type of LSAs, but it won't be until you get to CCIE that you'll get to learn about all 11 types of LSAs. Now let's quickly dig deeper into the OSPF header. And within an OSPF header, there's a field called packet type. And let's zoom into that field within the OSPF header, also called LSAs, or link state advertisements. What that packet contains is a hello message. That's what's responsible for neighbor discovery and neighbor adjacencies. These messages are sent to multicast address 224.0.0.5 or 224.0.0.6. Now let's pause here for a moment. I want to describe a very important concept here. Instead of doing a broadcast to all the devices, what OSPF does is it uses multicast to send hello messages. So let's say if you have all these different routers that are connected to the same LAN segment, and this router right here is only doing static routing, and so is this guy. Both of these guys are doing static routing, whereas these guys are running OSPF, these 3 right here. Well, because it uses multicast, only this router, and this router is going to get the hello message. These 2 routers running static routing will never even get this hello message, and they shouldn't, because they're not running OSPF. That's why multicast addressing is used instead of a broadcast, because broadcast would be sent out to everybody. Even the static routing devices will get it. But in this instance, they won't, because you're using multicast. The next type of packet that OSPF uses is called database descriptor, or DBD. It's a link state database summary. The third is link state request, or LSR. It's the request for specific networks, and it's a unicast. LSU is a response to an LSR, and it contains multiple LSAs within it. So you can think of an LSU as like a bucket. And within that bucket, you got a whole bunch of LSAs. And finally, we got link state acknowledgement packet that is designed for acknowledging the database descriptor packet, the link state request, and link state update. And this is what makes OSPF a reliable routing protocol. Now, if this doesn't make a lot of sense to you right now, hang in there with me. As we continue exploring additional topics, this stuff will make sense, and we'll come back to it, especially when we're doing the CLI configuration piece of things. this stuff will start to click. Here's a quick overview of OSPF neighbor adjacency formation process. So let me quickly explain. So we got a router on the left, R1, and we got router on the right, R2. Let's imagine these two routers are directly connected with each other with a piece of copper cable. Here are the steps these devices will go through in order to form an OSPF neighbor relationship. Step 1 is when the routing process is actually running on the router, but we're in a down state because we haven't learned about our neighbor yet. Step 2 is called init state. And this is where router 1 would send a hello message to router 2, also known as initialization state. Step 3 is when router 2 will respond back to router 1. And in that hello message, router 1 will actually get its own router ID back from router 2, like a boomerang. And when that happens, it achieves what's called a two-way state, meaning it now knows that I have a neighbor who has acknowledged my presence, so now you can start talking to each other. Step 4 is what's called an X start state, and this is where the DR and BDR election takes place, and the highest router ID becomes master. Now, let's park it for a moment. I'm going to go deeper into this momentarily. Once we get past that step, we'll get into step 5, which is called exchange state. Here is where the database descriptor or DBD packets are exchanged. Step 6 is the loading state. Based on that database descriptor packet that was exchanged in the previous step, the router sends an LSR or link state request. In this case, R1 will send an LSR to R2, and R2 will respond back to it with an LSU or link state update that contains multiple link state advertisements within it. And then the final step, step 7, called full state. Here all the LSAs are exchanged and OSPF databases are fully synchronized. Now let's quickly talk about one more item before we get into the CLI, and that is OSPF neighbor adjacency requirements. Now here are the 10 commandments of OSPF neighbor relationship. And what I mean by that is you must abide by these 10 rules to make sure the neighbor adjacency comes up. First one is interfaces. Interfaces must be in an up-up state. Now, it's one of those where you go, duh. I mean, of course you have to be in an up-up state for the routers to talk to each other. Second, no access control list filtering routing protocol messages. So the second one means you shouldn't have any ACL on an interface that is actually filtering the routing protocol messages, because that would make the adjacency not come up. Third, interfaces must be in the same subnet. That makes sense. Authentication must match on both ends. Makes sense. Hello and dead timers must match. Each router ID must be unique. So you cannot have two routers on the same network with the same router ID. It's going to cause issues. And your OSPF adjacency will flap or may never even come up. So make sure each router in your environment has a unique router ID. Interfaces must be in the same area. OSPF process should not be shut down. Duh. All neighboring interfaces must use same MTU setting. So that's another important one. Here, the OSPF adjacency will come up, but you're going to have weird type of intermittent issues if the MTU mismatches on the two neighboring interfaces. So make sure your MTU value matches. If it's 1500 bytes on one side, then on the other side of the link, it should also be 1500 bytes. And finally, all neighboring interfaces must use the same OSPF network type. It's another one of those scenarios where if you had a mismatch, the neighbor relationship is going to come up, but then you're going to have bizarre issues where the information will never make it into the routing table. Things will get lost into building the LSDB or the link state database. So keep this list in your back pocket. Now let's quickly take a look at OSPF network types. The two network types that are covered in CCNA are broadcast network type and point-to-point network type. Let's first speak to the broadcast network type. That's a default mode on all Ethernet interfaces. It requires neighbors to be on the same subnet. It's used for auto neighbor discovery, and OSPF hellos are sent to 224.0.0.5. DR and BDR election takes place in broadcast, and when we have DR and BDR, then those hellos are sent to 224.0.0.6, and we'll talk about that in a moment as well when I go deeper into the DR-BDR process. Couple of things to keep in mind. Highest OSPF interface priority wins the election. By default, all the interfaces have a priority of 1. So because interface priority is always the same, router ID ends up becoming the tiebreaker. Once the DR is selected, DR is in charge of receiving and sending all the updates to everyone on the local subnet. After the DR and BDR election, all other OSPF routers on the local subnet become DR other. And there's another network state that I think is important for you to understand called point-to-point network type. That's the default mode on serial interfaces. So if you guys are familiar with T1 or E1 in Europe, or OC interfaces here in the US, or STS interfaces in Europe, or APAC, then you know what serial interfaces are. And serial interfaces are, by default, considered point-to-point because there are no additional devices. There are only 2 devices on a serial interface. Hence the reason we call it point-to-point. It requires neighbors to be on the same subnet, uses auto neighbor discovery, and hellos are sent to 224.0.0.5. However, the big difference here is there's no DR or BDR election because the broadcast is not supported on serial interfaces or the point-to-point network type. Now let's quickly look at OSPF, DR, and BDR. So everything that we have learned up to this point would help us understand how this works. So let's quickly jump in. So if you look at this network segment here, this is a point-to-point link because this is a serial link, right? In this case, what's going to end up happening is there is no DR or BDR happening here, right? Because it's a serial link and we just talked about it. So this is a point-to-point. However, we are going to have a competition on a couple of different segments. First of all, this right here is a shared segment. So these 2 routers are going to go through the election process. Let's assume this guy becomes the DR, this guy becomes the BDR, and do you guys remember the third type? It's called DR other, or druther for that matter. And then there's another election process that's going to take place here on this segment. Let's assume this becomes a DR, this becomes a BDR, and all these guys become DR others. So that's how this whole DR and BDR process works. But what's the reason behind DR and BDR to begin with? Well, in OSPF, what ends up happening is when we're exchanging our databases, which is called the LSDB, Link State Database. When we're exchanging the database, we assume full mesh connectivity, meaning all of these routers can talk to each other and they can all send updates to each other. As you can imagine, this could become very chatty if everybody started sending updates to everybody on the same LAN segment. So what ends up happening is with the DR and BDR election, let me clean this up a little bit. If this guy is the DR and this guy is the BDR, by the way, BDR only comes into picture when the DR is down. So BDR is there, but it's not actually doing anything. DR on a LAN segment becomes in charge of everything. So what that means is if there's a change in this LAN segment, if something happens here, this guy is going to advertise it to DR. DR is going to receive that update, and then the DR would be responsible for responding to everyone. Instead of this guy sending the update to this guy right here, this router, and then this guy advertising it to everybody else, and then everybody else advertising it to everybody else. This chaos is controlled by this DR, and this DR then becomes responsible for letting everybody else know. And the criteria for the election is the highest interface priority. If that's not configured, then the highest router ID will end up becoming a DR or BDR. Now in real world, typically the best practice design would be to use the interface priority as a tiebreaker, because then you know for sure that, for example, if you want this guy to be DR no matter what, if you set up the interface, this interface right here with the highest interface priority, then this guy will always be preferred no matter what. And one last thing to keep in mind is on a shared network segment, all routers except DR and BDR stay in two-way state. And we talked about states a little bit ago. Now let's quickly talk through the OSPF metric called cost. So once the neighbor adjacency is done, like we talked about a moment ago, OSPF runs its SPF algorithm to find the best path to the destination. And to find the best path, it uses a metric called cost, and it's based on interface bandwidth. And the formula is cost equals 100 divided by bandwidth in megabits per second. And here's the default OSPF cost table. So as you can see here, if you guys remember the 56 and 64K modems, these are the default costs. T1 is a cost of 64, E1 is a cost of 48, Ethernet 10 meg is a cost of 10, Fast E is 1, Gigabit Ethernet is 1, 10 gig Ethernet is 1. And as you can imagine, if you let this default table operate, that's not a good thing, because in today's data centers and networks, you may actually have 100 gig links. And if the 100 gig is the same as the fast Ethernet, well, we got a problem, right? So there's actually a way to fix that. We'll talk about it in a moment. And here's a quick topology of how this can play out. So as you can see, the different type of links, this is 48 because this is an E1. And this right here is 1785 because this is the 56K circuit. And this guy's 1 because it could be 100 meg circuit. This could be 1 gig, so on and so forth. Now, if you wanted to change it, which we would want to, we can change it under the routing process, under OSPF routing process. We'll type in a command auto-cost space reference-bandwidth space. When we type in 100,000, this means 100 gig. The minute we do that, 100 gig becomes a cost of 1, and all the other subsequent bandwidths like a 40 gig, 10 gig, they will have higher costs than 100 gig, and this will truly reflect what our environment looks like. So remember, OSPF has been around since 1980s. This is where these values are coming from, and we'll have to make changes for this to work. Here's another way of specifying cost at the interface level. We can type in IP OSPF cost and then the cost of 1. Remember, cost of 1 is most preferred. And one last thing I want you guys to keep in mind is once you change the reference bandwidth command, it must be adjusted on all OSPF routers. So you cannot type in this command on just one router and be done with it. You're going to have to specify it on all OSPF routers in your environment so they can calculate and run their SPF algorithm accordingly to find the best path around the network. Now let's quickly jump on CLI, my favorite part, and talk about OSPF and actually get to see it in action. Love getting my hands dirty. When it comes to routing, there's no better way to learn. Now let me give you a quick walkthrough of this lab right here. We have two routers in the middle, router 1 and router 2, part of area 0. We have router 3 in area 1 and router 4 in area 2. Now if you start from left to right, we got network 10.0.31.0/30 between router 3 and 1. We got network 10.0.0.12.0/30 between router 1 and 2. And between router 2 and 4, we have network 10.0.13.0/30. So I want you to familiarize yourself with this. And I've also specified the ending IPs on each side of the link, so you know exactly how that's going to pan out. And on router 3, I've got a bunch of loopbacks that are defined, and these loopbacks are representing different type of networks or subnets that are behind router 3. And similarly to the right, on router 4, I've got a ton of loopbacks that are representative of different subnets or networks that are behind router 4. With this context in mind, let's quickly jump into the CLI. So let's quickly take a look at router 3 first. And let me show you what I've done. So I've configured the 10.0.31.2 IP address on router 3's interface. And let's make sure I have the correct subnet mask on this interface. So I'll do show run pipe section interface and hit enter. This is a cool command. Instead of running through the entire show run or running config, you can just simply look at the different interfaces. And by looking at fast Ethernet 1/0, I can see that I do have /30 specified on this interface. Let's also quickly take a look at show CDP neighbor command to see who's directly connected with me. And as you can see here, as depicted in the diagram up above, router 1 is indeed connected with me over my local interface of fast 101/0, and the remote side is also fast Ethernet 1/0. So that is great news. Let me go ahead and enable OSPF on my router here. And what I want you guys to understand is that when it comes to OSPF, the way we enable OSPF on the router is by simply typing in router OSPF and then the process ID. And when we do that, we're now under the OSPF routing configuration mode. Now let me take a quick pause here because I think it warrants a quick explanation. You see this OSPF process ID? It's locally significant, meaning it's not carried through the OSPF LSA update or anything. It's only enabled locally on the router, and that's about it. Now what we need to do next is we need to define the interfaces that I want to enable OSPF on. I'm going to give you a couple of different ways of doing this so you guys can become the masters of OSPF, okay? The least specific way or the laziest way is you type in network 0.0.0.0 and you type in a wildcard mask of all 255s, and you type in area 0. Now, I said wildcard mask, and you might be going, whoa, hang on a sec. What's a wildcard mask? And that's a great question. Let me quickly do some whiteboarding so I can explain what a wildcard mask is. So a wildcard mask is considered the mirror opposite of a subnet mask, and it's also known as an inverted mask, okay? So let me explain. So if you guys remember from the videos that I did on the topic of subnetting, what is this? This is a /24, right? /24 is represented as 255.255.255.0. What would be, this is called a subnet mask, right? But if I wanted to create a wildcard mask from this, how would I go about doing that? Well, it's the mirror opposite. So that means where I see 255, I will actually specify 0. 0, 0. And where I see 0, I'll specify 255. So once again, wildcard mask is the mirror opposite of the subnet mask. And Wildcard mask is used by EIGRP, OSPF, and also access control lists or ACLs. So it's something important that you have to understand and learn. And to continue building on it, in subnet mask where we see all ones, so for example, going back to 255.255.255.0 example, if I were to zoom into this, we have, if you guys remember the handy dandy binary conversion chart, I'm going to go ahead and specify all these values here. And these are the different binary bit positions. And in 255 means all the bits are on. So every single bit is on. And when we add up all these numbers, that adds up to 255. Now I've done a detailed video on this topic. Go ahead and check that out. It's called IPv4 addressing and subnetting. Now, that being said, in the subnet mask, wherever we see ones, that means we care. That means we actually care for these bits. And where we see zeros, like this zero right here in the last octet, if you were to zoom in, that would be all zeros from a binary perspective. That means we don't care for these bits. We do care about the ones, but we don't care about the zeros. Now, what happens in a wildcard mask is the opposite of the subnet mask. So in the wildcard mask, the logic is reversed, meaning wherever I see zeros, that means I care, and wherever I see ones means I don't care. And that's the wildcard mask for you. Let's go ahead and jump back on the CLI again. I could do it this way, but I'm not going to do it. This is the laziest way of doing it. And I'm going to go ahead and type in no in front of this command and remove it. Now OSPF is not running on any network. I'm only running a local OSPF routing process, but I need to be able to start running it on interfaces. Now, the next level up is less specific, but here what we can do is we can go network 10.0.0.0 and with a subnet mask of 0.255.255.255 area 0. And I'm actually doing it wrong. I shouldn't actually be saying area 0. I should actually be saying area 1. So what that means, I'm going to go ahead and have to type in no in front of it, retype this command, and put 1. Because remember, looking at the diagram, I'm in area 1 on router 3, right? So I have to specify area 1. Now what this command is doing is that, as I explained earlier, it's saying all I care for is the first octet, because that's a 0 on the wildcard mask. This means I care, but then the rest of the 3 octets, I do not care because I've got 255.255.255 there. So wherever I have ones in the wildcard mask, I don't care. Meaning, when I take this interface right here, and as long as the first octet matches, I'm going to go ahead and enable OSPF on whether I have one network or if I have 10 different networks. I'm going to go ahead and enable OSPF on all these different networks. And this should be fine. We can do it this way, even though I would prefer this to be more specific, but that's good enough for demonstration purposes. Now let me go ahead and jump on router 1, look at show IP interface brief here, and see what it's got going on. I'll do show CDP neighbor to see whether or not I'm seeing the appropriate devices, and sure enough, to the left of router 1, I'm seeing router 3 connected, and then to the right, I'm seeing router 2 connected. That's beautiful. Let me go ahead and enable OSPF on this router. So I'll do config T router OSPF 1. By the way, it doesn't have to be process 1. This process ID doesn't have to match. I can call it process 100 if I wanted to. And as a matter of fact, let me call it 100 so I can demonstrate my point that this value right here is irrelevant. it doesn't really matter. It's something locally significant. It's not carried in LSA updates or anything like that. So I'm going to prove my point in a moment. Let's go ahead and now let's be a little bit more specific this time around. We're going to say network 10.0.31.0, and we're going to go 0.0.0.3 for the wildcard mask. And if you're wondering, where did I get 3? I'll have to explain that to you in a moment. And we just got the OSPF adjacency message saying our neighbor has come up and we're connected. So that's good. OSPF adjacency has come up. But before I start looking at OSPF, I want to explain to you the wildcard mask and how I came up with 3. So let's go ahead and do some whiteboarding again. So as I mentioned earlier, a /24 in a subnet mask world is 255.255.255.0. The wildcard mask of this would be the opposite of it, so 0.0.0.255. What if we have a /16? Well, /16 from a subnet perspective is 255.255.0.0. What's going to be the wildcard mask of this? The opposite, 0.0.255.255. What about if we have /8? Well, we have 255.0.0.0. That's a subnet mask. How is the wildcard mask of this going to be? Well, simply the first octet is going to be 0 followed by a bunch of 255s. Now let me explain how I came up with that .3 in the subnet mask. So because it's a /30, what's a /30 from subnet mask perspective? 255.255.255.what? 252. The wildcard mask, like I said, is the opposite of it, but here I'm going to go in slightly more detail. So to figure out the wildcard mask, here's a tip you can use. So jot down all 255s at the top. And what you want to do next is take the /30 that we had and subtract. So let's get it all written here. And then we want to do what? We want to subtract, minus, right? So 255 would be 0, 255, 0, this would be 0, and this would be what? 255 minus 252 is 3. This is where the value 3 came from that you were looking at earlier, right? That I typed in on my router. This is a very, very specific entry, and this is a /30 entry from a wildcard perspective. Now what I can do is I can go ahead and look at show IP OSPF neighbor, and I'm going to have to type in do in front. And what we're seeing here is that I'm connected with my neighbor who happens to be, but hold on a sec. This command shows me that I'm connected to my neighbor 10.0.31.2, which is router 3, and my interface is fast Ethernet 1/0. And another critical piece of information that this gives us is that this ID right here, neighbor ID, this is called router ID. So if you guys recall, I talked about router ID or RID a couple of times before. That's what it is. And as you can see here, on router 1, I'm seeing a random, well, seemingly random neighbor ID. There's a better way of handling it, so we'll talk about that in a moment. Now on router 1, I'm not done yet. I still have to run a network command yet again on another interface. Now, this time around, let me use the network command 10.0.12.1, and I'll type in the wildcard mask of all zeros in area 0. Now, what did I do here? Once again, zeros in wildcard mask mean I care. This means this entire thing has to match. Now, this is very, very specific. This is like laser surgery. Here, I'm specifying that I only want to enable OSPF in this particular interface, and that's about it. Now, I personally really like it because what that does for me is ensures that I'm only enabling OSPF on the interface that I care for and nothing else. But there's even a better way than this, and I'll show you what that looks like when we get to router 2. So at this point on router 1, we're done. Let me go ahead and write the configuration. Let me go to router 2 now. Now let's go ahead and start configuring router 2. So look at show IP interface brief. Look at show CDP neighbor. That looks good. Let's go ahead and start configuring now. This is my favorite way of enabling OSPF. So what we'll do is we'll go under the interface. So interface fast00, we'll say IP OSPF. I'll give it the process ID. Let's just say 200, and we'll do area 0. And bingo, our OSPF adjacency just came up. And we'll go to the other interface now, fast Ethernet 1/0, and type in the same command again, but then change the area to area 2. Because router 2's interface pointing to router 4 happens to be in area 2. And let's go to router 4 and do the same thing, show IP interface brief. That's good. Show CDP neighbor. I should only have one neighbor toward router 2. That's good. I'll go under the interface and enable OSPF. IP OSPF. Let's just say it doesn't really matter, like 99 area 2. So now you guys have seen different methods of how OSPF can be enabled on a router. Now let's quickly go ahead and look at a couple of show commands. Show IP OSPF neighbor. I'm only seeing one neighbor, and my neighbor's address is 10.0.13.1, which is right if I look at the diagram here up at the top. And I've got a full adjacency with them, and that's good. And then the router ID is 10.0.13.1. Once again, this is something I will talk about momentarily. Now let me quickly go to router 1 and look at show IP OSPF database. And naturally, there's a lot more to unpack here. This right here is LSA type 1, router link states. And if you guys remember, router link LSA is where the neighboring router is advertising to us their router ID along with all the links that they have. Well, because we don't have the router IDs properly specified, it's going to be a lot harder to unpack this. So what I'm going to do is I'm going to go ahead and manually start configuring router ID on every single router to hammer the point home why it's important to have router ID specified. Always. That's considered a best practice design. So we'll do router ID. Because it's router 3, we'll do 3333. And as you can see here, it says we have to either reload or clear the OSPF process. So what I'm going to do is I'm going to do clear IP OSPF process. Reset all processes. Yes, please. Now let me go ahead and do that across the board. Now I have to remember the routing process. 100. So router OSPF 100, router ID 1111. That's good. I'm going to go ahead and do clear IP OSPF process. Yes. On router 2, same thing. Do show run section OSPF. We'll do router OSPF 200, router ID 2222, do clear IP OSPF process, and yes. And we'll do the same thing here. Do show run section OSPF, router OSPF 99, router ID 4444, do write mem and do clear IP OSPF process, and that should really be it. Now that we have reset the OSPF processes across the board on all the routers, let's go ahead and unpack the show IP OSPF database command that I've typed up here on router 3. Now look at the diagram up above and keep this context in mind as we unpack this. Okay. First, it tells us our OSPF router ID right here. It's telling us the local process here running here. Once again, this is locally significant and has no relevance across the OSPF network at all. It's only local to the device. This right here, as I alluded to earlier, is LSA type 1. Now, LSA type 1, if you guys recall, it describes a router and it tells us the different links that we have in our database. And everybody in the same area, which in this case happens to be area 1, because you're looking at router 3 up here, it only has connectivity into area 1. Everybody in this area should have the same database right here. So all the links are advertised, and you can also see the link count. There's only one link per device, as we are seeing here. Okay. The next one up here is LSA type 2. This is called the network LSA. And this describes a network that has a DR. So it shows us right here that link ID 10.0.31.2, which happens to be us, we are the DR. And we can confirm that when we look at the command that we ran above that, show IP OSPF neighbor, it shows that our neighbor is a BDR, or backup designated router, which automatically makes us what? A DR, or a designated router. So that's what we are seeing here. And finally, LSA type 3, which is called summary LSA. This describes all the subnets in other areas. So because you're in area 1, we're going to see this link ID, which is 10.0.12.0. This happens to be the area 0 link ID. And this right here, 10.0.13.0, which happens to be the area 2 link ID. So we're seeing those in here. So if you go back and look at when I talked about the OSPF LSA types, you'll get to understand now what I was talking about, because now this crystallizes that concept that I articulated earlier. Now, let's go ahead and continue moving forward here. I'm going to run the show IP OSPF database command on router 1 here. And what you're seeing is it's showing its own router ID and the local process ID that it's running. And then for area 0, it's showing all the different routers that are advertising the router LSA type 1. Then it's showing the DR on this segment. And here the DR happens to be 12.2, which is router 2, which means if I were to do show IP OSPF neighbor, we're going to be a backup designated router, which I'm going to do in a moment. And then finally, the summary LSA is routes in other areas or network in other areas. So 10.0.13.0 is in area 2, and 31.0 is in area 1, and we happen to be in area 0. So we always see information from other areas, not our own area. Now below it, right here is information for area 1. This is the LSA type 1 for area 1, LSA type 2 for area 1, LSA type 3 for area 1. So for each area, we have separate LSAs. It's per area idea. We can also look at a command show IP protocols to see what protocols we are running on this router. So here we can see our local OSPF process. We can see there are no update filters set. That's good. We can see our router ID. We can see that we are an area border router. And the reason is because we've got legs in multiple areas. And in particular, we have 2 different areas here. And we're routing for these 2 networks, one in area 0, one in area 1. It's also showing us the reference bandwidth command is set to 100 megabits per second. And it's also showing us the routing information sources, where the information is coming from. And our default distance is 110. Now let's also look at another very important command, show IP route. And here, what we're seeing is, of course, the connected routes are represented by the code C. But what we're interested in is the OSPF route, right? So which starts with O, and then it's got IA in front of it. So if you see O means OSPF up here, and IA means OSPF inter-area route. And what that means is on router 1, we're learning 10.0.13.0, which is a inter-area route, meaning it's a route that's being learned from a different area than the one we know about. Because remember, in router 1, what are the 2 areas we know of? On router 1, if you look at the diagram up here, we know about area 1 and we know about area 0. We don't know about area 2. But through the magic of routing, we are learning about this network from router 2 because it's connected to router 4, as you can see in the diagram. And we can see that our administrative distance is 110 and our metric to get there is 2. And the reason our metric is 2 is there's a cost of 1 here and there's a cost of 1 here to get to R4. That's why this value right here is 2. Because the idea is cumulative bandwidth, right? So we have to add the bandwidth of all the hops that are in between, and that will give us our metric. Now, one more thing we need to do is we should also go ahead and advertise all of our loopbacks, right? We got all these loopbacks that need to be advertised. So let's go ahead and do that. Let's do show IP protocols, because that can help us determine the routing process. So we'll do router OSPF 1, and we'll go ahead and do network 172.30. I'm just going to be lazy here and do this and type in area 1. And this will cause OSPF to flood the information, because remember, we just had a network change. So what this is going to do is this is going to flood this information across the entire OSPF domain. So show IP route. So we're showing these as are directly connected. I'm on router 3 right now. I'm seeing 2 inter-area routes. One is the 12.0 and the other one is a 13.0 network, which makes sense because router 3 is not connected to area 0 or area 2, but it's still learning. And if we go to router 1 now and do show IP route, what we should see now is all these routes, all these OSPF routes that are being learned, which are the loopbacks. So basically these loopbacks are subnets behind router 3. And we should be seeing them everywhere now. If we do show IP route on router 2, what do you think? Do you think router 4 is going to have that or no? All those routes. Of course we will, because that's what OSPF does. Because at the end of the day, we need to be able to communicate with all the devices, right? So you're seeing the flag here of OIA, which means inter-area routes. And we can see the cost here, which tells us that we're a couple of hops away to get there, 4 hops away. So the 3 hops would be the links in between. So router 4 to router 2 is 1 hop. Router 2 to router 1 is another hop. Router 1 to router 3 is the 3rd hop. And then the loopback is the 4th hop on router 3. So that's what we're seeing here. Now that's a lot of routes. So let's jump back to the deck again and learn about a couple of additional concepts. So how do we change the router ID? So remember, we wanted to change the router ID, right? Because that allows us more flexibility, which we did that earlier. How about the interface ID or priority? Well, this feature we configure under the interface. By default, all the routers have priority 1, but you can go ahead and specify the interface priority. And this will make sure that this particular router that has a better priority configured is always selected over any other router. And if you assign the value of 0 to that router, it exempts the router from the DR/BDR election process. Another very important concept that I want you guys to understand is the OSPF route summarization. So you just saw in the routing table, we have so many different routes that we're learning from router 3 throughout the network. Wouldn't it be nice if we could somehow figure out a way to advertise a single routing entry instead of having these individual routes? Now, it looks nice if you have a small network to have access to every single subnet. But in a very, very large environment, this can get out of hand. And looking at the routing table, you'll have pages and pages full of routing table, and it's going to become very, very difficult for you to troubleshoot. So there's a concept called summarization. And what we can do is all the different networks that we defined on router 3, if we were to line them up like the way you're seeing here, we would want to see where the changes are happening in order to do summarization. And as you can see here, clearly the 3rd octet is where the change is happening. So because this is where the change is happening, we focus on this octet. And what we do is we go ahead and zoom into this octet and we convert these IPs to binary. So if you convert 0, the 3rd octet 0 to binary, it's all zeros. 1 would be a bunch of zeros followed by 1. 2 would be this, 3, 4, so on and so forth. And when we jot all this down, what we learn is that the leftmost bits, the 5 leftmost bits are the same here, but the 3 bits to the right is where the change is happening. So if you recall, because this is /24, /24 is 255.255.255.0. And when we take that and we apply this logic where we understand the 5 bits are constant and only 3 bits are changing, what we can do in the 3rd octet is we can go 255.255.248.0, because only the first 5 bits. And if you recall, there's this binary conversion chart 1, 2, 4, 8, 16, 32, 64, and 128. If we were to line up these bits here, what we'll get is the 3rd octet being 248, because 5 bits are constant, right? So this is on, this is on, this is on, this, and right here. So if you were to add all these up, you're going to get the value of 248. And that's what I have right here. So therefore, the most efficient subnet mask, or supernet, we call that supernet, to advertise for this network would be this command right here. So let's go ahead and do that on our router and see what happens. By the way, just to quickly clarify, this is not under the interface configuration. This is under the OSPF routing process. So let's go ahead and check that out. We're going to have to do this on router 1 summarization, right? Because if you guys recall, we can do summarization only on an ABR or ASBR. In this case, router 1 is an area border router. So this router should give us the ability to go ahead and configure that. So let's do show IP protocol and see what our OSPF routing process is. Router OSPF 100, and we'll do area 1 range, and we'll type in the network followed by the subnet mask. Here, it's not the wildcard mask, it's a subnet mask. So remember this distinction compared to the network command. When we type in the network command under the OSPF routing process, we specify wildcard mask following the network ID. Here we typed in the subnet mask after the network ID. So now what this should do for us is down the line, like on router 2 and router 4, we shouldn't be seeing so many different routes. We should now be seeing a very tidy routing table. And sure enough, you see how tidy and nice this is. Now we're seeing 172.30.0.0. So basically all the routes have now been represented by a single entry in the routing table, and this saves on memory, CPU, bandwidth, all those precious resources on our router. And it should be the same thing on router 4. If you look at the routing table, sure enough, instead of seeing those individual entries for 172, we're just seeing a single entry now. And that's awesome. Now I want to quickly talk about the OSPF default routes. And as you can see here, I've got this diagram right in front of you. We're going to go ahead and set up a default route right here, pointing to this next hop on our router. And I kind of changed the topology a little bit. Instead of area 2 now, I'm going to call it ISP. And what I'm going to do is I'm going to actually remove OSPF here. Okay. I want to remove it, and I want to do this to show you how the default route works. So a couple of commands I want you guys to look at is, we're going to first type in the default information originate command. This command creates a default route for the network if one exists. So I'll explain what that means. And then the other one is default information originate always command. And this command creates a default route for the network even if there isn't one configured. Typically, as a best practice, the second command is not such a good idea. You would want to use the command at the top here, default information originate, and have a manually specified default route to the ISP. And this way, that route gets pushed down to the rest of the network and makes it really easy for everybody if they want to get access to the internet. So let's go ahead and get this configured. First of all, I'm going to go to router 4. Let's look at show IP protocol. And I'm going to remove OSPF configuration. No router OSPF 99. I'm going to do show IP route. Do show IP protocols to see if I have any dynamic routing protocol configured. I don't have anything configured at this point. So I am done on router 2. What I'm going to do is look at show run section OSPF and go ahead and remove OSPF from the interface that is pointing to router 4. So I'm going to type in interface and I'm going to do no and type in this command right here. Copy it and paste it. So at this point, I have no OSPF running on area 2. If I do show IP protocol, I see that I'm only running OSPF on fast Ethernet 00 in area 0. I no longer have area 2 specified. So that's good. Let's see, show IP OSPF neighbor. Do show IP OSPF neighbor. And you can see that I'm only seeing router 1. Router 4 is not even here. What I want to do now is set up a static route, static default route, by the way, which is all zeros, pointing to 10.0.13.2 as my next hop. So let me go ahead and quickly take a look at show IP route to see how it shows up in my routing table. And sure enough, what I'm seeing here is that I've got a default route pointing to this interface. Now, let me verify if I can reach the networks behind router 4. So let's ping 192.168.0.1. Of course I can. And sure enough, it seems like I can reach everybody because I've now just pointed a default route to router 4. And right now, in this example, router 4 is acting as an ISP. What we'll do now is I will go into the routing process, do show IP protocol, router OSPF 200. I'll type in default dash information originate and hit enter. And what we should see by typing in this command is that all of the routers down the chain, like router 1 and eventually router 3, they should be seeing a single default route being injected via OSPF in their routing tables so that router 3 can go ahead and reach all the subnets behind router 4 all the way through. So let's go ahead and check that out. So let's do show IP route. And there you go. You see this route? O star E2. Star means it's a candidate default route. So once again, it's a default route that we created, right? So what that means is anything that doesn't match my routing table, I'm going to send it to this particular entry. And it's very important to keep this in mind, okay? Because typically, like I said, when you have an ISP in your network and you have OSPF as your default routing protocol, you would want to inject a default information originate so all the routers in your environment know what to do with traffic that is internet bound. It will send it to the default gateway that's connected to the ISP. And E2 in this instance means it's OSPF external type 2 route. Okay. So now from router 3, see if you can ping all the way through and ping the loopbacks on router 4, 192.168.0.1. The reason it's failing is why? Can you think of the reason why this is failing? Our packets are making it to router 4 for sure, but you know what's happening in return? Router 4 doesn't know how to get to us. Because remember, we're no longer running OSPF, right? So how do we fix this? Well, I'm glad this happened because this gives you an opportunity to learn. On router 4, we're going to have to specify a static route. So once again, we'll just do all zeros. and we'll type in the next hop of 10.0.13.1, which happens to be router 2's interface pointing to router 4. Okay. At this point, we have end-to-end path. So let's see if we can ping now. Boom. There you go. You see? So what was happening is before I typed in that command in router 4, our packets were making it to router 4, but they didn't know, router 4 didn't know how to return the traffic back. So the traffic is actually dying on router 4. But by specifying a default route pointing to R2, and R2 has the intelligence using OSPF, R2 knows. So let's go ahead and take a look. Do show IP route. See, R2 knows how to get to 172.30 network. R2 also knows how to get to 10.0.31 network. By the way, let me show you another command that is very powerful. If I go to R3 and type in ping IP from router 3, we're going to ping this subnet that's behind router 4, which is all the way to the other side, right-hand side, and we will specify the source of loopback on router 3, which is all the way to the left. This will verify completely end-to-end connectivity all the way through. See if it works. And sure enough, it did. So when you do this, what this does is it constructs an IP packet, an ICMP packet, a ping packet that has a source of this and a destination of this. When you don't specify the source, what ends up happening is when you just ping 192.168.0.1, the source becomes this physical interface. You see fast A1/0. This automatically becomes the source when you're pinging. And this may be okay, but ideally you would want to check end-to-end connectivity to make sure the subnets behind your source or the actual source is able to get to the eventual destination that it needs to get to. Here's a couple of commands you can keep in your back pocket for verification purposes. These are my favorite commands right here. These are the commands that we primarily ran during our lab today. Those other ones are good to know, but these are absolutely critical. And of course, if you guys recall, we had to clear the IP OSPF process. So whenever your OSPF is misbehaving, not a bad idea to go ahead and clear the OSPF process so it resets. And we didn't run debug IP commands today, but you can run these commands to learn about OSPF at a much deeper level. We'll do that in the CCNP class.